Welcome everybody. This is another bonus lecture and it's Christmas, well almost Christmas as I'm recording this, so Merry Christmas if you celebrate that. If you don't and you live in the United States, at least it's usually a day or a week off, so that's a good thing no matter what. So I've been thinking about what to do for this bonus lecture. Now I was going to do another ESP32, some more programming stuff. However, two things happened. A new student mentioned how he was, in the field of electronics, and he was talking about a test he did one time, and he had to kind of reverse engineer a schematic. So he thought that kind of learning how to read schematics would be something interesting. All right, now, right before I read that email, a couple days beforehand, a friend of mine who's another kind of game developer. He used to be like at Sun Microsystems. They, Sun, Java, and so forth, the inventors of Java. They had a kind of gaming division. He was one of the evangelists or directors there of the gaming division. So, anyways, big into games and retro games. And to play some of these game systems on your LCD monitor makes them look really, really, really bad, right? So remember, most of these game consoles from the 80s and 70s and 80s, these retro game consoles, they were played on CRTs, right? Cathode ray tubes, like up here on Wikipedia. And the cathode ray tube works in a completely different fashion than an LCD. Now, depending on your age, you may have never seen a cathode ray tube, right? So if you're fairly young, you may have never actually seen one working, right? You may have seen pictures of them. A cathode ray tube or a CRT, how it operates is it generates electrons, it boils electrons off a filament, and then these electrons are accelerated, all right, with these various coils towards the screen, and the screen is covered with phosphor coating that when the electron strikes it, it gives off light. And there's three different phosphors, red, green, and blue, in various patterns depending on the TV manufacturer. There's three different electron guns that are generating these electrons and then firing these electrons, being accelerated, and the electron gun sweeps from left to right, top to bottom, and generates the image on the screen. The phosphor screens look really, really, really good. They look really rich and they have a nice look to them. And then when you try to play these games from the 80s on a new LCD, the signals coming out of the game systems are NTSC signals. NTSC, they're not VGA signals, they're not HDMI, they're not digital, they're analog in nature, and they're encoded as an analog signal. So the LCD TV has to decode this, extract it, this analog signal, and then render it on the LCD. It just looks really bad. All right. That said, so a lot of people, my friend included, what they would like to do is use a CRT to play their old video game systems, but instead of using an NTSC signal, and of course, if you've never, again, if you have no context, you're not even going to know what I'm talking about, but I'll get to it. If you have one of these old consoles and it puts out a composite NTSC signal, that signal is still analog in nature and it's encoded and it's not digital, so that means it has to be decoded. The pixels, the color, the sync, all has to be decoded, and it's noisy. So the image is still not that good because of the NTSC encoding. However, some of these game consoles, some of these older ones, and even some of the newer ones, have direct red, green, and blue output, like a VGA, right? Like a standard VGA output or monitor. That red, green, and blue is pure data, so it's not encoded, it's not mixed. And then there's maybe some sync signals. And again, I'll tell you how this stuff works in a second. There's some sync signals. So now if you could take that RGB signal and get it into one of these CRTs, get around the NTSC built-in hardware, the decoding, then you get a much better picture. So the point is, my friend said, hey, can you look at, I have this TV, I want to convert it from a normal CRT that takes NTSC signals, right, composite NTSC signals, and can you convert it so that it would work with an RGB signal, or tell me how to convert it and tell me what I need to do. And then he showed me some videos of other people doing it on the internet, and I've done this for many years myself. I've converted these CRTs, so they take RGB signals directly because it's a much better picture. All right, so anyway, in doing that, I had to start looking at the schematics for this particular TV set. So let me go here, and I'm going to show you. So here is my friend's TV. So it's this Sharp TV, and you can see it's a normal CRT TV. It's got a cathode ray tube in there, right? And if you start scrolling through here, what I'm looking for is the schematic. So this is the service manual, so for engineers. So if you scroll through here, and you can see it's got all these kind of technical pieces of information, really, really cool. And this is what the service guys would get. All right, and then here's, the chassis layout, kind of showing from a top view. There's these different PCVs, PWBA, PWBH, PWBB, etc. These are showing these different things. Now, when you, when you're looking at schematics, now again, so the whole idea of this lecture is we're just going to kind of look at a schematic. And there's lots of different kinds of schematics. For example, the schematics that we have been generating in the course, right, are kind of electrical engineering embedded schematics, embedded engineering schematics. So we have a certain way of drawing things and doing things. If you look at schematics from engineers that design television sets, the way they draw some things are a little bit different. They use, some different kind of techniques, and the way that their assumptions and their conventions are a little bit different, but more or less you can kind of figure it out. If you look at schematics, electrical schematics, say from a power engineer, right, who builds power plants, those will start to be a little bit confusing. Or if you look at even electrical schematics from electricians, they'll be kind of harder because they'll have symbols in them you just won't be familiar with. And for example, my air conditioning, I don't know if I mentioned this, maybe in a couple of videos, I mentioned my air conditioners, I've got two of them, and one of them blew out. And I was looking at it and looking at the schematic, and you're looking at the schematic trying to figure out what these different symbols are, right? And you stare at it, and after a while you start to figure out this thing's supposed to be like a capacitor, this thing's supposed to be like a coil, this thing's supposed to be ground, this is a switch, this is a relay, but they've got their own way of doing things. That said, as we look at the schematic, this is really good experience because it kind of gets you to be able to follow signals and then kind of drill down from kind of a block level, a high level, to a schematic level. So that said, when you get like a TV schematic or kind of an appliance schematic, a lot of times you'll see a block diagram. All right, so and that's what we see right here. All right, I'm going to zoom in just a little bit. So here's the block diagram of this TV, and it's showing different things right here. So what is this, for example? Well, that's a speaker. So that's a little coil, and that little symbol, that is a speaker. And you can see sound output. So this is the built-in speaker in the TV set, one of them. And there's probably another one someplace else. All right. So we would look through this schematic. And so my friend, his whole goal is he basically says, hey, I've got this TV, and it's got a video input, right? And that video input takes NTSC. And I'm going to talk about that in a minute, signal. And I want to figure out, can I somehow connect red, green, and blue, an RGB signal, into this TV? Because I know you can do it, because I've seen other people do it on YouTube. Can you show me how to do that and show me where to connect it and all that kind of stuff? So that's what we're trying to figure out here. So this is a big project, not something we're going to do in an hour. Right, but I'm just going to kind of show you some of my thought process, and this is what engineers do. So this might be a job. So he's my friend, right? I'm just going to kind of show him where to kind of put this and tell him some things to watch out for and all that. But if someone were to say, hey, Andre, I want you to do this project for me, I'd say, well, it's going to take maybe 20 hours or 40 hours or 60 hours or 80 hours or 100 hours, whatever it's going to take. I would come up with a proposal. Then this would be a job, and I would sit here, figure it out. I would design it, make a prototype, build it, test it, verify it, and deliver it. Okay, if someone wanted this, maybe they want to make a product out of it, I don't know. But in this case, we're just looking. Okay, so here's the block diagram. And so, the first thing you do is just kind of look at it. At first, it's kind of confusing. So we know that this PWBH and this PWBB, these are boards. And then there's this PWBA board. So this is the big main board, and these are two smaller boards. And we know that because here is kind of these representations of these mechanically. So there's these three boards. This is a pretty simple board, this PWB-H board, and this means absolutely nothing. This is probably an acronym for something, printed circuit, printed something. It's probably printed something board with these different letters H and A, but a lot of times things just are made up. But you can see this just has two connectors and it has this HA here, which I'm not sure what this is, okay? And a lot of things you're not sure what they are. HA, I don't know, maybe heat sink, I'm not sure, have no idea. I'd have to look at it, and this is what we got to do. All right, so there's a speaker. This is where the inputs are. So on a TV set, again, I'm sure you've seen audio and video inputs. Here they are, and this is the composite input that takes NTSC video. All right, and then if we were in Europe and whatnot, then you know, those TVs work on PAL, right? There's NTSC, PAL, and SECOM were the old analog standards, right? And so here in the United States, obviously we have NTSC signals and NTSC TVs. And most TVs will still take these signals, even the modern ones with HDMI. All right. Then we've got this other board right here, which you know, so to CRT cathodes. So this is like a driver board. This is the actual board that's connected to the yoke of the CRT. And let's kind of go back here. So this whole thing is called the yoke. And this is the whole CRT assembly. These are the deflection plates, accelerator plates. And so one of these boards connects right here. All right, so one of those boards connects right there. That's this board, I believe. All right. Okay, now we're looking down through here. So now we're getting stuff that looks more familiar to us, right? We've got, this is a chip, and you can see, let me zoom in here a little bit. Excuse me, I'm going to be coughing and this and that a little bit. I've got horrible allergies right now. My face probably looks all puffy and my eyes may be watering. So I've got allergies like cedar fever. Here in Austin, Texas, we have these cedar trees, and this stuff is hugely allergic. I am hugely allergic to it. So it's just stopped right now. That's why I sound stuffed up and all that. So I will try and edit out most of my allergy attacks, but we'll see what happens. All right. So we see this IC right here, and this is IC 201, and it's saying PIF, SIF, chroma, video deflection. So these are obviously abbreviations of something. So PIF stands for something, SIF, chroma means color, video deflection, that's the video deflection circuitry. So this chip drives the display. This drives the actual CRT part, okay? So this is good. So we know that, and then this, you know, all these various signals here in these kind of block diagrams, they represent either a chip or chips or analog components. So this, for example, Q201 IF preamp, this stands for intermediate frequency preamp. SF201, this is a SAW means sawtooth, so this is some kind of sawtooth generator IC. Q401, it's probably a transistor, could be a transistor or FET. You know, and you just kind of look through these things. Now, of course, this is TV technology, so I don't expect you to understand it, but you're just looking through these blocks and trying to figure these things out and see what's going where. So here's the driver chip that drives this, and then over here, let me see if I can get my little hand here. Yeah. Then over here, there's another IC, IC 2001. Now, this is interesting, and this says system control. And it's connected to, let me back out a little. It's connected to this chip here. It's got RGB coming out of it, going into this chip, so that we're going to swing back to that. It's got this mute control here, which is kind of going up. So we've got this mute going up here to this sound chip. So wait a minute. This is the speaker. This thing right here, so IC352, this says R sound, probably means right sound, right channel sound. All right, and then there's a signal here, which I bet you this one right here is sound. See, it's audio out. So there it is, audio out right there. So this is the right speaker. Now, I said there's probably a left speaker, but on this one there may not be. Nope, so there's a single speaker. Here's the output, and then one of these is a mute control to turn the speaker off, and then the other one is this line right here that I'm following, is a delay driver. So this is relay driver, and then there's a relay regulator. This looks like it's power. Yeah, this looks like it's power going into this chip. So anyway, that's what you do. You gotta just start tracing things for what you're kind of interested in. So again, a lot of these things, and I don't even know what they stand for because I'd have to look and figure out what these guys mean by these abbreviations a lot of times. You have to figure it out, right? Now, I do a lot of video hardware. I've built a lot of video systems, a lot of video hardware, graphics chips, all those kinds of things, and obviously game consoles. So I do a lot of NTSC, PAL, VGA, RGB, all those kind of things. I mess with many, countless TV sets. So I've gone through this, but every single one of them has some different things in it so that you're not quite sure what these little symbols mean, like ATT. Okay, this is a switch right here. So there's an audio here, there's an external audio in, there's a TV audio in. This is a switch, and so this ATT right here, okay, have no idea what that means. But this is some kind of switch here, so it allows you to switch between these two things. ATT could mean attenuation, right? And right here, YN, so in TV parlance, Y means luma, or the brightness signal, right? And that's what Y means. So this means YN, luma in, luminosity in, and C is the chroma or color signal, CN. So, you know, you kind of figure out what you know, and you got to kind of figure this stuff out, right? All right, but again, we don't really care about that. We're going to come back and figure out how we would convert this into an RGB monitor. But I just want you to kind of look at it just for a minute here. So this chip here kind of is this controller chip. This is this video driver chip. And then we can see things here. Now in this schematic, again, it's a block diagram, so you're not going to really see many parts. But we can see, hey, there's a transformer, right? There's some kind of transformer. This is, these are coils, right? These are inductor coils. There's some stuff going on here, right? More, so this is another transformer. So this is it's got multiple primaries and multiple secondaries, right? And these two lines, that means the core of the transformer. So it's got a common core and there's primaries and secondaries. So that's interesting. Some more, these are relays. So there's a coil, right? There's the core, and then here's the armature. So these are relays, right? There's our line coming in. There's our power coming in right there. There's a fuse symbol. So you kind of can make your way through this thing, right? Just slowly and surely, kind of what's the whole, you know, global view of things, right? Now, after you've kind of figured that out, and I'm going to tell you, the only thing we're going to care about are these two chips for what we're going to try and figure out. Then we go down and we start looking at the actual schematics. All right, and then if you're a TV service guy, these waveforms right here represent what things should be doing at different test points. So if you're testing the TV and you're trying to debug it, you're trying to fix the thing, that's what this manual is for, you need to be able to see, hey, this horizontal signal is number 1 and it should be 0.96 volts peak to peak. This, if you go, this is signal 12, it should be 5.4 and it should look like this, etc. All these should look like this. So if something says at this test point you should see a number 19, it better look like this one. And it better be 260 volts peak to peak, okay? All right, now here is the schematic. So here's where things get fun. Let's just close that. That doesn't help us any. So here's the schematic, and I'm going to zoom out a little bit. And yeah, there it is. Okay, so that's the whole of it. And let's go back in. So there's that IC201. There's that video driver chip that we were looking at up in the other one, right? That's the top chip, the video driver. Now someplace there's going to be that video controller chip, and it may be on, it's probably going to be on another page. I'm going to zoom out. So here it is right here. So there's that video controller chip. So there it is right there. So you can see it's very complicated. But now we know every single one of these parts, right? What's that? There's a transistor right there. What kind of transistor is that? That's an NPN transistor. These are capacitors. This is a capacitor. These are resistors, right? Here's another capacitor. So this symbol right here, this is an electrolytic capacitor, and this is the way they do it with these little lines, but they put the plus and minus to let you know it's electrolytic. There's resistors. We know all that. That's easy. More resistors, more capacitors. What's this thing right here look like? So we look here, and it's got an input, it's got a ground, it's got an output. This says KIA 7045A reset. Not sure what that is. We'd have to look that up. It's a 3-terminal device. It could be some kind of regulator or something else, but we would just look that part up, and we're going to see how to do that also. Here's an IC. So this is IC 2101, and then so it's telling us this is an EEPROM. And then you can see here's the I squared C inputs. So I've talked about that a little bit maybe. Again, this is not a embedded course. This is not a course about microprocessor, microcontroller design. It's about electronics, basic analog digital. So we haven't talked about protocols like I squared C or SPI or UARTs and all that. But anyway, this is a I squared C EEPROM, electrically erasable programmable read-only memory. So that's a memory. And then this right here, I'll tell you, is a processing chip. I've looked this up, and we'll go look this up. This is a processing chip. This is a processor right here. All right. And let's see, is there anything else interesting? Over here, we can see some of this nastiness, all this analog, a lot of analog electronics. But again, we know what all this stuff is. There are diodes, right? So this is a kind of bridge rectifier situation going on here. There's that multi-tap transformer we saw. Let's see, right here, FB702. This might be a ferrite bead. This might be how they draw a ferrite bead. And again, we have to look at the parts list and say, what is FB702? Is that a ferrite bead? But that may be how they draw it. So FB702, for example. And there's a Schottky diode, right? Zener diode. There's a Zener diode, right? And this is it looks like it's an 18.5 volt Zener diode to keep that clamped, this overvoltage protection signal at 18.5. That's what that must be. Let's see. And anyway, and then here's our little ground symbol, right? These little ground symbols. So this is us going through this schematic and kind of looking at things, all right? And then, and let's see. And then here's another one showing what's connected to that actual CRT. This is all these signals that are connected to it for red, green, and blue. And this is the actual driver section. You can see red, green, and blue, ground, 9 volt. This is 9 volt. B means usually bias, 9 volt bias. And this kind of is what's driving these drivers here. So we're not going to mess with red, green, and blue there. I'm going to actually show you a different place we're going to do it at. All right. So before we dive into this, we've been talking about 20 minutes. Before we dive into this completely and kind of look how we would want to do this, what I want to do is I want to just talk briefly about the whole idea of CRTs. And let's close this. So definitely go on Wikipedia and look up Cathode Ray Tube. I'd like you to do that and just do this and kind of read this a little bit. It's very interesting, and so you just get an idea of what's going on here, right? So go through there and kind of see that the first CRTs were actually invented in the late 1800s, believe that or not. I think it was 1898 or something like that. If you look through here, I bet you it'll say it. But yeah, unbelievably old technology. Yeah, cathode rays were discovered by John Wilhelm Heitorf in 1869. And then, yeah, Crookes showed that it could be deflected by a magnetic field in 1890. Electric Crookes showed they could be deflected by magnetic fields, 1897. Yeah, so you got to read this, but that's just crazy. To think about these people were doing things in the late 1800s, how nutty is that? This is advanced technology. You're talking about subatomic particles. Crazy, crazy. So take a look at that. Then the other thing I want to talk about, NTSC signal spec. And again, if you're not interested in CRTs and NTSC and video signals and all that, you can just not care about this too much. But the whole idea, engineering is about a lot of times learning something new because a client wants you to do something. So you may have a situation where someone wants you to make a video converter from NTSC or VGA or RGBA or this or that to HDMI to whatever. And so you're going to have to go read this stuff. So it's good experience to learn how to look this stuff up and understand it. So NTSC stands for the National Television System Committee. And in like 1950, it was formed. The first standard was developed in 1941, and then the second in 1953. So the standard's very, very old. And so here's the whole thing. NTSC is, basically was developed in 41. The kind of one that we use is 1953. So this is 50, 70 years roughly old. 70 years old, and it's still not bad. I mean, it's amazing that it was invented that long ago. All right, so you can kind of read through here. But the technical details that I want to get to, and like I said, there's NTSC, and then over in Europe there's PAL, which is a French word. It stands for something French, which I can never remember. And then there's SECOM, which is sequential color and memory, I believe. And then PAL, we'll look that up in a second because I can't remember it. Even though I'm half French, I should know what it stands for. But what I want to show you is, let's see if we can see a signal here. I'm sorry for scrolling. And there's versions. There's version of it. Let's see. Do they say what PAL is here, what the acronym is? No. Yeah, phase alternating line. I feel like there's another something French. I can't remember. Anyway, phase alternating line. Yeah, so PAL is similar to NTSC. It's maybe a little bit better in some ways. All right, but I want to show you the signal, and no. Okay, so let's go here, NTSC signal, no spec, and let's go to images. Yeah, so this is, and you know, you'll see this if you read my book, my Black Art of Video Game Console book, or my Design Your Own Video Game Console book that comes with this course, which is basically just the e-copy version of it. You'll see figures like this inside of my book here. And let's go here and open this up. And of course it did that because it's a transparent image. All right, let's go grab another one. Let's see. This one's not bad. Okay, and so what are you even looking at here? Now, this is an analog signal, so again, I don't expect you to understand this. This took a long time for me to understand and study and all that, so I don't expect you to understand it in 5 minutes. But this right here, what this represents is a video line. So this is the signal of one single line of video in an NTSC signal. All right, in what's called a baseband signal. Now, NTSC is modulated, so you've got channel 2, channel 3, channel 4, channel 5, and then the base signal is modulated on a carrier. Forget about all that. This is just the base signal. So this is the base signal before modulation. So this represents one single line of pixels across the screen. Then in addition to this, there's line. So it draws all these lines on the screen, and then there's a vertical sync signal that tells the electron gun to go back up to the top and do it all again. Now, in each horizontal line, there's different portions of it. So this right here is the horizontal sync, and at the beginning of every line, there's a sync, and a signal happens that goes in the negative direction. This tells the TV receiver, hey, I want you to take that electron gun and bring it back to the left point of the screen because we're going to draw a new line. All right, so this electron beams, red, green, and blue, are scanning across the screen constantly. This says, bring it back and synchronize to the left side of the screen, and I want to draw a line. All right, then it says, okay, great. Then how did they encode color? Now this is one of the most interesting things, NTSC. It's also laughingly called never the same color twice. How color is encoded, it's not red, green, and blue. How color is encoded is as a phase angle. All right, so basically what happens here is there's this thing called the color burst, and this little oval really looks like this. So this is a zoomed in version here. And what it is, it's 8 to 10 little pulses of a certain frequency, right? And that certain frequency is the color burst frequency, right? And the color burst frequency is what, let's look that up, get the actual, 3.45 megahertz color burst. And you can see it's been a while since I've done old-fashioned NTSC, even though I've done an enormous amount of it. 3.579545 megahertz is the color burst frequency. Okay. So you create a sine wave of 3.57, right, megahertz, and you put out 8 to 10 pulses of that. Then you put that on top of this signal, right? What's going to happen is that TV receiver is looking, it's got a filter looking for this 3.57 megahertz signal. The second it sees that signal, it tries to lock onto it, and it's got 8 to 10 different waves, right? 8 to 10 different samples to lock onto it. So it starts trying to lock onto it, and finally it locks onto it. So now it's in synchronicity with the signal. All right, now, here's the interesting part. Then we come over here a little bit more. This whole thing happens in 63.5 microseconds. So we'll talk about that in a second. Now we start drawing pixels. So this is where the pixels get drawn. You got 52.6 microseconds to draw pixels. In this time, you're going to draw the pixels on the screen. And there's about, depending on what you want to do, about 160 pixels or color clocks that you can control the color of. So on a normal SD TV, old school CRT, you only had about 160 pixels across that screen, believe it or not, that you could control the color of. You could change the luminosity at a much higher frequency, but or much higher pixel rate, but the color was only about 160 pixels. That's it. Now, how the color is encoded is like this, is as you are drawing the Luma signal, so this is basically this Luma signal, as you're drawing each one of these pixels here, the phase angle of that Luma signal compared to the phase angle of this color burst, depending on the phase of it, relative to this reference frequency, depending on the phase of it, that'll be the color. And then as you go around 360 degrees, you would get different colors. I know this is super crazy, isn't it? So if we say color burst circle, maybe. Let's see. That didn't help us. Let's see. NTSC color burst circle. Yeah, here we go. And so what this is showing is at phase angle 0, right, you get kind of a blue. And then as you rotate around and change the phase angle, so from your reference color burst, as you shift it to create different colors in that pixel stream, here's magenta, there's red, there's yellow, there's green, there's cyan, etc., right? That's how you encode the color in the signal. So it's encoded in phase. Super brilliant to encode it in phase, but kind of hard to extract out because you have to have filters and phase lock loops and extract this information. So the whole point of it is, this is a really nasty analog signal. The sync is in the signal. The color is in the signal. The luminosity is in the signal. Horizontal, vertical sync, all in the signal. So basically everything is in one single signal line. So you can encode this in a signal line and ground, and then you have your video signal. That's what your component video, or excuse me, composite video on your TV set, the composite, the old school composite, when you plug that in, it's looking for this signal and a ground, and that's it. It's all encoded in here and has to be extracted. So during the encoding and decoding, it just gets really messy and yucky, and then the signal doesn't look good. That's why we like red, green, and blue, because it's like red, green, and blue. So I want the pixel, this pixel to be red, green, and blue. Then the next time frame, I want this one to be this red, green, and blue. Then typically a RGB monitor has a separate signal for sync. So it'll have an H sync and a V sync separately. Or it could have them mixed together, called composite sync, right? Or sometimes even if they want to save signals, they'll take the sync signal and actually embed it in like the green. So it'll be sync on green. So you see red, green, and blue, and there's only 3 signals. You're like, where's sync? Well, it's in the green. So you'll see red, sync on green, and blue. And sometimes they actually put it in the other channels also, but the majority it's in green. So anyway, the whole point is that's what NTSC is all about. It's an analog signal invented in the 40s and 50s, and that's what all our TVs have been using, or a variant of, and European TVs that use PAL and SECAM are very similar. All right, now, if you want to know more about this, in the book for the course, let me go grab that, the Design Your Own Video Game Console manual here, my book. If you go to chapter 9, and go to the graphics section 9.9, I'd like you to read the graphics section 9.9, just kind of go through here. And it'll show you, and you know, when I wrote this, I have all the details here much better than I have off the top of my head now. So here's the distribution of NTSC, PAL, and SECAM, all right? And then here's how the raster works. So you know, like I said, I've done a lot of work with NTSC signals and generating them with hardware and software. And this is you know, a very, very good explanation of this at a practical level. So, you know, I would highly suggest you read what I wrote here. It took me a while to generate all this for you and for readers. So try reading this and you'll really understand what's going on. And let's see if there's anything else here. There's that video signal that we just saw, with some more details, and then getting some more nitty-gritty here, what these signals need to be looking like. And then I talk about, you know, how to generate them, how to generate this stuff in software and hardware, and then talk about it in the abstract. So read through that, that'll kind of give you an idea of, how to do this stuff. All right, now let's go back over here to our schematic, and this one here. Okay, so we want, to basically say where inside of this TV schematic, this TV set, if we had a red, green, and blue signal, and if we had red, green, and blue, we're going to need sync also, where would we put it? So I have a game console or a computer that puts out red, green, blue, and sync, and I know this TV can do it because it's an RGB, CRT. At the end of the day, red, green, and blue. The hardware is here to do it. But where on earth what do I do? How do I do this? Okay, so again, this is a big project, but I just want to kind of show you my thought process and how I get into this. So the first thing is, if you're interested, let me go back here, and let's see here. If we just type in, let's go CRT to RGB, we'll just do that, and then we'll go back here. And then, oh, well, this is interesting. So what this is showing is in these pictures, these are people who have done this and then showing the different video quality. So you can see right here, even though he's got this on this image right here, and then you compare this image, it's much cleaner. And then again, this image right here, and then you got this image right here. It's showing these, all these different monitors. So this is a composite video, and it's horrible. Then you've got this RGB monitor one. You can see his eyes. Everything is just so much clearer. Here's another picture. And RF composite. This is actually a good one. Let's see. Can we open this in a new tab and make it big? And of course not. It opens up the whole thing. This is probably a good page right here too. Yeah. So again, this is hard for you to see, but you're looking at a monitor of a monitor and video of video. But you can see here's RF. So this is the modulated NTSC video, RF, radio frequency. There's the modulated video. And that's up at some high frequency. And then now the composite signal has been extracted through demodulation. So this has been extracted, but it's still an NTSC signal. So they both look, the same. They both look bad, right? What's interesting here is this anomaly, which I'm not sure, it looks like the pillows were there in that picture and then not here, but they're almost identical. Then we go to S video, which is super video. And the difference between S video and composite video, in composite video, the luma signal, the brightness, and the color are mashed together in that single signal that I showed you, right? But in S video, super video, luma and chroma are separate. So this is actually a pretty good video standard, an old video standard. And you can see this looks much better. Again, you can't see it that well, but if you look at the character here, it's blurry. Everything is not very clear, but here it's much clearer. All right. Then here's an RGB. So forget the YUV part. Just this is an RGB signal. So this is extremely clear. And then here's another RGB. Look how clear this is. This looks like a computer display, right? So that's why people like RGB. It's extremely clear. Even on, if you take an old CRT from the 70s or 80s and you forget about all the NTSC hardware and jump over and plug directly into the RGB driver and then inject an RGB signal from a game console or computer, it's crazy how good it looks. You're just like, oh wow, I cannot believe how good this looks. Like, here's another example. Sonic the Hedgehog. There's composite. Look how horrid that looks. Just a train wreck. I can't even see Sonic, right? Look at that. You can actually see everything perfectly, just like a computer display, like an LCD or a modern display, all right? Now let's go back here, and let's go back here, and then go to all. And again, this is a process, guys and gals, I don't like editing everything out. I like you to see how this goes because the stuff doesn't take 2 minutes. It takes 22 hours to do, right? It takes a long time being an engineer in engineering and doing things right. We got to find this stuff out. We got to figure it out. So if we type in CRT to RGB, we could even put mod in there. So I want you to kind of do that, CRT to RGB mod, if you feel like it. There's some good examples of people that have done this, and you can read about it and so forth. And kind of go through here and watch different people do things. Now, the thing you want to be careful of, a great majority of these people do not know what they're doing. Some of them sort of know what they're doing, but they're hacking things without understanding side effects and so forth. So you got to take things with a grain of salt because a lot of people don't know what they're doing, and some of them that are good admit they don't know what they're doing. So they'll say, "Hey, I talked to an electrical engineer and they said do this and this," and then they go and modify the board and so forth, but they don't know exactly what they're doing. So just be careful when you're watching stuff. And again, if you're thinking of playing with doing any of this, uh, and for fun, maybe you are a retro gamer like me and you want to do this modification, please do not mess with the television set if it's plugged in, right? Make sure you learn how to discharge it, wear rubber gloves, rubber shoes, wear goggles, glasses, if you're probing around, messing around, because the TV will absolutely kill you. So be careful messing around with the CRT TV. Know what you're doing and just wear protection, your goggles, your glasses, your gloves, rubber sole shoes. Don't mess around with this stuff. You see these guys playing on here, soldering and probing and trying things, you could really get hurt. And it just shocks me the kind of things that people do thinking it won't happen to me. All right, so anyway, there are videos on here so you can see other people kind of doing this. All right, so that's that. Now, so let's go and so one of the ways that people have done this is this. They take so if you do something like this, if you say TV with OSD, on-screen display, right? And we'll do an image. All right, this is what that means. So here's our TV, and of course I click on the worst possible image. All right, thanks for that. Here's a TV or a computer monitor is displaying on this right now. Windows, it looks like, right? Windows 7 or 10. But here's the on-screen display. So the TV set or the monitor generates this on-screen display and then overlays it or mixes it with the video signal. All right. Now, a lot of these CRTs have on-screen displays, right? They have on-screen displays. You press a button like, now I'm looking at a monitor right now as I'm doing this, but over here is a TV, which you can't see. I can press menu and then video can be playing and I press menu and it just overlays on top of it. So that hardware, if you recall, inside of this schematic, and let's go here and let's scroll down to that block diagram right here. And looking at this white screen is like burning my eyes right now with these allergies. I can't even tell you. I can't even talk about it because then it makes them hurt more. All right, so let's go to the block diagram. So check this out. There's that video chip. This is a chip that drives the CRT. But here's the controller chip. And that controller chip, this is a microcontroller, a microprocessor, microcontroller here that controls the whole TV set. This is the brain. But it also generates this RGB signal right here. This is the on-screen display. So what a lot of people do is they say, well, wait a minute. Here is this controller chip, this microcontroller that controls the whole TV set. When you turn on the on-screen display, this red, green, and blue is an RGB signal, and it goes right in here. So there's an input for red, green, and blue right there that then this video processor chip will then take and then amplify and do everything it needs to send to the driver board, which is connected to the yoke, which is connected to the CRT. So rather than us messing around with the driver board and high voltages and all the crazy stuff, we can inject the signal right here. So right here. So now here's what these signals mean. And here's another thing about schematics. When you see a thick line with a bunch of thinner lines, it means it's a bus. It just means that this single line represents all of these signals. They're not mixed together. They're just on a bus. That's all. So you don't have to draw 4 signals. Okay. This red, green, and blue is the RGB that we want. And then this BLK, this is not black. This is blanking. So this signal, what this does is this blanking signal goes out and it says to turn off the on-screen display. So the blanking signal turns off the on-screen display so that the normal video shows, or you turn on the on-screen display and then it goes through. So we want to control this blanking signal and we want to inject into this red, green, and blue. All right, that's all we need to do. All right, so now the question is, all right, some things come to mind. And again, I don't want to do this whole project with you because it's very complicated. But So we've got red, green, and blue. What format are these red, green, and blue signals in? Well, they're in analog. They're analog voltages, each one of them. And they range from about 0 to 1 volt, okay? And actually 0 to like 0.7 volts is accurately where they are, because there's the way that this video specification is, it's like 0 to 0.7 volts, and from 0 below, like to negative 0.3 volts, is the sync range. So anyway, it's about 0.7 volts analog. So we know that. All right, now the RGB coming out of whatever device we have typically will match that, but we have to look at it. So first we have to understand what these RGB signals are, what their format is, their analog, what their voltage ranges are, so that when we inject the RGB signals from our video game console or our computer or whatever it is, our 8-bit computer or video game console, we put red, green, and blue in here, right? And then we basically say, turn on this blanking signal here, so that we turn off the normal video signal, right? And then we inject the signal in here. We want to make sure that we match what this chip is expecting. Okay, so that's very important right there. All right, now, so we've got red, we got green, we got blue, we got this blanking signal. Now, let's go look at the schematic. All right, and also, so let's look at these two chips. So this is IC201, and this is IC2001. All right, so remember that for a minute. And let's go down the schematic. Let's take a look here. All right, so there's the IC201, our video chip, right? And now, so here is that CRT out. Those are those signals right there, which are going to the driver. So now we're looking for, where are those signals coming in from our other guy, the red, the green, and the blue. And if we look here closely, here it is. OSD in, on screen display in, red, green, and blue, and then there's that blanking signal. Now check this out. So here's the blanking signal, and it's got a pull down on it. You know what that does. So that keeps it pulled down so it doesn't float. So to turn this blanking signal on, we're going to assert a high to it. Now, I'll tell you right now that the blanking signal is digital. All right. So we got to look here and we got to say, well, this chip is this a digital chip? Is this well, obviously it's analog and digital mixed, but what power supply does this use, right? So we have to make sure what it is expecting for a power supply. So if you look here, so check this out right here. Here's a 9 volts right here, and this is going into this V sub CC. So check this out. This says 9 volts right here, going into V sub CC, I think. All right, so we gotta figure out what the voltage is that this thing is being powered. So V sub CC is at 9 volts, I believe. All right, and then again, you got to look at all these different signals. Now check this out. There's a SCL and SDA. That's an I squared C bus. So you can. This actually has I squared C bus to control it. So that's cool. We can do things to it. Now we don't even know much about this chip, but we're going to find out in a minute. I'm going to show you the chip. But you know, you kind of go through here. We know that we need this red, green, and blue. We know we need this blanking signal. Then we can see on red, green, and blue, these are capacitively coupled. All right, so they're capacitively coupled signals. So whatever signal we inject into here, this from this red, green, and blue, it's going to get capacitively coupled. And check this out, there's pull downs on here also, capacitively coupled. So whatever the signal that we send in here is going to basically get the DC component's going to get removed off of it. All right, okay, that's fine. Now we go look here, and so here's this whole bus, red, green, and blue. And this blanking, it's on this line right here, this line right here, this line right here, this line right here, this line right here. So red, green, blue, and blanking. This is how the schematic shows things go to another page. So red, green, and blue, this is basically a signal to another page. So now let's go find the other page. There's our speaker, right? Remember that? So let's go find the other page. So here's the other page. And then we go over here. Oh, there's our red, green, and blue. And our blanking signal. Now it buses them back up, just represents a bunch of wires. I know it's hard for you to follow this, so I'll just kind of go on here with my little hand, go up here, and there we go. So it goes to these pins right here. And then there's a couple of resistors here. So there's a 6.8K, 6.8K, and another 6.8K. and another 6.8K. So all of them just have a 6.8K for the red, green, and blue. And now if you look at, so now let me show you what's happening here. So we've got 6.8K coming out of each one of these. Now this thing, this chip, this IC2001 is the driver. This one's driving the RGB signals for the on-screen display and sending them to that driver chip on the page above, right? So there's a resistor coming out here, right? And it's 6.8K. Now let's go back up here, all right? And let's look at all those red, green, and blue inputs right here. Check it out. So then there's a 2.2K, right? And then there's this 2.2K, 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 and then a 3.3K. All of these are to ground, and then from that node goes through a capacitor. Let's look at that circuit. Let's look at that circuit, all right? Let's go look at that. So this is what these circuits look like. Wrong one. And so we're just engineering here. We're trying to figure out what is going on here. All right, so I'm just going to kind of draw this for you. So here's the red, and it comes out, and then it looks like this. So there's the red signal, and I'm going to do the green in green, because for once we have colors of things, so I'm going to take advantage of it. And then here's the blue, red, green, and blue. All right. Okay. All right. And then let's go back here. So let's draw these in. And this guy right here, this is, and again, I'm drawing on this graphics tablet, which is way better than drawing on the mouse, but it's still not easy to do, I'll tell you that. So this is this controller chip, and again, we're gonna, so it is not this IC201, but this IC2001. This is the chip that actually generates those signals. So they go through a 6.8, and then on here, each one of them, red, green, and blue, it goes to ground through a 2.2, and then the blanking is at 3.3. All right, so now, so this is the 2001 IC 2001 chip. So let's now put those values there. All right, so this one was 6.8 K ohms. This one is 6.8 K ohms. Oops. Because we're just trying to figure out what's going on here, right? What's going on? What's up with the resistors? All right, and then each one of these goes through a capacitor, right? And then the capacitively coupled signal then goes into that driver chip. Okay, so if we go back here, there's those capacitors. They're all just 0.1 at 16 volts. Just means they can tolerate 16 volts. So these are just 0.1s. And let's get the back red here. So this is 0.1 microfarad and 0.1 microfarad. And last one. And then, the whole idea here is we're just trying to make little simple models of things. And then if we have to, we'll go to Proteus, the simulator, and then we can simulate these. So these are all going in to the inputs on the other chip. All right. So this one is the controller chip, and this one is the driver chip. And it's funny, when you've got allergies this bad, it's like you're high on drugs. Everything, you're just woozy, woozy, woozy right now, which is what I am. All right, and I haven't taken anything to be woozy. It puts you in a state. It's terrible. Anyone who has allergies, I'm sure you can empathize. Okay, so here are our inputs, and signal is flowing. Oh, what color are we going to do signal? How about this color? So signal is flowing this way in each one of these, obviously, right? Same direction in each one of them. The signal's flowing that way. Okay, now what's interesting here is these right here, these resistors are 2.2K, 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 and then what's our last signal here? We'll just let's just go ahead and draw it in cyan. This one is this last, and unfortunately, I'm gonna kind of go like this for you guys, and I'm gonna kind of just put this right through here, like this, and there's that. and this one again is 0.1 microfarad. Is there a coupling capacitor on there? No, there's not. The blanking signal is not AC coupled, right? Which I would expect it not to be. All right, it's not AC coupled because it's just a digital control signal. All right, but this is 6.8K here again, and then this one here was 3.3K. Okay, so what's going on with resistors? Well, what's going on with resistors is this. Whatever signal comes out of here, 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 and this signal is a digital signal. Whatever signal comes out of these three analog ports, this is a voltage divider. So this is a voltage divider. So the voltage divider is just 2.2K over 6.8K. All right, so 2.2K over 6.8K times Vin, so V out equals this times Vin, where here's Vin coming through here, right? And V out is going to be the final voltage here, right? So basically, if we just look at this right here, get our calculators out, you can clearly see that's a third, right? But we just 2.2 divided by 6.8, right? It's it's 0.32, but basically a third. So the whole idea here is whatever signal we put in here, we're going to get a third of it out. So if we put out a volt, if this is say 1 volt here, right, out here we're going to get about 0.3 volts. So that's what this is doing. This is scaling this because whatever voltage this is putting out, this IC201, it's a little too high for it, right? So these resistors are picked to scale that voltage down. Then once you have that scaled voltage right here, right, then we're going to get through this capacitor, and we're going to remove the DC component out of it, so that what we're going to have through here is a signal that is like this, where here is where here is 0 volts here. All right, so this basically removes the DC component, and then we have this kind of signal coming through here, then the driver can use it. Now, over here on the digital signal, this is the blanking control. This is just digital. And so again, he's got a 6.8 and a 3.3. He's dropping it by about 50%, right? 3.3K over 6.8K, right? That's about 50%. So V out equals this times V in. So whatever the voltage is here, it was 5 volts, whatever. Now it's going to be 2.5 volts over here, right? So if this signal over here happened to be a 5 volt pulse, we're just going to get a 2.5 volt pulse over here, all right? A little bit smaller. That's all. That's all that's going on there. So those three signals are what we have to mess with and inject into. Okay, so let's hold that there for a second. Now, the other thing that I got to do when I mess around with this kind of stuff is I need to see, these chips and understand them kind of in detail. That's how I read about what these red, green, and blue levels are, and the blanking and all this. So we need to figure out, what these chips are. I mean, I can see the pinout of it, but I mean, I want the data sheet for the chip, right? So let's back out here for a second. So IC201 is it's got 1 times 325 CE. That might be a part number. I'm not sure, but I know it's called IC201. And again, this is reading these things. Depending on who makes them, it's kind of like a detective novel. All right. Then this one's IC2001, and it says 1 times 3366 CE. Okay, I'm going to tell you right now, there is no way that both of those chips have similar part numbers. They're radically different technologies. This must be an internal part number for Sharp or Sony. Who made this thing? This is Sharp, yeah. This is an internal number because they make millions of TV sets, right? Maybe billions of TV sets. And so they have their own numbers for all of their ICs and parts, but we don't care about those numbers. And where is it? Right here. All right. Okay, so we just need to go look up on a bill of materials if there is one. So the question is, in this service manual, is there a bill of materials or a parts list? Let's go see. So we go down here. Here's the actual layout on the boards. Real nice. You can see all that. Cool. And again, this is great to look at. This is the guys who make these TV sets are analog gods. They know what they're doing. So, it would not hurt you to look at all this stuff, see the layout. All right, and Okay, here we go. Parts list on page 21. There's a parts list and it's just saying all the different parts. Now here's our integrated circuits. There's our 201. There's that internal number that we just saw, right? And there's that 2001 and there's that internal number, see? And they're so similar, right? I'm like, there's no way those are actual numbers. This is the number. There it is right there. So it's a TA1268AN is the 201 driver chip. And then it's a TMP 8700 CPF 164. All right, take those two numbers, and now let me blow your brain up a little bit more. Take those two numbers, and then Google them. You start Googling them, right? So this is the process, because I do not recognize either of those, and no one does. So I take this right here, TA1268AN, and we go into Google. All right, let's see if that comes up. All right, and then immediately we got lucky and it came up on datasheet. Doesn't mean it's the right chip, could be anything, right? But we know it's a driver chip. So then we look here and we say, okay, TA1268 is kind of coming up without the N part, close enough. It says I2C bus control NTSC chip color. That's it, there it is. And we click it, and then here we go, data sheet. So there's the actual data sheet. All right, and we could click that, and I already did this, but it's going to come in this little viewer here. And so this website's called alldatasheet.com. So there it is. There's our chip. Now I already did this for you, and it's actually sitting right here. There it is. So we'll look at that in a second. So there's that chip right there. So that's the driver chip. But now there's the controller chip. And, you know, there it is right there. But let's not cheat. All right, so there's the controller chip. So now let's go back to our schematic. And our driver chip was this one, but the controller is this one, and it's this TMP 8700, this guy. All right, I'll tell you, I had a hard time trying to find this one. So I'm going to go back here and I'm going to just Google it. And when I Google it, this came up, and then there's a reference to it here, right? And then if we say here, we could say datasheet also, all right? And then so there's a reference inside of the, and then here is the data sheet, which we could probably go to datasheets PDF here, and then hopefully I don't end up someplace weird. All right, and then it says click to download PDF. So I think I found it here, and what is it? It's an 8-bit microcontroller, all right? And then here is it showing the first page here, whatever. So we'll just, you know, click download PDF, and we got the same thing, and there it is. It's 161 pages, no joke. You got to read through this a little bit. But you know, if you look at the specs of this thing, it's an 8-bit microcontroller, 16K bytes, whatever. It's got these different versions of it: RAM, 1K byte, 2K byte. So let's go look at the real version. All right, so forget about all this stuff. We already did this, and I'm just going to close these windows. And I've already got it here. Okay, so here is the driver, and then here is the other chip that we just saw, which is the controller chip. So now we know the controller is like a microcontroller. It controls the on-screen display. That means it's analog, though. It's a microcontroller that has analog stuff in it. Sure, they will make chips that have analog stuff in it because it goes in a TV set. And if you make 10 million, 100 million TVs, it behooves you to make a chip just for a TV. So we're not going to read through 160 pages, but we're going to look here and just kind of look through this a little bit. And I'm looking for clock generator, reset circuit. I am looking for, is there any kind of video stuff in here? Remote control signal processor. Look at that, remote control. That's just processing the infrared from the remote control. A to D converters. Check it out, on-screen display. So inside of this chip is an on-screen display circuit. There we go. So now the A8700, so on and so forth. There are 251 characters, and any characters can be displayed on an area of 32 columns by 8 lines. So it explains what the graphics capabilities are here. It shows the on-screen circuit, what it looks like, and then the output signal generator. Oh, there's our red, there's our green, there's our blue, right? And then this is Luma, or it's BL, which means that blanking control. It's showing what this thing does and so forth. So there is that circuit. and then we would read through here. Now we don't need to program it, we just need to know about its levels, right? So we would go through here, and this is all very interesting. So I mean, if if you have time, kind of parse through it like I am right here. It's very fascinating, and I've read so many of these data sheets, probably hundreds of them in my lifetime, maybe more. Understanding how CRT controllers work and graphics chips work. So you read through here, and then right, and then here might be some information about signal. Maybe. I'm looking for the signal specifications, which might be in the DC or AC electrical characteristics in the bottom of this data sheet. But I'm just kind of scrolling through here to see if I can pick up anything with my eyes. Here's all the register sets inside of the chip. Very complicated, very advanced, obviously 160 pages. It's not a simplistic microcontroller. And then you ask yourself, well, how do they program this? Well, they have a tool set. They write code. It's probably an assembly language for this thing. And then, this is kind of showing some of the video signal, and then how's the on-screen display. So all this stuff in here, and some more showing you some of these signals. It's probably in this area talking about those levels that we want to talk about. And yeah, so reset, okay, so this is interesting, oscillator. So this is kind of showing what these circuits look like. And yeah, so here's what these circuits look like. And the question we have, these are each one of the I/O ports. That red, green, and blue, what does it look like? So here's the electrical characteristics, output currents, input voltages, all this kind of stuff. And then what we're looking for is that red, green, and blue, and might be here. And it's going to typically be under AC characteristics. And again, I don't want to sit here and figure this all out right now because this is a big job. But anyway, this is what you do. You go through here and you figure all this stuff out. Okay, now, so we're running out of time, but we've got the data sheets. We kind of know what we want to do. The deal is this: we want to, or I want to. We have this situation here. We've got that controller chip. We've got that driver chip. This is how it's connected. So what I'm thinking I'm going to do is this. Now you'll see some people do this. What they'll do is they will connect onto here, right there, and then, or anywhere at this node, or they might do it right here. But the point is they'll kind of connect on like that, like that, like that, and like that, and then they'll connect this thing up to their red, green, blue, and blanking signal. But the problem is the blanking signal blanks the normal video, but it doesn't blank the on-screen display video. So you'll see, so you're mixing your signal with this signal here. There's this impedance here. This is kind of a messy way to do this, and you're kind of mixing these signals together. So a better way to do this is to actually cut these lines. So you actually cut these lines, and literally break open the line there, 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 cut the lines open, and then you have 4 signals coming from here. So we've got those 4 signals. We'll draw the first 4 in this purple. So 1, 2, 3, 4. Then now we bring in our 4 signals. So this one was from the on-screen display. This is from the on-screen display chip, this thing, right? And then we bring in our 4 signals, 1, 2, 3, 4, all right, from our RGB, and then this little blanking signal, which is just a control. So that could just be a switch. But anyway, then the whole point is, then we want to take 1, 2, 3, 4 signals out, right? And now what I'm going to do is I'm just going to kind of represent this. I'm going to go like that, I'm going to go like that, and then I'm going to go like this. And then the whole idea is we just put a switch here. We put a switch, and we can switch these 4 or these 4. Then these 4 signals, then we take and we reconnect right there, right there, right there, and right there. So basically, we switch either electronically or with a mechanical switch, like a big 4-pole switch, all the signals, boom. Then on our RGB side, which is here, we put whatever resistors we need to do the same. We want to get the same voltage, right? And so we're going to look at this IC2001, what it's outputting voltage-wise for red, green, and blue, etc., so that when we take our RGB signal from our game console or whatever, we're going to put a similar kind of network. We can't mess with the 6.8 because that's coming from the chip, right? So we have to put whatever our resistor is here so that we get the same kind of division. So we get either 30% of the signal or 50% of the signal. All right. Then the last piece of the puzzle is this is red, green, blue, and this blanking basically turns on and off this on-screen display thing. But we still need sync. That's a problem. So where do we get the sync from? All right. So red, green, and blue we got, but there's no sync. Okay. So now we go back to our schematic. All right. We'll go back to our schematic and let me bounce out here. And let me go up here. Let me go back up to the top. So where does the sync come from? Remember, I told you it's in the composite signal. So here we are at the block diagram again. Let me zoom into this now. So we come in and there's that video signal. There's that composite video. It's got Luma, it's got Chroma, and it's got sync all in one signal. It's all in one signal. It's all in there, right? We need to get that sync out of there. So that signal comes in here, it comes down here into this driver chip, and this says external in, and then it's got this little switch here, and then there's also TV in, and then there's this video out. This video out signal actually goes here, and check this out, it goes here, and then it comes up here into this buffer and trap. What does that mean? I'll tell you in a second. Then here's Luma in and Chroma in. So check this out, this buffer and trap, this is what they kind of call filters, traps. So what this circuit does here is as this thing comes up here, right, this extracts out the Luma, this chip, this circuit, and then the Chroma is here, and then both are brought into these two pins, okay? The sync is actually in there still. The sync is in here, so this could use the sync. Now, this video out is also going here, right here to the CC pin, and then look here, there's CC sync, so see this? So there's the sync here, so there's some sync stuff going on here, right? So the bottom line is, if we can just inject into this video line, so we could put red, green, and blue and connect it to those red, green, and blue lines. Then we could take our sync signal, right? But we would have to have composite sync from our red, green, and blue. So we'd have to have horizontal and vertical composite sync merged. We could actually just put it into this video signal, and this thing would this circuit would extract it for us, right? But I don't really like that. That's not clean. So what we really need to do is figure out where exactly we can inject horizontal and vertical sync from our RGB output device, which is our game console or our computer, because it's going to have red, green, and blue, and it's going to have either H-sync and V-sync or composite sync on one line, or maybe it's going to have sync on green. If it's got sync on green, that's a whole different story. I want you to talk about it. But let's assume it's got red, green, and blue, and then it's got horizontal sync, vertical sync, or it's got composite sync with horizontal and vertical on the same line. In that case, the question is, how can I get that into this chip here? How can I trick it, right? So then, check it out. We can go into the schematic again, the deep schematic, the detailed schematic, and we zoom in here, and we start to see. So there's Y in, that's Luma in. There's Chroma in. There's the TV video signal in. So if we could just take the composite sync, we could probably put it here, and this thing would probably extract the sync for us. But check this out. And after it does that, it actually generates the sync out. So it actually extracts the sync from the video and then sends that sync out. This chip does all these processes. But look at this. Here's H-sync right there. And then there should be a V-sync someplace here. And you guys can someone's already probably found it. There's H-sync. There's H horizontal out. Anyway, the point is, we could find where on this to inject H-sync and V-sync separately if we had them. We could do that and then switch into here also, or we can just take a composite sync and we can inject it into this kind of video in with our switch also, so it's nice. So there's a lot of different ways, but we got to look at the schematic and we got to figure it out. But we know how to read these schematics now. We know what these things are. We know what these resistors are, and we know what these transistors are doing. There's another NPN transistor. There's a PNP transistor, NPN transistor. Look at this right here. Here, just this little circuit right here. If you've taken the class or you're in the middle of the class, what is this circuit? Well, look at this. We've got some kind of, this is driving this way, whatever, but look what this construct is here. Well, there's an inductor, there's a capacitor, there's a resistor, an inductor, capacitor. These are filters. These are filters. So there's filters here, a filter here. So this is a filter block. That's all that stuff is. Remember, this is, there's an L and there's a C, and it's got a certain response, and you add them in series or parallel, and you get certain responses. There's filter blocks right there. Again, there's a normal diode right there. There's a probably, yeah, this is another Zener diode, 3.9 volts. So anyway, you go through here, and if you have to dig down and understand the schematic, you take your time, you try and figure out what it's doing remotely, and then add your design elements that you need to, and then test it. So that's basically it. So I wanted to show you how you would go about, how do you reverse engineer something? How do you hack something? You got to get the service manual, you got to get the data sheets, you got to get the designs, you got to get the schematics. Then you got to dig down into the data sheets and the chips and understand what the signal levels are if you're going to start injecting signals and connecting things, and then understand what the ramifications are. But then you got to understand the global, what is it you're doing? We're messing around with an NTSC TV, trying to hack it into an RGB TV. You need to know something about NTSC and RGB. You need to know how a CRT works. You need to know that it generates a stream of electrons and accelerates them towards a screen. And then as they hit the screen, they hit phosphors, and the phosphors give off light. It's a quantum level device. You got to understand all that stuff, not every detail, but the general picture of what's going on, so that you can hack this and do whatever. And all of this is just so that someone can play an old school game console on a CRT and get a better picture. All right. So I hope you guys enjoyed this kind of little example of what I do sometimes for either fun or for money. And this is, engineering for you. So hopefully you learn that you can read schematics. You guys know how to do them. If you've been taking the class, we know what all these components, and you know what a lot of this is very analog. You guys know this now. You know what filters do. You know what capacitors do. You know what inductors do. You know what transistors do. You know what all these things do. And these chips basically are, these black boxes at this point. You don't need to know exactly what they do, but you can understand the signals coming in and out because you understand the constituent components because we've studied them. All right. So anyway, I hope you like this bonus video. Have a Merry Christmas if it's something that you celebrate, and I will see you in the next lecture. Bye. Hello, everybody. This is a bonus lecture, and we are going to talk about amplifiers. So this week is Valentine's Day week here in the United States of America. So there's a lot of countries, I guess, that have this holiday. It's basically a holiday for, your girlfriend or your wife. Anyway, so if you are in the United States or a country that celebrates it, do not forget. For me, it's fun because I have a little daughter, so I took her to a daddy-daughter dance, and I'll take her to another one. So that's kind of a fun thing to do if you have little daughters on Valentine's Day. Go with little dances. Anyway, so I've been trying. Normally, I would have put out a bonus video a couple weeks ago, but I've been really trying to think of something useful and interesting. And again, we only have an hour to do it in. So what I was thinking is a lot of people have been asking me about amplifiers, and so I thought it would be maybe a fun project just to build an amplifier in real time, so you can see the thought process and the steps that we go through. All right, so that's what we're going to do. We're going to build an amplifier. Now, we're not going to build anything crazy. In 1 hour, we're going to build a very, 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 very simple amplifier. But I'm going to talk to you about my thought process, some of the things that you're thinking about, so that you could build more complex amplifiers. All right, so let's just dive right into this. So let's say that you build some project and it has maybe an audio output, right? But the audio output does not have any power. So now let's talk about this for a minute, what this means by power. Now, if you're watching a bonus video, you could have skipped the entire course and just watching this bonus video. So obviously, if you take the class, you're going to know a lot of these things that I'm talking about. But when you're talking about amplification, there's three kinds of amplification. We can amplify voltage, we can amplify current, we can amplify both, which would be a power amplifier. So when you're doing a audio amplifier, typically we want to definitely amplify power, and many times we want to also amplify voltage. Now, A lot of times you may not need to amplify voltage. For example, say if you have a 5-volt system or even a 3.3-volt system and you generate an audio output, that audio output is already going to be swinging 5 volts or 3.3 volts. Most of the time that's enough to drive a speaker, no problem. The problem is there's no current to that drive, right? So you've got the voltage but no current, so you need more current. So that's where the power amplification comes in with the audio amplifier. Now, many audio amplifiers also have voltage amplification, so you can take a tiny signal, maybe a millivolt level signal, and amplify it 10, 50, 100 times. So those are some of the things that you're looking for in amplification. You definitely want power amplification, meaning I want to amplify current and potentially also voltage, but I definitely need current because we want to put out watts or fractions of watts or many watts when we're talking about amplifiers, right? Audio amplifiers. So a typical audio amplifier, something in a small handheld device, like say, like this phone, maybe this little speaker puts out, maybe 500 milliwatts, right? 200, 500 milliwatts. I doubt it puts out a watt, all right? And then you'll see these big giant stereo systems, maybe it puts out 500 watts or 1,000 watts, maybe at a concert, crazy big stuff, right? All right. Now, so then we say, okay, hey, we want to build an amplifier, and then you could go look and you could say, what are some amplifiers, little breakout boards, so that you can play with these in experiments. So if you go on Amazon and type in audio amplifier breakout board, we can go through here and you can see there's various small devices here, and you kind of look through them and you can see what's going on here. So for example, we look at some of these that came up in the first search. Some of those are fairly complicated. Like you can see, this is a very nice one. But some of the simpler ones, like this right here, we come in here and we see, okay, so 1.4 watts into 8 ohms. What that means is it can drive 1.4 watts of power into an 8 ohm load or an 8 ohm speaker, right? And then if you look at it, it's just basically one chip. And then this is potentially a regulator. I'm not sure. Let's get another view here. And so very, very simple. And we can see it's based on this particular IC, this TPA 2005 D1, which I know is a Texas Instruments amplifier. So we could go look this IC up and say, let's take a look at this and just basically copy something like that. So we can do that, and we might do that, right? Again, I'm doing this in real time with you right now as we do it. Now, here's another one. This is shockingly expensive, actually. And this is based on this PAM 8302 2.5 watt single channel Class D audio amplifier. So this Class D, if you don't know anything about amplifiers, then you're going to be like, what does that even mean? Even if you know about amplifiers, you may not be familiar with D for digital. And we're going to talk about that also. But for now, we're just shopping. We're just looking around. And so this PAM 8302, I've used these PAM chips before. This is from, I'm trying to remember what company makes these PAM chips. It is, let's see here. Is it Diodes Inc? Yeah, it's Diodes Inc. So the company Diodes Incorporated, they have a whole line of these audio processors or audio amplifiers that start with PAM, which I don't know what the PAM stands for. But anyway, they have some really good ones that are fairly simple. And so this is a good company to get simple amplifiers from. Now, Texas Instruments and Maxim have a whole line, a whole slew of amplifiers, like, I don't know, dozens, maybe even over 100. Diodes Inc. does not have that many, but they have some simpler ones that are easier to get up and running, all right? So we want things that are fairly simple. So here's another possibility. The 8302A is a 2.5 watt Class D. So there's another possible opportunity for something that we might want to use, all right? So let's go back here. So we saw, there's this PAM IC and this TI IC. Let's see what else. This thing right here is more complicated. This, I think, is a audio file playback IC. There's another PAM 8302. Now 8403, and a lot of times when you see these numbers increase, it might mean it's stereo, it might mean it's more power, etc. That's all. And another thing that you can kind of glean from this is what manufacturers make ICs, and then what are people using to make these little kits? Because they went through the same process so like here's another TPA 3116 2 by 50 watts. So now this one's interesting because this is a very high output amplifier. So it's 2 channels by 50 watts class D. That's a big, powerful amplifier, right? So that's no joke right there. So someone has to go through this process. Now, the process of looking for these things is very time consuming when you go to the manufacturer websites, all right? Let's see, another PAM 8302, and there's that 2005 again. All right, so now what I want to show you is, so you could go on Amazon, and you could look this up. You could also go to SparkFun, which is another site, and I'm trying to keep an eye on the time here, because we do not have a lot of it. Audio amp, let's see what comes up here. Audio amplifier, and come on, SparkFun, render the page. So there's one with the 2005 that we just saw. Let's see here. Anything else exciting? And okay, here's one here. Oh, this one's I2S. All right. So now you can either drive these amplifiers with an analog signal, which is kind of what you would be used to, or I2S. And my course is not a digital course, it's a basic electronics course and PCB design, but I talk about I2S a little bit. I2S is a serial protocol similar to I2C, and these things stand for inter IC communications I2C, and I2S is inter IC sound, I think, or it's a sound version of I2C basically. So you can digitally send information to an IC and amplify it so that you aren't working with analog signals that can degrade, you're working with digital representations. So this is nice if you want to do an I2S amplifier and if you have a microcontroller or a computer or something that has an I2S output, but we're not going to do that. Nevertheless, Max, remember I said Maxim Semiconductor has a lot of audio amps, and this is one of them right here, this 98357. So anyway, let's go back, and then of course Adafruit is another great website that has a lot of cool stuff. And if we look under audio amp here, and then there's quite a few of them actually. And so again, this is a great way. So there's a TPA 2016, and this one's got I2C control. So that means that you need an I2C bus to control it and set the registers in it. So that's a little bit more complicated than we want to deal with. So this PAM 8302, so this PAM series is looking good. And then here's that I2S, we don't want to mess with that. And then there's 14 pages that probably degrades it to other things that are not the search terms. Here's one. This one is 2 by 3.7, and this is this Max 98306, and then here's this Max 9744. Let's take a look at this one. Let's take a look at this one right here. All right, so 9744, for example, we can look here at it. So this is a fairly complicated chip. It has a good amount of support hardware around it, a lot of stuff. And we may not want to get that complicated to do whatever we're going to do. But again, we're just kind of looking and getting an idea. Now, so we want to make an audio amplifier. So you say, hey, Andre, why not just use an LM386, right? You may have heard of this. We could do this, but I mean, these LM386s are very, very, very old. Now, even though this says 2004, this thing predates this. So this is kind of a very crude audio amplifier IC. They're a buck. They're real simple to use. They have a wide supply voltage range. So, and here's what the circuit looks like inside of an LM386. So you could just make something out of this. It's got an input, a couple other pins here, the output, ground, power supply, and then it's also got, you can set the gain in this a little bit. And if we go down here and look down here, you can see what it looks like: minus, plus, ground, gain, bypass, these different inputs. And we can look at some of the circuits of this. There's kind of this functional diagram. Here's an example circuit. So you can see with the LM386, for example, you can make a good audio amplifier, and the input comes here, and then this is kind of a volume control, using this potentiometer as a volume control. The non-inverting input is grounded, and then some of these other pins do other things like set gain and whatnot. The one big problem with using an LM386 is it needs an AC coupled output, and you need a very large output capacitor, usually 100 to 200, 300 microfarads to block DC. so that only the AC signal gets through here. And you want like very low frequencies, like 10 hertz and up. So you have to put a big capacitor here. And a lot of people don't want to put a big capacitor. That's a big part, especially if you're making a surface mount board. Nevertheless, the LM386 is surely not bad, and you could always make an amplifier out of this. This is specifically designed for amplifiers, the LM386, and amplification circuits. And here's another example with gain 200. And again, this is voltage gain 200. So the voltage gain is 200. Then the final output, right, will be whatever that voltage is through whatever this impedance is. And this impedance is a speaker that will draw as much current as it needs. So the final output will be the voltage times the current, obviously, right? Okay. And just some examples setting gain with these gain settings. I believe pin 1 and pin 8 help set gain. Anyway, the data sheet on this is not short, and I think it's about, let's see, does this, yeah, 29 pages, yeah, 29, 30 pages. So you could use an LM386. Now, another thing that you could do if you want to make an audio amplifier is you could use an op amp, right? No one said you can't just use an op amp. And again, I'm showing you, parts that are very common and kind of older because they're ubiquitous. So the LM741 is kind of a very, very basic operational amplifier. I would never ever use this any product or project I ever made professionally because it's just too slow, too old, too everything. Everything now is 1,000 times better than this on every single factor: power, noise, amplification, linearity. I could go on and on, but it's simple. And this is kind of, if you start learning about electronics and you want an operational amplifier, hey, people say use an LM741. Just like for transistors, I'll tell you use a 3904, 3906, 2222A, etc. in the course. Same thing here. And we don't talk about operational amplifiers in the course other than a little couple anecdotal things where I talk about them just for a few minutes. But operational amplifiers are basically black boxes that are idealized amplifiers. And you can set them up in different ways to kind of create all kinds of different amplification and functional analog operations. Amplification is one of them. This configuration right here is a non-inverting amplifier configuration with it. There's countless configurations that have different properties, and they have really cool properties. There are whole books, thousands, hundreds of books on operational amplifiers. And if you just Google for operational amplifier circuits, there's tons of them. You can find PDFs from Texas Instruments and other companies that make really good white papers that are hundreds of pages long describing how to do circuits with op amps. So we could just use an op amp. There's no reason we couldn't just do that. All right. But again, when we do things ourselves, then we have to understand what we're doing. So we have to understand things like filtering and power amplification and so forth. So in this case, we just kind of want to use a chip, right? All right, so you just want to use a chip. Okay, now let's go a little bit farther. So now we want to use a chip, so we go to a place like DigiKey, and I've typed in audio amplifiers here, and I think, yeah, 5900. All right, so then we can go through here, and we can say, okay, where to even begin, right? Okay, there's a lot of these different parameters here. Okay, the first thing is, before we do anything, we need to understand what we're looking for. All right, so let's say, hey, I want audio amplifiers in stock. I want it RoHS, bulk or cut tape. Okay, I don't care about the series. I want it to be active. This type thing, we don't understand this yet. I'm going to talk to you about this in a minute. All right, so let's go there, and now let's apply filters. All right, give that a second. Okay, then we have max power output. We're not going to play with that yet. We're not going to play with voltage supply and all that yet. But I do want it to be a surface mount chip. Okay, so surface mount, surprisingly, there's not that many through hole. There's almost no through hole. Okay, now it's saying the output type. All right, and we can say one channel with 2-channel stereo. We can say 2-channel stereo, all these different variations. So we kind of need to know what matters here to us. All right. Before we go do that, let's go talk about the class of amplifier. All right, let's go talk about the class of amplifier. So I think I have something open here. Yeah. All right. So when you're talking about amplifier class, there are many classes now. And here's a little chart. You can see there's A, there's AB, there's B, there's C, and then there's D, E, F, G, H, I, T. There's all these other classes which have just kind of happened recently in the digital world to describe those kind of classes. But what I'm going to talk about is these simple amplifier classes. So an A amplifier amplifies the entire signal. All right, A amplifier amplifies the entire signal. It's very linear, and I think there's a circuit of it here. Yeah. So again, if you haven't taken the course, you're not going to understand this too much, but in this case, we bring the signal in here, we capacitively couple it, and then this transistor is biased into the operating, it's operating, right? So it's biased, it's running. And then we take a small signal, and then we get out a larger signal here. So the transistor is always on. So here's the input, and here's the output. So we get an amplified version of the signal. The transistor is always on. So even when there's no signal in here on the input, the transistor is still running. It's running hot. It's burning energy, right? This gives you a very linear, great amplifier, but it burns a lot of energy. So if you want an amplifier that gives you the best audio, right, then a lot of people just stick with a Class A and they'll just burn energy. Now, so then we said, hey, let's come up with another one, and let's see if we can, reduce this power. So then there's these other two classes here, this A, B, and B class. So now if we come down here, take a look here. So we have this Class B amplifier. So then the Class B amplifier, how it works is there are two transistors. So one transistor turns on when you have a positive going signal. The other transistor turns on when you have a negative going signal. All right. So what's happening here is when you have the input signal come in, you get your output signal. And this isn't showing the entire signal. You get your output signal, which is turning on each one of these transistors depending on which wave or which half wave of the input, right? The problem with this is that as these things turn on, all right, they need to, there's a portion where they turn on, so you get kind of this discontinuity at the middle point. So in other words, as the signal goes up and goes down, there's a little amount of voltage that gets lost turning on each one of these transistors until you start getting amplification, all right? So you get this nonlinearity, all right? So then we kind of mix these two things, and then there's this AB. So what AB does is it overlaps the on portion, all right? So wastes a little bit of energy. So if you go to AB here, hopefully there's an AB, yeah. So in AB, what we do is we bias these transistors in such a way that we turn them on so that as these transistors are conducting and they're making this crossover point, there's a crossover, there's an overlap, so that we get the signal out, but we don't get those discontinuities. So we get a better linearity in the output signal, all right? And what that does is it burns a little bit of energy, but for it, we gain a better signal. So the bottom line is that if we're looking for transistor amplifiers, we are interested in an A or an AB. We're not interested in B. We're not interested in C. And then over here are these digital amplifiers. Let's take a look at those. So now we can convert the signals. The chips can convert the signals into a pure digital signal. If they do that, they start off, the first one's a D. And if I come down here, where are we? Yeah. So here's where it starts to talk about this. So a Class D amplifier is basically a nonlinear switching amplifier, or a PWM amplifier. All right. And then from that, there's all kinds of variants of it, F, G, I, all these different things, which are more or less fairly arbitrary. They just kind of started coming up with these as companies invented these things. But the bottom line is these are all digital versions of analog amplifiers. So you can read through here, like a D amplifier is basically this PWM, pulse width modulation amplifier. So it's completely in a digital domain, all right? And they can, theoretically reach 100% efficiently. And then Class F, both efficiency and output using harmonic resonant. There's all these kind of crazy things that they try to get better performance, lower power, right? So what we're looking for is either A, AB, or if it's a digital amplifier, we'll go for a D. Now that digital doesn't mean that it necessarily will take a digital signal. It just means that internally it converts the signal into a digital signal, amplifies it, and then converts it back into an analog signal using this technique for the output, and that's why it's called a Class D or F or G or whatever amplifier. All right, so that's the type of amplifier. Okay, so given that, let's go back to our search. So we like A, we like B, all right? And then In fact, we like all these. All these will do, all right? Notice there's no B and there's no C, right? No one wants those. Okay, so let's go ahead. Oops, clear that. All right, and then we've already applied our filters. Let's do that again, just for kicks. Okay, now, so now we got to talk about, do we want to amplify headphones, or do we want to amplify just speakers kind of thing, all right? And do we want it single, mono, or stereo, all right? So let's go ahead and let's make this stereo. All right, so we want 2-channel stereo. And this says 1 mono or 2-channel stereo, 1 mono with mono headphones and stereo headphones, all this different kind of thing. I just want to stick to 2-channel stereo, all right? And in fact, and I don't even want headphones. Let's not mess with that. Let's just go 2-channel stereo. Done. Apply filters. Okay. All right, here we go. Now, let's go and sort by price. You know, I'm always concerned about price. All right. Now, let's see what we came through here. Oh, look at that. Check that out. There's that PAM 8403 came up, right? There's a PAM 8406. Here's an interesting chip. So this is AB 2-channel, 2.2 to 5 volts, 68 cents. That's pretty cheap. And does it say what it doesn't say what the wattage is. Let's go take a look at this one right here, this NC on semiconductor. And then of course, like I said, the big companies will have tons of these kinds of chips, but you'll see outliers from other companies that have a few ICs. Piece of advice, if you're building and designing a product where you're building millions of something, be careful. If you find some company that now On Semiconductor is a very large company, but maybe their core strength isn't audio amplifiers. Maybe they got just 1 or 2, right? But they've got 50,000 of some other kind of chip that they design. I feel good about buying one of those other chips, right? But if they've only got a couple audio amplifiers, it's not real important to them long term, their roadmap long term. So I really don't want to buy those chips, because if I go build a product with 100, 1,000, 10,000, a million, 10 million, 100 million units, right? Ideally, hopefully, I don't want to be stuck with a company that's like, we're not into this anymore. We're not going to build this chip anymore. So be careful. Pick chips that you can find a lot of, and it's a core strength of the particular company. Okay. All right. So this, whatever this is here, let's go take a look at this data sheet. See what we're doing here. And this is what I do. This is the process, right? And I want you to see this. So no cap, right? So this has something to do with no capacitors, I would imagine. I've probably seen this chip before, but I've never used this. Pop free, it just means it doesn't pop, make popping sounds when there's transitions in the audio. When the audio turns on, turns off, a lot of audio amplifiers will pop and click. It's very annoying. All right, so it says from 20 hertz to 20 kilohertz is the flat frequency response, meaning from 20 to 20 kilohertz it will amplify the same way and doesn't have a frequency dependent amplification, which of course you don't want in an amplifier. It works from 2.2 to 5 volts. Okay, so that looks good. This PSSRR, this is the power supply rejection ratio, 90 decibels, which means that as the power supply is all over the place, the audio will not hear it. And adjustable gain from 1 volt to 10 volt to volt. So all this means is basically 1 to 10 for the voltage gain. All right, and there it is. Looks pretty simple. So this is not bad. Let's see if there's a schematic. I like looking at schematics because that kind of shows you what they think you're supposed to do with the chip. And some equations here. Resistor divider, probably for gain or something. This is for shutdown volt. Okay, that's something else. All right, and yeah, so as you can see, so this basically is a very simplistic amplifier. So here's a differential mode version of it, and here's a inverting configuration using it. So it's basically like an op amp. It's a very specific kind of op amp. So that's what this thing is. It's like an op amp. You can see it even has a symbol of an op amp. So this is it's like the LM386 that we're looking at, or the 741, the LM741. It's just kind of an op amp, all right? So that's a possibility. We could use that, but I want something a little bit more like a black box, an audio amplifier. So let's move on, all right? Let's see here. We got this PAM 8403. Now we saw that there was that 8402, I believe was the other one. So this might be interesting. I don't want to mess with anything that's a BGA, ball grid array. I can solder it, but a lot of people won't be able to. So we're going to do this surface mount. So this 8403, let's take a look at this one. All right, this is 3 watt. This doesn't look too bad. Let's see what we're doing here. And this is, you know, and if you watch the videos and you know how I do this, this is a painstaking process of figuring out what to put into things. We're sitting here looking at some basic chips. If we were doing this professionally, I might have to review 100, 200, 300 ICs, meaning I got to look at 200, 300 data sheets. Then I might pick 10 of them that I like. Then I might have to get 10 samples. Then I might have to build 10 boards or get 10 dev kits and listen to it and look at its performance. All of that could take hundreds of hours just for one chip that I'm going to put into a final design. And a final design might have 10, 50, 100 chips, right? So this is a long process, but this is how it's properly done. So you're just not picking random things that other people pick. Like we can go on Amazon and look what someone else did, but here's the process where we're doing it ourselves, right? Okay, so if we look at the design here, so now you can see this is a little bit more of a black box. So one thing is we've got a couple power supplies here. We got to look here because it might require 2 different power supplies. That would be bad, which is more complicated for our little board. But here, this input left, input right. Zoom in a little bit. Input left, input right. These are capacitively coupled through small capacitors, 0.47. I can deal with that. This has got a, now here's interesting. Look up here. So here on this PVDD, 470 microfarad is the recommended bypass capacitor. Why is it so big? Well, I'll tell you why. Audio amplifiers are going to pull an enormous amount of current, right? Now, we saw the other thing where we had the capacitors in the output to the speaker. Those are for filtering on the LM386. We don't like that. But we don't mind if there's big bypass capacitors here, and they're just required. Because when you pull so much current, you need to get it from someplace. If you run back to the power supply over the impedance of the lines to the power supply, you're going to get a voltage drop. So you put a big capacitor at the chip, 100 microfarad, 200 microfarad, 400 microfarad, 1000 microfarad, so that you can get that current, that charge that you need. So this is very common. All right. Anyway, you've got a shutdown pin, a mute pin, a bunch of grounds, and then we've basically got these 2 outputs. So this looks to me like a very simple IC, and input left, input right, stereo input. These are reference to ground. All right. I don't see a gain control. Don't see a gain control. So if we back out here and we see here internal reference, connect a bypass capacitor, mute. These are just digital lines. Mute, active low, and then shutdown just shuts the whole thing down for power, active low. All right. And let's see if there's anything else interesting here. Bunch of charts again. I would read this very carefully. Kind of here's a block diagram of their whatchamacallit. Operating voltage is 5.5 on the PAM 84 is part of. Should be noticed that the voltage of 4 new dry. Okay, so this is battery. Works with LC. Should be connected to speaker before it's powered on. All right, and so this is talking about, here's like the whatever their output is, and they've got a filtering system on it also just to filter some of the stuff. We don't care too much about that. Let's see here. Let's see, maximum gain. As shown in the block diagram, the 8403 has 2 internal amplifier stages. The first stage gain is externally configurable, while the second stage is internally fixed. The closed loop gain of the first stage is set by selecting the ratio of RF to RI, while the second stage gain is fixed at 2 times. Okay, so we can't play with this 2 times, but we can play with this RF to RI. But my question is, where is this RF and I, which usually is feedback and input? So let's go back to the design here, the little schematic that they did. So here, let me zoom this a little bit for you. So here is this RI that they're talking about. So this is R input. So then this RF, we kind of need to figure out where that RF is, right? Where's that RF? So that's where the gain is getting set. So I can sit here, let's search for RF, and picking up just words here. All right, selecting the ratio of RF to RI. This is going to show you the average gain, but we still don't know where this RF is in the actual design. So sets a maximum RF of 142, a minimum of 18. Okay, so that tells us the range that we can select here. That's great, but we still don't know where we put this RF. How is it getting this? This is showing some filtering that you might want to add if you're having noise problems. So on this one right here, I like this, but I'm not clear where the feedback resistor is on each of these channels. All right, And here's the input, and this is actually, so see this right here? These are feedback resistors, this one and this one. There's two stages, this one and this one. See this attenuation decoder? And this is connected here, this is connected here, mute, but I don't see how to set it. So we'd have to figure that out, right? And this is why this stuff takes time, right? We're already 30 minutes in, so we got to move on. Okay, so that's a possibility, this PAM IC. Okay. All right, so let's skip through the PAM things. We've kind of looked at the PAMI stuff. And so I've looked at this 8406 before. What were we just looking at? We were looking at an 8403. 8406. Now this is class D and AB. This is 2-channel 5 watt times 2. Let's take a look at this one. So I've looked at this at some point, and let's see why I liked it. Is this anything? Okay, so the PAM 8406 offers low THD. That stands for total harmonic distortion, and that is a measure of noise between harmonics during the amplification. And all these different chips, depending on what you're doing, have a whole language of their own that you have to learn what all these acronyms mean and so forth. So you can't know everything. So you got to read through this. So 5 watts, 2 ohm load, 3 watts at a 4 ohm load. Okay, so this looks fine. Now let's go over here. So we see our block diagram. We're always interested in the block diagram. Now if you look at this, high and low. So this is interesting. So this allows us on this mode switch to put it in high, which is class D digital, or low, which is class AB. It's stereo output. Notice on this one they use much smaller bypass capacitors. And then again, there's this RN, and we're not sure about this whole gain thing. So let's just search for gain. And RL. And let's see. So works in DX should be connected. One should not make, so this is very similar to the other one, and we're not quite sure. The PAM sets maximum RF equals what minimum RI equals this. So the closed loop gain is 24. I'm not sure if it's set itself or if we set this RF. It doesn't look like we do. So again, I'm already confused by a little bit of this chip, and maybe I don't want to figure this out, right? So let's keep going. Okay, ISSI is a good company, but they don't make a whole lot of amplifiers. All right, we can look at this 2.6, and again, you just got to go through this, and this is a huge pain, right? And then down here now we're starting to get a little bit more expensive. Now this one new, so 2-channel stereo, 2.4 to 5, class AB. Let's take a look at this Max 4062 chip. Okay. All right, so this is interesting. So this one right here, this looks like it's a microphone amplifier. Differential microphone, yeah, it's a microphone preamplifier. Okay, so that's cool, fine, whatever. The search came up with something that we weren't interested in. All right, and then here's some of these TPA chips. Now, notice it's got, a good amount of pins here. Now, if you're afraid of a lot of pins on a surface mount, we can avoid that. So maybe let's go take a look at this DRV. This chip I'm familiar with also. Let's take a look at, where did it go? This this one doesn't look too bad. This LM4666 Class D 2-channel 1.2 watt. Not a whole lot of wattage there though. Let's go take a look at that. Okay. Okay, the LM4666 is a fully integrated single supply high efficiency switching audio amplifier. It features an innovative modulator that eliminates the LC output filter. Typical switching amplifiers, remember we talked about that, you might have to filter the output if it's a switching amplifier. Okay, fine. And again, you'd really want to read through this. Okay, so what do we got here? So here's the right input and left input. So this is showing differential inputs, but we can ground one of these if we wish. And we've got right, we've got left, and it's got kind of a little gain control here. So this doesn't look too bad, all right? So this doesn't look too bad. All right, so let's take a little bit look here more and scroll down here a little bit if the browser will cooperate with us. Okay, and what again, I'm looking for just kind of a schematic here. So here's the single-ended input version that we're going to kind of use, right? And so it's very, 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 very simple. All right, so I'm liking this, and this looks pretty good. And notice it's capacitorless outputs on the speaker output, so that's cool. All right, and very simple network here. Just basically, we've got the power comes in, it's bypassed, and then it's split on these two supplies and then bypassed again. We can do that and improve that a little bit. And here's if you want to add a little bit of more flair to it and put these filters. So these are filters here, and then this is also for making measurements. And then this stuff right here is jumpers, so you can kind of short these inputs, and then a switch so you can select gain select and so forth. We're going to look at that gain select in a minute and see how that works. And then this is basically showing the dev kit schematic, all right, and PCB layout, and that's about it. Okay, so you know what? That's not bad. It's only 1.2 watts, which is a little bit thin. I'd like it to be a little bit higher, but LM4666 is not bad. LM466, it's a $1.50. So, and it's fairly simple. So I kind of like that. And what do we have over here? Now here's another one, and this is LM1877 and LM325. Let's take a look. Let's take a look at this one. This one's cool, but it's got too many pins. Let's look at this one. This LM1877. Let's see what this is talking about, if we like this. All right, this is looking a little bit old school, 1995. I can tell it's a little bit old. 2 watts per channel. All right, and okay, they show the inside of it. Great, and let's look at a schematic. So this is fairly old. And again, this is, yeah, so it's basically, these are op amps in here, right? These are op amps in here. And it's kind of showing you different configurations. Nah, not interested. Not interested. Let's back off that. All right, we got about 20 minutes more. So we want to find a chip so we can do a design. All right, and let's see, this LM4880, direct path, this DRV, let's take a look at this one, this 4880. All right, it's got very few pins, so it's not going to have a lot of features, I can tell you that. And this is going to probably just be 250 milliwatt. Yeah. So yeah, this is not bad. This is very simplistic. It's capacitively coupled to both speakers, and then capacitively coupled here. Very simple, but no bias control, no gain control or whatever. Okay, so I think what we're going to do, because time is always against us here, is we're going to take a look at this LM4666. Now, obviously, we didn't do an exhaustive search here, and we could just look at those other chips that the other companies, SparkFun, Adafruit, Amazon, we see are using, but we're just trying to do this to show the process. Okay, so LM4666. Now, what we hope is that the tool, so let's go here. So we're going to go to Circuit Maker, and again, if you haven't taken the course or Section 8 specifically, you don't know how to use this yet, but if you don't, just bear with me. So we're gonna, I've already created a new project called CCE, Crash Course Electronics, Beatbox Amp version 1001. Whatever version we get done with, we'll just have 002 or something like that. So if you kind of search for Beatbox in my account, you should be able to find this and clone it. In any event, right now it has no documents, so let's go ahead and let's add a schematic. We're only going to have time to do the schematic today, but I think that'll be okay. So I'm going to call it CCE and Beatbox Amp. I like to name everything the exact same name. Oops, V1_001. And is that right, everybody? I think so. Okay, so there's our schematic. And now let's go ahead and let's see if we can find this chip. So I'm going to go up here and we're going to search for this IC. Let's take some of this off so we have less. Oh, we got lucky. Look at that. All right, so there it is right there. First hit. That's good. Now, which version is this? This is the WSON, and looks like it's always the same. And these different versions of it could mean there are different ways that the IC comes. So we're going to stick to this one right here, which is actually the one we're looking at. So let's go place this. All right, so I can see right now I might need a little bit more room here. So I'm going to right click and I'm going to say sheet actions. Where is it? All right, and let's go up here and we'll go to project, document options. All right, and I can never remember which way these go, so let me try A1, and that's massive. Oops. And so let's try A2. That kind of, yeah, that's more what I want. I like a little bit of space, you know what I mean, when I'm working. Okay, so we got that. So here we go. So we got this. Now let's go back here. Let's go back to our LM4666. Now typically when I do design, I will have this document up on another screen. So I have another screen over here, all right? So you can see it. I'm going to kind of keep it here, and we'll just kind of toggle back and forth as we go here, all right? Okay, so let's look down here. So here's what our basic design looks like. You know, fairly simple. Let's go to our single-ended design reference. And where did it go? Right about here. Okay. All right, so it's making a recommendation of these 0.39 microfarad capacitors. We've got this input, we got this input, we got this right here, and then we got our outputs, and we got this little network right here. Okay, so the first thing that I'm going to do is I'm going to go steal some parts. So here's a power supply project that I did for a previous video or whatever. So what I'm going to do is I'm just going to go steal some parts here. I'm just going to grab these parts right here. And this is the cool thing. This is one of my manufacturing people about an LCD. One of the cool things about doing electrical design, just like software, you can do things kind of in an object-oriented way, and you can reuse things. So let's see here. Let's go back here. And there we go. Okay, and I'm going to paste this here. Okay, now we're going to build this all with size 805 components. So let's see, these are 805s. You can see 805 surface mount component. Now, I talk about this at length. When you're doing design, you don't have to pick the exact part that you're going to use for passives. You can pick a part that has the right size, and then as long as it's an 805 or a 603 or 402 or whatever the size may be, you can later, when you generate your bill of materials, pick the exact manufacturer, the exact part, because I don't want to sit and have exact capacitors, exact resistors. I just want generic stuff. And so in this case, all I'm going to do is I'm going to say what I want this thing to be. So I'm just going to come here and I'm going to say what I want this to be. And I want this to be 0.39 microfarad, done. Okay, so that's one of these capacitors right here. Now we go back here. All right, so we basically got VN plus and VN plus are both going to go to ground through capacitor, okay? Simple enough. So here we go. So here's one right here, so VN plus right there. I'm going to put that there, and then W for wire mode, and then I'm going to copy this. And notice the reference designator right now are both C4. I don't care, I'm going to fix that later. And go to VN plus like that. Let's get our grounds here. So here's our ground, and I kind of like putting things on the same level so it's kind of symmetrical. So we're going to put our ground here. We're going to put our ground here. All right, so that looks good so far. Now we've got these V sub DD lines, and if we look, the way that they've got this is we've got a capacitor real close to it, and then we got kind of the input coming in here with a 1 microfarad. All right, so I'm going to kind of enhance that a little bit. That's not enough for me. So what we're going to do is we're going to go back over to my little power supply design here, and I'm going to steal this ferrite bead. I'm going to steal this ferrite bead first. All right, and then I'm going to come back here. So right now as I'm sitting here, I can hear my dog barking. She just is constantly hungry. I don't care how much she eats. She's just, give me more food, give me more food. It's supremely annoying. You can't hear it, but I can. All right, and so we're going to go here. And then now what I'm going to do is we're going to be careful with this. I'm going to scoot this over a little bit like this. Now, so electrically there's one thing, and then when we do the layout, which we're not going to have time to do the layout, right? That's something you can do yourself. We're just designing a circuit. When you do the layout, you got to keep notes to yourself and say, put these capacitors close and all that kind of thing, all right? So what I'm going to do here is I'm going to do this. I'm going to actually draw these like this. So I'm going to put this up here, and then I'm going to put this up here like this, okay? Now what I'm going to do is I'm going to go and get my capacitor here, and I'm going to put a 0.1 microfarad All right. Now, I've said this before, when companies show these designs, use the bare minimum of everything to make things work, right? So we're not going to use the bare minimum of everything. We're going to kind of, crank things up a little bit. So what I'm going to do is on each of these channels, I'm going to use larger capacitors, so I just get, better bypassing and better noise reduction. All right, so that's good. So I'm going to take these two, copy them, and I'm going to put them over here because it's this symmetrical design. Again, if you look here, where is it? Kind of, you got capacitor, and the whole thing's tied together, and a capacitor on the main input. Okay, this is going to be our main input here, so we're going to get there in a minute. Okay, all right, and then we are going to go here, here to here. Oops. And remember, it's a W puts you in a wire mode here. So I just press W and I can press escape, that takes me out of it. Now we need to tie these two things together. All right, so to emphasize, yeah, I'm gonna do this. I think that kind of emphasizes. All right, and then what I'm gonna do is the power, we're gonna bring the power in. Come here, little ferrite bead. All right, so we're gonna bring the power in right here. All right, and the first thing we're going to do is we're going to filter it through this ferrite bead. Now we need a power input here. All right, so we're going to steal one of these little power icons here, and it's just right here. If you just go here, we could say power port here, and then I could select one of these, but I've already got it, so let's just use it. All right, and then now this is going to be the power from the output. From the input to this board. I don't really know what this is going to be called. So it's supposed to be about 5 volts. So we're just going to call this V sub CC. Okay, we're just going to call it V sub CC, and you're going to put that input in. All right. Okay. Now I want to put some bypass capacitors here. All right on this input. All right, and let's make this nice and pretty. I'm going to do this. I'm going to do this. Okay, and let's tighten that up. Oop. Let's zoom back in. Okay. All right, and then now what I'm going to do here is I'm going to put this up a little bit, 47 microfarad. We're just going to put that to 47 microfarad. All right, so this ferrite bead is a high frequency filter basically, and this can handle up to an amp. So this is a nice little ferrite bead. All right, so we've got our power coming in, we've got it filtered, then we've got it kind of bypassed and decoupled here. Then we go down and we split the supplies. We go into V sub DD both ways, and then now I'm going to know when I put this thing together, these two capacitors go next to this pin, these two capacitors go next to this pin. Keep that in my head. All right, now we're looking good here. So let's go ahead and let's save that. And let me save project. Good. Okay. Okay, so now what else do we have to do here? Let's see here. What else do we have to do? Okay, we got our speaker. Now, what are we going to do for our speaker? What are we going to do for our speaker? So there's no capacitors, there's no nothing, which is really good. We just need to literally connect this to a speaker. How are we going to do that? Well, we could just put some pins on the board. So we could do that, but we could put a terminal block. Okay. Okay, so we can use terminal blocks, which we can kind of connect to. And so again, you could search here to see what's kind of in the library that you can gain access to. Now I've already kind of done this. Luckily, that's why I've kind of got this design here. And for this one, what I'm going to do is I've already selected these terminal blocks here, which look really cool. Let me show you what they look like. There they are right there. I kind of like those. So we're going to have these terminal blocks here. Then also what we're going to do is in parallel, we're going to put these little headers. So you could plug in with a header or you can go with a terminal block, right? So we're going to kind of do that. All right, so what I'm going to do is I'm going to take this part right here, copy it, and I'm going to put it into our design here. Okay, and again, we will mess with all of the labels for everything shortly. And now we need a 2-pin header, which I just showed you is also in here. So I'm just going to steal that. Oops, we're going to steal that, and right here is just a little 2-pin header. I'm going to steal that. All right, there's a 2-pin header. Okay, all right, so now we're getting someplace. So I'm constantly control saving. Okay, so we look here, what else do we need? We kind of made a little bit better power supply. So we got our input, we got our outputs. We're going to deal with the input in a minute. We've got our outputs, which are going to go to our terminal block. or to our header that we just put in there, and just straight to it, nothing else. Okay, cool. All right, and it's just the right out, left out, left out. That's it. Very simple. Okay, so we're going to go here, and we'll go like this, and we'll go like this, and we will then wire this thing straight in. Boom, and we will wire this one. Let's go down a little bit, like this. Give a little bit of room here, like this, and so. All right, and then this thing right here, this is just a label here. All right, and we're just going to say, we'll just say 2-pin header. All right, and what we're going to do is each one of these is going to just connect directly to this also. All right, and let's keep the pins the same. So this is right 2, left 2, and right 2, and left 1, right 1. So let's put the 1 pins on the 1 just to be consistent. And that's another thing, when you're doing anything with stereo equipment or audio stuff, you've got right and left channels, right? So what that means is if you hook something up in one way and you flip it, audio will be out of phase, right? The speaker will be pushing while the other one's pulling. So be careful, pluses and pluses, minuses and minuses. Labels are important is what I'm saying, all right? So my electronics teacher back in high school, his name was Kenneth Barron, and he had a story one time about some very expensive equipment that they installed for a high school something, some kind of show that was going to be in the gymnasium that week, and they had it all set up and the audio just sounded horrible. They couldn't understand what is going on. This is this high-end equipment. And then the students said, wait a minute, maybe we should flip the speakers plus to minus, minus to plus, and they did, and then they put them both in phase, so both speakers are pushing and pulling at the same time, but it was because they had their labels wrong. So always kind of be very consistent with things. Okay, all right, so that looks good. Okay, and then, so now I don't need to say what this is. I'm going to call this audio out. And this is what, left? Audio out left, right? Is that one correct? Good. And this one's audio out left. Oops. And again, you know, it may look easy talking and doing this at the same time, but believe me, I'm not. There's nothing I'm editing out here really. It's just all in real time, so I'm just kind of doing this as I go. Let's see, this onshore technology. We do need these part numbers on this one. So this one is important to keep this exact part number, this onshore technology. So there it is there. So I can lose it right here if I want to. So what I'm going to do is, you know what, I'm just going to leave that right there. A lot of times I won't leave the part numbers. This is just a generic 2-pin. Looks like this. Well, doesn't exactly look like, that's what it looks like going through the board, and then these are just going to be the holes in the board, the footprint, which you can put a 2-pin header in. Okay, so that all looks good. Okay, so we're getting there. That looks good. And then we've got this gain select and shutdown. All right, so shutdown is active low, right? So shutdown is active low. And then gain select is up to V sub DD. So we are gonna, for shutdown, we are gonna just make this kind of a pin header, and maybe we can make it an input and we'll just kind of pull it high. So for shutdown, let's start off, let's just pull this high. All right, so that it's not, oops, so it's not shut down. So let's get a couple resistors here. Let me find a resistor. And you know what? As a matter of fact, let's take this whole piece because I want some kind of power indicator. All right, so right by this power indicator, and so this is a V sub C in. You know what? I like that name better. All right, we're going to call it that. 470, LED 1, blue LED, that's cool. Now I want this resistor. And now what I'm going to do is up here, so this is a shutdown pin. So on the shutdown pin, I am going to connect it just like this. And we're going to go to V sub CC, and we're going to pull this thing up. And we can, you know, there's a lot of different ways that people like to design things. Let's put this here. I kind of don't like to put things in between things. I'd rather pull it out, so we can, let's just pull this whole little pin out like that. We can do that. Or we could put it up right here. That's another option. We can do that. So let's do this. And again, you know, I don't need to do all this, but I'd like you to see what I'm thinking. See if we got enough room here. Yeah, that's okay. And let's move this over here a little bit. Great, no thanks. Doesn't work. There we go. All right. And then we're going to move this back here. And what I'm going to do is, so I'm pressing spacebar, which kind of does all these rotations. And it's not going to be, it's not being cooperative. That's exactly what I didn't want it to do. All right. So what I'm going to do is I'm going to break this. Now I'm going to take this resistor and I'm going to rotate it. There we go. Okay, now I'm going to put this gain select here, like this. Now I'm going to put V sub CC here. Okay, now this pin right here, this is going to be our control. All right, so we're gonna bust that out at some point. But now we've got this thing doing what we want. Okay, so that looks good. That was on the shutdown control. We're going to do the gain select momentarily once we read how to use the thing. Okay, we need these input capacitors, so let's go do this. So I'm going to copy that and rotate that, and where are our inputs? Here's our input minus. So there's our input minus, and where's our other input minus? Right there. Okay, so we're going to do that, and they're saying use the same value. All right, fine. Okay, so this needs to be brought up a little bit. So let's go here. Let's bring this up just a hair. Good. Okay, and then we're going to bring this up here. And again, there's a lot of different ways to do a layout. And as you do this, you can kind of clean it up, do things differently, whatever suits you. Okay, now we need our input. So let's go back here. So basically, it's input to ground, input to ground. So we're going to do this exact same thing. So I'm going to take one of these guys right here. We're going to do, oops, we are going to flip it around, all right, and we're going to do the exact same thing. So on pin 1, that's going to be the input, all right, and pin 2 is going to be the ground. We're going to get a ground here, so that's going to connect to ground for us, all right, and you can do this also. There's nothing wrong with doing this, putting a ground like that. You can do that, right? There's nothing wrong with that. You can do that. All right, so we're going to do this, and we're also on the inputs, we're also going to put these headers, so we kind of have the ability to header in. So you just have to give ourselves enough room. All right, now on this right here, there's no plus and minus here, so we can't make these the same, but we're going to make the input consistent. So whatever we do, so pin 1 is going to go here. All right, and then pin 2 is going to be the ground on both of these. All right, so pin 1 is the input, pin 2 is going to be the ground. So we can tie these together like this, straight down to ground, and we're going to go like that. Okay, there we go. So we have both inputs. You can use this one or this one, and then it's going to go to our input. Okay, so that looks good. So let's just go copy this block. All right, I'm going to copy that block. We'll put it right there, and then we're going to go here. We're going to go here, and then we're going to pop this up and pop this up and go like that. So that looks good. Now this is not audio out left anymore. This is audio in. Audio in, and I think, is it right? This, yeah, this one's right. Audio in right, and this is audio in left. Okay, let's move this out of the way. Put it right there. Oops. Put it right there. And again, you can sit here and make this really, really pretty, right? And label things, kind of move things around. But we're doing pretty good. Okay, let's put a big label on the whole thing. Let me get a big font. Boom. I'll just steal that. Lots of stealing. Good. We'll come up here and just put this here, and we're just going to say stereo audio amplifier. Cool. All right, and what's it called? Oh, I gave it a name, didn't I? I called it the Beatbox amp. And I'll put a dash, okay? Beatbox amp, stereo audio amplifier, looks good. Okay, all right, so we're getting there. So you got the outputs, that's done. This DAP, we got to see what that does. We've got this signal right here, which is going to be pulled up, so it will not be shut down. It'll be running. So this signal's right here. So now let's go ahead. Now for kicks, let's just use a label here, and we're going to go here. I want to use a port label. I prefer these. So let's pull this out just pull this out just a little bit. Okay, and now let's get a port label here. Okay, and what are we going to call this? This is shutdown. So we're going to say shutdown, and we're going to put a little n on it, meaning it's active low. Okay, shutdown n, active low, fine. And then, so remember, you can run wires all over the place, or you can put labels on things, and then wherever the same labels are, those nets will connect, right? So we don't necessarily have to run wires everywhere and make it a super big mess. But things like this, the audio outputs, the audio inputs, you know, they're very close to the chip, so we might as well put those as wires, design those as wires. Okay, so we've got our power LED. Things are looking good. And now, so now we're going to figure out what this whole gain select business. Let's go read about this. Okay, so gain select and gain select. Okay, all right. So let's see what it says. Okay. Oh, so it looks like you only have two selections. So if you put it high, you get 6 dB. If you put it low, you get 12 dB, decibels of gain, right? And we've talked about a decibel measure for power gain, for voltage gain and power gain. It's either 20 log of the ratio of the input to output, or output to input, excuse me, or it's 10 log. So if it's power gain, it's 20 log the ratio, and if it's voltage gain, it's 10 log the ratio. It's just a measurement, a logarithmic scale of gain if you haven't taken the class. So anyway, I think it looks like that, yeah, you just selected high and low, huh? So let's go through here. All right, gain select function. Let's read this. I'm not going to read it out loud to you. You kind of, if you can, hopefully you can see this with me. Let's just kind of read through here. Huh. Okay. So it looks like this pin high or low, it selects the gain of 6 or 12 dB. Okay. So what we're going to do is we're going to do the same thing here. We're going to pull it up. We're going to pull this up to V sub dd, and then we're going to make it an input. Okay, so we're going to literally kind of copy this circuit here. Hopefully we have enough room. So we're going to do this same circuit twice, and we're going to have kind of an external input that controls the gain. All right, that's one way to do it. So let's see. Can we scooch this over a little bit? Give us just a little bit more room. You know what? I think we got enough room here. Let's do this. Okay, so also on this pull-up, let's fix this. Let's make that 10K, all right, for that pull-up. And then let's go ahead and we're going to copy this. And do we have enough room? So if we put it there, we don't have enough room. So let's go ahead and let's scoot this whole IC over here. And we'll put that there. Be very careful when you're scooching things, right? Because you don't want some, see like what just happened right there? Look at that. Oh, yeah, you got to be careful. All CAD programs are DOS programs, basically. So they're very old and they have really weird artifacts. You got to watch what you're doing. Be very careful. Watch what you're doing. Okay, so that seemed to work. So now I'm going to grab this. Okay, and right about there, I don't like things touching, so I'm going to move this over one. Come on. Grab the wrong thing. There we go. Okay, good. So now I'm going to put this right here, and this is going to go here. And this is going to go to this pull-up here. Now, this pull-up might have to be a little bit lower. It probably doesn't require any current. We could look in the data sheet to see how much current this is going to source or sink when we select gain. But we'll put it at 10K, and hopefully that'll be enough to hold it. All right, and we're going to make this an input. Okay, so I'm going to call this gain, and is it just called gain select? Yeah. So we're going to call it gain select. All right, and now, okay, so then let's go here and IO type, we're just going to call it bidirectional. It's not bidirectional, but I like the symbol. All right, I don't take the time to make all these different ports, inputs or outputs or this or that, because it's just too much work. It drives me nuts. Okay, all right, so that's that. So now both of these will be pulled up. So it'll be in the gain mode when it's high. So if we go here and we say For differential gain of 6 dB should be permanently connected to V sub dd or driven to logic high. For differential gain of 12, it should be to ground. All right, so the bottom line is if it's a low, it's going to be higher gain. So we're going to put it in the lower gain mode so it doesn't blow something up. All right, so that's good. One last thing, these colors are driving me crazy. So the fill color, I'm just going to make this port, we'll make it this little blue color, and we're going to make the border color black color, and we're going to make the text color a black color. Let's see how this looks. All right, that doesn't look very good. So let's make the text color, where'd the text color go? Let's make the text color white. Okay, that's better. All right, just, you know, everything doesn't have to be completely ugly. And was it that one? And the text color was white. And again, I'm just showing you things as we're doing this. Also, the border is black. And and you know what? Well, you know what? Let's just make these different color to represent that there's, you know, different things. How about let's make this one kind of this green or aqua color. No, it's a little bit too much, even for me. Let's make it kind of a dark. Make it this brown color, kind of. Whatever. All right. So now we're getting there. What time okay, we're doing okay. We're about an hour in. Let's see here. So what are we missing? So we've got this gain select. Now let's put this out. Let's port this out to some kind of control port. So we could do the same thing. Okay, so let's think about this. We could do the same thing with these ports, these terminal blocks. And so that we could control this externally, because maybe you want to plug this into something and control the gain, or we could control it with a switch. We could control it with a switch, right? Now for shutdown, all right, so what I'm going to do is this, and again, this is just design. It's, you know, whatever you want. So let's do this. Let's we're not going to put these to terminals, but we're going to put them to a header. Let's put them both to a header so they could externally be controlled if you want to control it. All right, the thing will not be shut down in default, so it'll be running. The gain will be low, and we'll put it to a header, and if you want to do something with it, you can through the control of the header. Okay, so let's go ahead and let's do this. We're going to go here, and we're going to, well, you know what? Let's do this. So let's just show the use of these port pins. All right, so now I'm going to put them right here. And then what I'm going to do is these are basically wherever these are will connect to these lines here. So I'm going to take one of these guys and I'm going to go here, and then I'm just going to put this right here. So this is, and we're going to call this gain slash shutdown. Call it shutdown. And these are just notes to us, right? This doesn't get printed on anything. All right. And so now we're going to make pin 1 is going to be the shutdown pin, and pin 2 is going to go to this. Okay, so those two go there so that you can access them from the external world. Now, on the gain select, I also want to have the ability, maybe with a switch, to change what this thing is. So let's add a switch. Okay, so let's add a little slide switch, and I think, yeah, where am I? See this little slide switch right here? This is a really small switch. There's a company called eSwitch, which makes a lot of cool little switches. So we're just going to use this, okay? If I can get it to select. Good. All right. Okay, so we got our little slide switch right here. And we are going to, basically, in one position, it's going to turn the switch on, it's going to turn it off in the other position. Okay, so what do we want to do? We want to ground this thing. So I'm going to take this, I'm going to ground it here. All right, and then in the other position, it's going to do this. So when it's in one position, it'll do nothing, so it'll just get pulled up high up here. And then once the other position, it'll ground it. And then at worst case, we'll have a circuit with a 10K dragging current through here, so it's not going to hurt anything. Okay, so now what is this thing called? This switch here, let's put a little name on this. So this is a EG1217. So we can leave that label, what that is right there, the value of it, so we know what the the part number is on, because we're going to use a specific switch, just like this specific part right here. But let's put a little label on it. And what I like to do is do this, and let's just shoot this text down to about 12-point font. Whenever you do anything messing with fonts or whatever, this tool Circuit Maker, I think it goes to the cloud and downloads stuff. I'm not quite sure because fonts are already loaded on the computer, but I don't know what it does, but it seems like it's going to the cloud for some reason and downloading things, who knows. So it takes it about 30 seconds. There we go. All right, and let's smallen this font maybe to size 14. All right, that's good. All right, and then we're going to put this right here. And so what is this, everybody? This is the, what is this? Gain select 6/12 dV, okay? And we're going to have to know which way is which, and we would do that on the PCB itself. We would put some writing so we could say 6 dB or 12 dB on the PCB. All right, so let's move this a little bit out of our way. All right, cool. Okay, looking good, looking good. Let's see here. Now, what else do we have? Okay, we've got power. We got to bring the power into this thing. So right now we're bringing the signals in on terminal blocks. We're bringing the signals out on terminal blocks. Let's go ahead and bring the power in on a terminal block also. All right, why not? Okay, so we're gonna kind of bring the power in. Typically, I bring the power in the top left of a design. Okay, so I'm gonna bring it in right here. All right, just like that, as simple as that. And pin 2 here is ground, pin 2 here is ground. So just be consistent and make this pin 2 ground. Again, it's not going to matter, but I just like consistency. The less you have to remember when you're doing electronics, the better. So if you have conventions, better. All right, and then here's V sub C in. So here's where V sub C in is going to tie to. Now, if there were other devices on here, I would have some filtering on this input, but there's only one chip and it's already got its own filter. So we're just going to bring that in there, and that's that. Okay, let's see. All right, what do we got here? All right, so we've got our input here. We've got our other input here. We can come in both ways on a terminal block or on headers. We've got our filtering capacitor here, which is basically going to block DC. And where's our kind of reference design? Our crude reference design, which is the bare minimum usually. There it is. All right, so we're doing this one. All right, we've got that hooked up. We've got capacitors to ground. So this is very important. A lot of times when you have a differential input and you want to use it in single-ended mode, be careful. Don't just hook the other end to ground. A lot of times you have to hook it through a capacitor. All right, be careful of that so that AC can pass through here. All right. And those are 0.39, is that the recommended one? And those may be wrong. There may be better values to make those at, maybe 0.47, 0.22, maybe 1 microfarad. So we'd play with that in our design. Okay, we've got our filter, which we did our better filter up here, which is a much more robust filter. It's got a high frequency ferrite B, then it's got really good bypassing on the inputs. We've got a stable power supply, then we split it off, and then we bypass with a high and a low, so we get low noise. Then we also have 10 microfarads for charge, so we can get that current when we need it. And then gain select, we just know that it's high and low. Shutdown is low, so we're going to pull it up high, so in default the thing will be running. The outputs, no magic there, it's a direct connection, which is what we like about this IC. Okay, so that is that. And that is about it. And let's see. That's it. We got our LED. We're all good to go. Okay, so now one problem we have is all the reference designators are all over the place. So now you can let the system do it. So let's go look at that. And you know, I use so many tools, everybody, an enormous amount of tools because I do software and hardware and firmware and mechanical that you know, if I don't use something for a week, I forget where certain things are. Okay, so now what we're looking for is we are looking for to be able to label all of the reference designators. So we're looking for that option. So it's not here in view, definitely not there. In home, so there's net label here, component, junction, directives, no that's not it, round, it's not here. In project, commit, add existing variants, templates, no it's not there. Tools, number sheet, yes, this is where it is, it's in tools. Okay, so under annotate, if we go here and we say annotate schematic, that is reset 26 changes, and that is not what I wanted. Reset duplicates. Okay. Reset duplicates. So that's what that, okay, so that reset. There's a way to annotate the entire thing. Let's see, annotate schematic quietly, force annotate on all schematics. Yes. Okay. All right, there it is. So anyway, so that went through and annotated everything and made sure that we don't have any duplicates. Now, you can also go through manually, which is what I prefer to do, and just go through manually in kind of a sensible way. If you have, hundreds or thousands of parts, a lot of times it's a lot of work, but a lot of times I like to keep, my capacitors, resistors, and blocks so I know where they are in the design. But anyway, this looks like it did it right. And we're okay. So T1, T2, T5, T3, T4 kind of jumped over there. We've only got one resistor here, R2, R3. We've got one FP1. The capacitors all look pretty good. So anyway, so that's not bad. Okay, so we'll stick with that. Okay. All right. Now we're ready. So now what I'm going to do here is I'm going to save this project, and then I'm going to commit the project. And this is the first time that I've done it. So it's all good to go. Now what I'm going to do is I'm going to right click on here and we're going to say compile. All right. And as we compiled, we saw no errors, so there's no problems with it. All right. So that is it. So that is our schematic for our amplifier. So what's the next thing? We're not going to do it in this video. We don't have time to do it. But the next thing that we would do is we would go to our project here, and we would say add new to project, and we would say add PCB, right? And then we would name this PCB, and then we can go ahead and do this real quick, but we're not going to finish it. We just don't have time. Beatbox amp and version 1.0.0.1. I always feel like I'm keeping you guys after class, and I know everyone likes to get done. Okay, so there we go. All right. Okay, now we've got this, and now we're going to go back here. So we got this thing right here, and then what we do is let's recompile this one more time. And then what I'm going to do is we're going to save the project. We're going to commit the project. This is just me making sure everything's all hunky-dory. Okay, now if we go here, there's nothing there, right? So then what you do is you can go up here to home, and then you go to project, and then you go import changes from CC Beatbox, and then this is going to push all of this stuff. So we say validate changes, and we say execute changes, and of course in section 8 is a whole class, a whole course, as big as a whole course on PCB design. All right, then we say close, and then all of our parts are right here. So then we would just start placing them in a sensible way. So maybe we can do that in another video, and then if we want the 3D view, we can go here, right, and we can see what they kind of look like, exactly what we expect. Okay, so everything is as it should be. But what I wanted you to do is I wanted you to see the process. So here's an amplifier. So this should work. We got good power. We got power coming in. We got our right input. We got our left input. We got our left output. We got our right output. We got different ways of getting the signal out, different ways of getting the signal in. In default, the chip will be enabled. The gain will be selected at 6 dB, or we can control it with our little switch here to switch it into 12 dB if we want to get some more gain out of it. And that's it. That's it, everybody. So there you go. So there is an amplifier in real time, how my thought process works, a fraction of what the things that you have to do. You can look at what other people have done. You can go look for ICs at different vendors and go through them all. Now, if we were really going to do this as a professional product, we'd spend a weekend just looking for chips, right? Then we'd maybe spend a week or two evaluating some chips, maybe get some dev boards, maybe 2 or 3 weeks, right? Then we've kind of say, hey, we really like this chip. It's got a good price. It's really available. Then we'd build some prototypes of it like we're doing here, lay out the PCB, send it out, evaluate it, test it, verify it, and then say, like, this is cool. I'm going to make a product out of this. Bam, right? And that would be it. So that's it. So what you can do is you can look for this project, CCE, under Beatbox Amp _ V1 _ 001, right? Beatbox Amp under my account on Circuit Maker if you want to download this and finish it up or play with it or make your own version of it. And I'm curious, I don't remember using this chip, but I mean, You know, who knows? Maybe I have, but I'm curious to see how this works and if it's a nice little amplifier. So anyway, that's it. So I will see you in the next lecture. Bye. Hello, everybody. It's been I think a couple months since I've done a bonus video. I was planning on doing a programmable logic video, but the hardware that I want to use, it's called, the company's name is Silago. I'm having trouble getting it to work on my particular computer. There's a driver issue or whatever. So I'm still trying to work on that, but it is a very cool way to get into programmable logic. So we'll talk about that next time. Anyway, in the meantime, I've had a couple different people ask the same question, and it's about 555 timers, but more specifically, kind of some math stuff, how to solve for the different variables of a 555 timer. There's two resistors and a capacitor, and some of the students are having a little bit of trouble with the math, maybe a little rusty or whatever, and so I wanted to kind of go over that, which also lends itself to solving many other similar problems where a system of equations is underdefined, so you have parameters that you can set to any value you want. And this is a common theme in electronics. A lot of times you have a variable and you can set one variable and then you still have another variable maybe and even another variable that can be anything. So you're like, well, what should I set it at? Well, so typically we want to set these things at values that are reasonable or sane, all right? So anyway, you'll figure it out when I get into this. So right off the bat, let's go here and let's pop open DigiKey and let's see here. So let's just look for a 555 timer, and then this, of course, depending how much of the course you've taken, you may have got to this section or not. We've already talked about 555 timers and gone over a lot with timers and clocks and oscillators, but I'm just going to do this. I'm going to try and keep this fairly quick. I know I always say that, but I never do. Try and keep this quick. But we're gonna talk about this math problem because I think this is something that a lot of people are having a little bit of trouble with solving systems of equations. All right, so we type in 555 timer and we get this coming up in DigiKey. All right, so now we go here and we say, let's say we want cut tape. All right, and we want in stock, we want RoHS, good enough. And comes back and we have a lot of different options here. Of course, let's always say active. We don't want anything we can't get our hands on. All right, so let's leave it right here. We could pop open more filters, but we're going to leave it here for now. And then we start to scroll down here and we can see we've got 50 or so possibilities. Now there's of course, when the 555 came out originally, there was just, one kind of 555. Now there's many kinds of them. And now there's faster 555s, dual 555s, CMOS 555s, all kinds of variants. So now if we look here, just the way the search came up, we've got some 2.7 megahertz, we've got 100 kilohertz. This is kind of the standard 100 kilohertz. 1 megahertz. Let's do a couple things here. Let's just do a couple things for fun. So first, let's search on price, and let's reduce that and see what we get. So for 37 cents, for 37 cents, we get a half a megahertz 555. Let's see, 40 cents, 46, 100 kilohertz, 100 kilohertz. Okay, so no love there. So right off the bat, if we want to go and play with this NE 555 from Diodes Incorporated, it'll go to half a megahertz. But here's what I don't like about it. It goes from 4.5 to 16 volts. This means it's going to work on a 5-volt system. Now, if you wanted it to work at 12 or 9 volts, that's great. But if we wanted it to work at 3.3 volts and 5 volts, this is requiring a little bit too high of a voltage. Let's change things up. Instead, let's search on a frequency, and let's start at the highest frequency. All right, if we start at the highest frequency, we get this Rohm semiconductor part here, and it is not showing the frequency. I'm sure we could go look that up, but I don't really care. But look at this Nexperia 555, and this goes to 89 megahertz. That's pretty cool, but that's too crazy of a chip. Now look at this little tiny guy right here. This Micrel part or microchip part. from Microchip Technology. This is a 5 megahertz 555. So that's kind of interesting. It's in this tiny, cute little package right there instead of a normal 8-dip package. So, and then coming down here, here's an SoC, SOIC, small outline integrated circuit, an LMC 555, and this one goes to 3 megahertz. So we've got some 5 megahertz in these kind of small packages, and some 3 megahertz. We've got a BGA there, some more SOICs. Now, for us, playing with our solderless breadboards, we probably want to have a DIP package, right? Dual inline package. So let's just go over here and let's see if we can get a DIP package, which should be here. And not sure why that's not showing up. Let's just go back to 555. And remember, when you're doing searches in DigiKey, this happens a lot. Depending on the order that you change your search items and kind of drill down, the search space will change in different ways. So if you do A then B, it's different than doing B then A when you're doing a search. So it's got some weird little peculiarities. All right, let's make sure it's ROHS. Let's do cut tape. It's again apply filters. All right, so I bet you this ROHS is killing us right here, but let's see here. Dip, dip, dip. I do not see a dip here. That's really curious. Okay, let's get rid of ROHS and just let them have lead in them. All right, and then still, unless I'm blind, I don't see any dips here. That's really interesting. Okay, let's go back. 555 dip. All right, let's go here. Okay, and all right, there's our dip or pdip package. All right, so let's stick to those two packages right there. All right, let's make it active. Let's make it in stock. Let's make it ROHS. And again, this is why you got to play around with DigiKey because a lot of times the order you do things, how you get into the search can change things. Okay, now we can see the dip package. So why that didn't come up when we just did 555 timer, I don't know. All right, now we get into here and we can see we got some variation. So we see this is a 2 megahertz, 2 megahertz, 3 megahertz. This 3 megahertz, this is nice. This goes from 1.5 to 15 volts. So that covers the entire range of kind of what we're interested in. So, and this is called an LMC, the C for CMOS, LM555. Let's take a look at this one from Texas Instruments. This is kind of a nice part. All right, so the LMC 555, and I've used this, and this is a common one that I do like to use because it does have such a high frequency and then it also has a nice voltage supply range. All right. Okay, so let's go ahead and jump right into the data sheet here and let's see what it is I'm talking about. And again, if you're just coming into this not knowing what's going on, the 555 is a timer chip, and it allows us to use a resistor and a capacitor to set the duty cycle and set the frequency. All right, so let's take a look here. All right, so we got the 555, we got the timer, okay, 2016, so this one is fairly up to date. All right, and now what we want to look for is we want to look for the astable or astable mode of operation, which is just kind of the free running mode of the oscillator. All right, and that's not showing. Let's try just astable, and that's not showing up. And let's try A-stable, and then we will just go hunting for it. Okay, so that's not helping us. So we are going to just jump down here and try and find the various versions. All right, overview here, and let's see here. Okay, so that's monostable one shot. We don't want that one. Monostable, don't want that. Astable. So why that didn't find it? Maybe it was a matching case when I originally did astable. Anyway, all right, so here's astable or astable. The circuit diagram looks like this, and then this is kind of what's happening with the internal electronics, and then we get an output waveform. So there's a couple things that we can control here. So there's RA, RB, and C, and then here's the circuit schematic. It's very, very simple. We basically tie trigger back to threshold. We put a capacitor off of V sub CC, the input power. This is our normal bypass capacitor. Then we've got two resistors, RA and RB, and then we've got a C. All right, And we've got our ground, we've got a reset, which is a reset low, so we want to pull this high, and then this control, which can change some of the features, but you don't have to mess with this actually. Now, let's look at the equation. So this is where everyone's getting caught up with, all right? They're getting confused with these equations. So we've got T1 equals this equation, all right? And T1 is the output high, and T2 is the output low. So the total T, or the total time, or period, T is T1 plus T2. And then if you just do this math and run this math here, T1 plus T2, right? Find a common denominator, you get this equation right here. I think we can all follow that, right? Now, frequency is always 1 over period. So then if you do the math, you'll get this equation right here. So these equations describe the duty cycle. They describe the total period, the total frequency. And then if you want to compute the duty cycle, D, it's RB over RA plus 2 RB. So that's what the duty cycle is. And we want the duty cycle to be, 50%, right? The fraction of the total period that the output is low. So for their definition, it's the output is low. So 50% means it's half the time it's low, the other half the time it's high. So we ideally want a 50-50 duty cycle, right? So that kind of defines that. All right, so now we've got these equations here. So then you say to yourself, okay, great. Well, all right, I want a certain frequency. Let's say we want a certain frequency, right? Then, well, I've got RA, I've got RB, and I've got C. So what should I do to pick these things, right? Well, uh, you've got 3 different variables, right? RA, RB, and C, but you only have one frequency that you want. So how are we supposed to pick these? All right, that's question number 1. Question number 2 is, well, you don't just have a frequency, you have a duty cycle. So we have 2 equations at least now, but we still have 3 variables. All right, so we have a whole series of possible solutions. So now if you look at the data sheet here, check this out. This is for different capacitances, all right? And then it's showing you at different capacitances and at different resistances, these are the kind of frequencies you can get. So this is showing a series of solutions, which are lines. So you're getting 2-dimensional lines, and you can find a solution anywhere on here, okay? So what it's saying right here is, I believe in this particular chart, is that if you have RA plus 2B and it adds up to something in the 10 meg, the 1 meg, the 100K, the 10K, the 1K range, right, then you can pick off what your capacitance is that you want to set the capacitance as. So for example, let's say that whatever RA and 2RB add up to, it's something along, we're going to fix it at say 10 megohms, right? So if it's 10 megohms, then we say, all right, I want to run at 10 hertz, okay? Then we come over here and then we go to the left, and that means the capacitance has to be 0.01. So that's how you can use these charts if you like to. But let's just do the math. The math is much easier to, this is kind of confusing, I think. So let's just look at the math and let's see what we can do. So let's go down a little bit farther here, all right? And we want to look at this circuit right here, output. Okay, so this is kind of a good little circuit that we can do. So again, we want to, let's see, this is monostable. That's not what we want. We're gonna go back to this circuit up here, and go to this circuit here. So this is what we want for our circuit, all right? And we have to pin the pin numbers to this so we can figure out what's going on. But right now we have these modeling equations, all right? So that is what is important. So let's just get to this. So what I'm going to do is I'm going to program up here, and we're going to copy these modeling equations down. So I'm going to copy them for you. I don't have them memorized. I've used the 555. You know what? I'm lying. I did have these memorized when I was younger, probably when I was a teenager. I had them memorized, but now I don't memorize them anymore. Okay, so let's go over here. So we're going to say T1 equals, and T1 is the output high time. We really could, you know what, let's just call this, I'm going to call this TH for T high. That makes more sense. All right, so it's 0.693 times RA plus RB times C, the capacitor. All right, and then T2, which we're going to call T low, because it just makes more sense, equals this one's easier, this one's simpler. 0.693 times RB times C. So those are 2 times. So then the total period T equals T low plus T high. And what does that mean? Let's make a little graph here. So make a little graph, and then let's make a little waveform. So, and we'll start the waveform here and say this is low, and this is the high portion here. All right, then this T low is this time here, and this T high is this time here. That's what that is, all right? And we got our little graph here, and then this is just time going this way, all right? And this right here, of course, is just amplitude, which typically would be voltage. All right, so we've got these two modeling equations. So let's do a little math. Again, I don't want to assume that everybody is good at algebra, even though it's kind of a requirement. It's just kind of basic high school algebra, but we have some of our students that are even in junior high school maybe trying to take the class. So we've got these two things here. So if we have T high and T low, and we just add these things together, right? Let's just see what that comes out to. So T, we're just going to say T here, right, equals this right here, 0.693, right, RA plus RB times C, right? And then plus 0.693 times RB times C, okay? So what can I factor out of here? What can I factor out that's easy? Is there anything we can factor out? Well, we can factor out this right here, this term, right? We can factor that out. We can factor out the C term of each one of these, right? Because it's a product, so we can do that. So let's go ahead and do that. Let's write this again. So then we have T equals 0.693, and I'm just going to parenthesize this. All right, and then we have C, right? And that's it, right? So we factored that out, and then what do we have left? We have RA plus RB, I'll just put some parentheses around that, plus RB, all right? And we'll bracket that up. So we can add these things together, right? So we can come here, now we can say, again, we can say 0.693 times C. And then here, let's simplify this. We've got RA plus RB plus RB. So what's that? That's just RA, oops. That's just RA plus 2RB, okay? And then if I go look at our equation here, and that is correct, good, so I did the algebra right. All right, so that's it. So that's all I did there. So again, some students are having trouble just with doing this math right here. So this is just basic algebra. So I'm just collecting like terms and pulling them away, right, factoring them out, and then whatever's left, and then this is the result of that, okay? So that's it. So the simple equation right here is the total time. Okay, now let's look at the duty cycle. All right, and again, this up here is the showing kind of the format of where we're getting this duty cycle from. So the duty cycle in this equation, all right, the duty cycle in this equation is actually duty percentage, all right. The way that they're defining it is the fraction of the total period that the output is low, all right. So they're defining it like that. You can do it either way, that it's high or low. So it's T low over T low plus T high, or we could say that's also equivalent to T low over time total, the total period. Okay, so that's what the duty cycle is. Now, we ideally want this thing to be around 50%, right? So we want it to be high and low the same amount. So that's kind of one of our requirements. Now, if we go through and do the math, we call it D for duty cycle, then it ends up being RB over, and all we're doing is the algebra again, over RA plus 2 RB. So all that is we just did this. TL divided by TL plus TH. TL plus TH is what? What? That's this, right? That's that. And then TL, right? Whereas TL is just this. So if you take this expression over this expression and simplify, you'll get this expression. I'm not going to do that um, because it's going to take too much room. All right, so now we have our two expressions. So we got this expression here, which is t, which is just in the data sheet, and then we've got d, which is also just in the data sheet. Okay, so now let's go back to our circuit here. And I'm going to bring it back over here with my PDF viewer because Adobe PDF does not work at all. All right, and let's look back at our circuit here. Here we go. Make this a little bit bigger for you guys. All right, and so we've got RA, RB, and C. So that's it. So we've got these three different things. All right, now we go back and we say, all right, we've got three different variables, and we have two different equations here, right? And so I want to get a certain frequency and I want to get a certain duty cycle, and that's all I want. All right. So now let's take a look here. What starts to happen? And this is the question that the various students have asked. So we've got what our total period is, and then we also know that. Let me go back and put the data sheet over here so I can see it over here. Good. Okay. So we also know that the other equation is that if you take, if you want the frequency equals 1 over the period. So that means I just need to invert this. Okay, so if I just want to invert this, this is pretty easy to invert, right? So 0.693, right? So if we just take a calculator, 0.693, and we invert that number, right? We're going to get 1.44. So we get 1.44 and some change, and then we just take this right here and then put that in the denominator. So this right here is simply 1.44 over this exact same thing, and they like putting it in this form here. So I'm just going to be kind of consistent, RA plus 2RB. Now, what I like doing when I'm messing around with this kind of stuff is I like to make an Excel spreadsheet. Make Excel so that it solves for these things. So you put in a couple numbers and it gives you a solution. That's kind of a fun thing. In the course, we do many lectures, maybe not many, but we do lectures where I show you how to use Excel if you're not familiar with it, if you've never played with it. But it's a really good tool to do math and not just do accounting stuff with. So it's great to do calculations where you have formulas like this that model various things. We can use Excel also to draw charts of it, solutions, which is also nice in 2D, 3D space, etc. Okay, so this is what the frequency is. All right. So now here is where the crux of the problem that I got from a couple people. Let's use green. So they said, okay, here's the frequency, great, and I'm not sure what the duty cycle is. A lot of them didn't really, duty cycle didn't really get, but so we know what duty cycle is. It's the percentage of, how long this thing is high and low, and in their case, they're defining it as the low time over the total time. All right, so that's duty cycle, all right? So that's fine. So we have two different things, two different modeling equations, but we have three variables, RA, RB, and C. So how do I pick these things? All right, so we can solve these things, and then we can come up with a linear equation which will give us a solution space that's a line, an infinite number of solutions basically, and we can pick one of them. All right, but before I do that, let me just do something different. So let's say that in our heads we say, all right, we want to make something, and it's got to be within the range of the 555, but let's say I want the 555 to put out a frequency of, let's say, 10 kilohertz. All right, so let's say 10 kilohertz. So our target is F equals 10 kilohertz, okay? All right, I don't know anything about RA and RB yet, but I know I want 10 kilohertz, okay. Then let's say for the capacitor, I don't want to solve for the capacitor because I could get some crazy capacitance value. Now with resistors, you can usually find any resistor value you want from 0 to mega ohms and anything in between these days. But for capacitors, it's harder. So instead, let's pick a very common capacitor. So I'm going to give you a rule of thumb. Okay, if you want to make something that's going to oscillate like in hundreds of kilohertz or even megahertz, I want you to maybe use a 0.01 microfarad capacitor. If it's going to be like hundreds of kilohertz or 10 kilohertz, just use like a 0.1 microfarad. If it's going to be like thousands of hertz, maybe use a 1 microfarad. You see what's going on here? If it's going to be hundreds of hertz, maybe use like a 10 microfarad. And if it's going to be in hertz, maybe I want you to use a 100 microfarad. Do you see how common these values are? All right, so here's the deal. So over here is megahertz. So anytime you want to kind of do a megahertz oscillator, try a 0.01 maybe. Start with that as the capacitor. And then as you get down to hertz, then use 100 microfarads as your capacitor. Set this exact value because you can get these very easily. Okay, so let's go ahead and we're going to try, and this is where this leap of faith happens. We're going to set C at this 0.1 microfarad. We're just going to set it. All right, so 0.1 microfarad. That's what we're going to set C as. Okay, now we have C. Good. And now watch this. So we want our frequency to be 10 kilohertz, right? And then maybe we should have made that 1 microfarad, but we're going to just leave it at 0.1. We're going to see what happens here. Okay. So now we have this formula, and it says F equals 1.44 over RA plus 2RB times C. Okay. Well, what about this? What about we can just solve this whole thing for this term here. For example, we could do this. So 10 kilohertz, check this out, equals 1.44 over, see this term right here? Now I'm going to be tricky for a second. I'm just going to call this whole thing, just for a minute, I'm just going to call it R. Okay, is that okay? I'm just going to call it R. And then we have C here, C, right? Just RC. So R really equals this term here, R times C. What does C equal? 0.1, right? So this is really 1.44 over R times C, which is 0.1 microfarads, all right? And that whole thing equals 10 kilohertz. Okay, so can we solve this whole thing for R? Sure we can. That's really easy, right? So we've got, take a look here. So we've got R here. So all I'm going to do is I'm going to multiply both sides by R. So I'm going to bring R up over here by multiplying both sides by R. Okay, that'll cancel it out here. So now I've got R over here. And then I'm going to divide both sides by the 10 kilohertz. Divide both sides by 10 kilohertz. Okay. All right. And we'll put it here. Make this long enough. 10 kilohertz. Hopefully you can see this. All right. So these will cancel out. So now R equals 1.44 over 0.1 microfarad times 10 kilohertz. Okay. Let's go ahead and calculate that on our calculators. All right. So here we go. 1.44 divided by 0.1 to the minus 6th times 10 to the 3rd. All right. And some of you also have had trouble with scientific calculators. So remember, micro means 10 to the minus 6, kilo means 10 to the 3rd, etc. All those different multipliers, you have to learn how to put them into the calculator. And typically, I don't know if you'll be able to see it, but there's like the exponentiation key right there. So if I want 10 micro, I'm going to say 10, then I'm going to hit this, then I'm going to hit minus 6, enter. So do a YouTube video on how to use scientific calculators if you need to. All right, so this says, if you can see that, 1440. So the total result is 1440. So R equals 1440 ohms. Okay? So we're done. So R equals 1440 ohms. All right, so now we're getting someplace. So we got C, it's 0.1. R equals 1440 ohms. Now wait a minute. But what does R equal? It equals RA plus 2RB. Okay? So now, well, now we've got R, so now we know that this whole term here, R, almost, we know that this term, where are we here? This term right here, sorry, this term equals our R, right? And then here's our duty cycle. So this is 1440, right? And then this is RB. So part of RB is in this. So now we again, we have some choices here. We have to pick something that we want, all right? So now another thing that I want is, I want to make sure that my duty cycle is like 50%, 0.5. Okay, so now watch this. So we'll set duty cycles equal to 0.5, all right? So that means that 0.5, or if even make it easier, let's not even use decimals and make it easier like this. Check this out. 1/2 equals RB over RA plus 2RB. Okay, so 1/2 equals that. All right, so now let's maybe flip this around, make it a little bit easier. So I'm just going to cross multiply here. All right, so I'm going to multiply the bottom times the top and the top times the bottom here. So check this out. Okay, so let's just cross multiply here and let's see what happens. So we're going to get 2 times RB equals 2, I'm sorry, so that's 2 times RB and then 1 times this quantity here, which is just RA plus 2 RB. It's hard to do algebra on this. You'd be surprised how difficult it is looking at it and trying to do it. It all looks alike at the same time. Okay, so now take a look here. Take a look here what's going on here. So this says 2RB equals RA plus 2RB. The only way to make this true is if this is 0, right? And you can kind of see it here. If we want 1/2 for the duty cycle, RA has got to go to 0. If RA goes to 0, then RB and RB cancel out and we get 1/2, all right? So this just models the duty cycle. So what it's saying is the duty cycle of 0.5 is a very special, it's a singularity, it's a special point where if you want that perfect duty cycle of 0.5, then you get away with being able to set RA to 0. All right, so we're just going to set RA to 0. Okay, great. So now we go back and we look at our equation, our frequency equation. So again, we're trying to get 10 kilohertz, and then we know that our total R, right, R has to be RA plus 2RB. Our total R has to be RA plus 2RB. All right, we just found out that if we want a duty cycle of just 50-50, 50%, we can make RA equal to 0. Well, that simplifies our life. So then it says that 2RB equals R. That's all that is resulting here. So let's just write this down so we don't confuse everybody. 2RB equals R. What's R? Well, we figured out R is 1440 ohms. Okay, 1440, that's the worst omega I've ever seen. There we go. And then, therefore, RB equals, divide both sides by 2. All right, so that's 720, right? 720 ohms. All right, so RB equals 720 ohms. RB equals 720 ohms. Okay, so RB equals 720 ohms. Where do we go? RA equals 0. So if we have RA equals 0, we have RB equals 720 ohms, and we have C equals 0.1, we should get out 10 kilohertz. Let's check it out. All right, so let's actually run this back here. Okay, so let's give it a try. So this is the frequency. So frequency equals 1.44 over RA plus 2RB quantity times C. Let's try and do it. So 1.44 divided by RA, which is 0, okay, plus 2 times RB, which is 720, times C, which is 0.1 microfarad, all right, and finish my calculation here. That calculator upsets me. Okay, 1.44 divided by the first term, which is 2RB, so 2 times 720 equals, there we go, divided by the C, which is 0.1 microfarad, 0.1 microfarad. There we go. All right. There's the answer. 10, or if we put it in scientific notation, 10 kilohertz. Okay, so that works. So that means our values work. So then what's the moral of the story? The moral of the story is when you're doing these calculations for the 555 timer, pick a capacitor that you have, because you can find any resistor, but you can't find any capacitor. Pick a capacitor that you have. If you're working with megahertz, a really small capacitor is what you need. If you're working in hertz, a big capacitor is what you need. So just these few 5 or 6 capacitors, each one you can see is like 10 times the other, 10 times previous, right? That'll get your capacitor. Then go over and kind of decide what you want your duty cycle to be, 10%, 20%, 30%, whatever, 0.5. And then when you do that, that's going to kind of lock down the relationship between RA and RB. Then you just pick RA or RB, and then you can solve for the other one. So that's how you do this. Now, let's do this one more time. So let's just remember that 720 because we're going to actually build this. But let's delete all this. All right, let's delete all this, and let's do this one more time, the hard way. All right, so now let's assume, and the eraser on this sucks, so I'm not even going to try messing with it. Instead of 1/2 for the duty cycle, all right, so instead of 1/2 for the duty cycle, let's say that we wanted, let's say, I'm trying to pick a simple number. Let's do 1/4, all right? So that would mean 25% was the duty cycle, 1/4. Let's do that instead. So instead of 1/2, all right, can I get away with and do this for you guys? All right, and then I'm just gonna, I don't even want to mess with the eraser. Every time I do, it kind of messes things up. Okay, so 1/4 equals RA plus this, RA over RA plus 2RB. So now let's go ahead and let's multiply this out. All right, so again, we get, what do we get here? We get 4RB equals just this term down here when we cross multiply, RA plus 2 RB. All right. Okay, so now let's just divide both sides by, no, let's not do that yet. First, let's subtract 2RB from both sides. 2RB from both sides minus 2RB minus 2RB. All right, what do we get? We just get 2RB equals RA. Or we get that RA equals 2RB or RB equals 1/2 RA. So this is our equation. So it just means that they're twice as much as each other. That's all we need to do to maintain the duty cycle. Okay, we need to do that to maintain the duty cycle. But we also know that if we want the frequency to be right, the 10 kilohertz, their sum must be 1440. Okay, so their sum must be 1440. Okay, so here is where the math that was giving people trouble comes from. All right, so what I want to do is I'm going to, I don't have much room left here, so I'm going to remember this. So RA equals 2RB, and we had a total R of 1440 ohms. Okay, so let's just do this and delete this. All right. So hopefully I remember that. So we had 2RB equals RA, and that was for a duty cycle of 25%. Okay. And then we had our total R equaled, remember what that was? It was 1440 ohms. That was at a C of 0.1 microfarad, which we set, and that was for a frequency of what? 10 kilohertz. All right, so in our previous example, with the duty cycle, let's put it up here, with the duty cycle of 50%, right, we found that RA equals 0, and we found that RB equals 720 ohms, right? We found that RB equals 720 ohms. Yes. Okay, so RB equals 720 ohms. Now what we're trying to figure out is at 25% duty cycle, we want to know what does RA equal, and of course C equals 0.1 microfarads, and then RB equals, and C is still going to equal 0.1 microfarads because we're setting C, and that's the whole point of this. All right, okay. All right, so let's go over here. And so R equals 1440 ohms, C equals 0.1 microfarad, F equals 10 kilohertz, and then this is one equation here. Now, let's go back. What was this whole thing R again? So R equals 1440, but it also equaled, what did R equal? It equals RA plus 2 RB. Okay, so we've got this equation here and we've got this equation here. So now check this out. So now we can solve this, all right? So we know what R is. Where is it? It's 1440 ohms. So watch this. So 1440 equals RA plus 2 RB. And then let's take this, let's just write this over here so you guys can see what goes on here. And again, for those of you that are obviously mathematicians and college students, I'm sure this is boring you, so don't watch it. But other people that are just rusty, this is hopefully this is helpful. So now let's get this in the same format here. So I'm just going to subtract RB from both sides. So now I'm going to get 0 equals RA minus 2RB. All right. So now we got these two equations. We've got 1440 equals RA plus 2RB, and we've got 0 equals RA minus 2RB. All right. So let's flip these things around a little bit here, clean them up, and I'm writing at an angle at this point. So what am I doing here? RA plus 2RB equals 1440 ohms. Okay, and then we got this equation here. RA minus 2RB equals 0. All right, so this is equation 1. So this is equation 1, and this is equation 2. There are many, 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 many ways to solve these equations, right? I'm going to show you a couple simple ways. So we can do operations to these things where we can basically we can do row operations to them where we can take either equation, multiply it times a constant, and add it or subtract it to the other row until we can get rid of one of the variables and solve for it. That's one way of doing it, by a row operation kind of solution. Or we can do a substitution where we write one of these in terms, so like for example, this one right here, we could write this equation in terms of, we could say RA equals, and then we could take that value and plug it into this one, so substitution. All right, so let me kind of show you substitution. Most people can kind of do that. So RA minus 2RB equals 0, or RA equals, I'm just going to move the 2RB over here, so it's going to become positive, equals 2RB. Okay, so now RA equals 2RB. Well, I'm going to substitute RA into here. So this is going to come over here. So RA equals 2RB. So check it out. So 2RB plus, I just substituted this into there, right? 2RB plus 2RB equals 1440. So what does that tell me? Well, divide everything by 2 if I want, or add these together, whatever I want to do. So I'm just going to add these together. So this is 4RB equals 1440, or RB equals 1440 divided by 4, which is, get the calculator that's cooperating with me, 360. I should have known that. All right, 360. 360 ohms. Now, take that and plug it back in to here. So RA equals 2 times 360. So RA equals 2 times 360, which equals 720 ohms. So RA equals 720 ohms. Okay, so there's our two values. Now let's see if these things work. So let's go back and let's recompute everything, the frequency and all that. So I'll tell you, so let's get the frequency equation. So frequency equals, what is it? 1.44 over, and you know, this is why I did have this memorized. I'm memorizing it now, how these work. That's right. It's pretty easy. Once you write this a few times, you'll start to remember it. That's the frequency, and then what's the duty cycle? The duty cycle is just RB, I'm not looking, is RB over RA plus 2RB, right? I believe. Correct. So that's it right there. So now let's plug our values in and see what happens. All right, so let's start with the frequency. So 1.44 divided by RA plus 2RB times C. So let's do all that. So 1.44 divided by, and you can do this along with me. 1.44 divided by RA. What is our RA? 720. 720 plus 2 times 360 equals, and then the whole thing times that or divided by C, whichever way you want to do it, divided by 0.1x minus 6, our 0.1 microfarad, and the answer is, there you go, 10 kilohertz. So that worked, 10 kilohertz. Let me put it in scientific notation for you, 10 kilohertz. All right, so our frequency worked out, so that's good. Let's see if we got our duty cycle. So our duty cycle is RB, let's just do this one longhand, is 360 over RA, which is 720, plus 2 times RB, which is 720, again. So 360, right, divided by 1440, right? I think you can see that's 1/4, right? So 360 divided by 1440, right, is 1/4. 360 divided by 1440 equals 1/4, 25%, equals 25%. Ta-da! Okay, so that is a couple ways. So, so we had a special case when the duty cycle is 0.5, RA disappears. Then if it's not 0.5, then we have to create a system of equations. And then we have to solve that system of equations, all right? And then we get this kind of thing right here. So you can Google for solving systems of equations. You can do this with row operations like I alluded to, or substitution, which is really easy, or matrix operations, or what's called Cramer's rule, right? Cramer's rule. There's all kinds of ways to solve these equations. Anyway, the simplest that you can almost eyeball is substitution, which we did, and that's it. That's how you solve for these things. Now, let's go ahead and let's build this thing real quick. So let's build the simple one. Let's go see if we can, let's run Proteus. This is our simulator. So I will create a file called 555 something, but right now I'm just going to use another simulation because it's got a lot of nice parts in it. I can just steal them so I don't have to go hunting for them. All right, so the first thing we do, let's go 555, which, let me see, I think this one will work. Okay, so here's a 555 here. Now, the one thing is, whenever you're doing any modeling here, I'm not happy with that. Hold on. We have to be able to map it to the actual pins, and we need to make sure that it's got some labels that we understand what it is. So I think, let's do this one. Update, sure. Okay. All right. Okay, so here is a 555 timer. Okay, so watch this. And again, you're not going to be able to follow this too much if you haven't gone through these lectures, which I teach you Proteus, but I'm just going to start hooking up circuitry here. All right, so let's just add a ground here. There's our ground. All right, and then for V sub CC, we're going to just put a plus 5 volt supply. So I'm going to steal one of these guys, which I probably have a 5 volt supply here someplace. There was one. Let's steal this one. Let's steal this guy here. So I'm going to copy this and put it here. Okay, and I'm just going to call this 5 volts, and I'm just going to make it 5 volts. All right, good. And let's connect this down here. Good enough. All right. Now, what we need to do is we need to look at these pins. So let's go back to our schematic here. And for our astable or astable circuit, we've got to make sure we connect these things properly. So let's go up here. So here is, and let's see, can I do this for you guys? Get this thing to cooperate. Let's move this out of our way. And let's make it really tiny. So we have, now another thing I do is I'll put this application, these PDF viewers are just all so bad. All right, so that's good. So another thing I'll do is I'll take the bitmap, and you can actually insert bitmaps into Proteus so you can see the circuit schematics of what you got to do. Okay, so we got to hook up ground. We did that, and then output is output. So where is output? Output is called pin 3 here, Q. All right, TR is trigger. So trigger goes to threshold, all right? So that's easy enough. So the trigger goes to threshold. So 2 goes to 6. That's that wire right there. So let's get 2 to 6. Okay, that's easy enough. So we're just going to put a wire in there manually. and just put this in here like this. Give us a little bit of room here. So there's 2 to 6. Okay, 3 is going to be our output. So you know what? On our output, all I want to do is put a resistor. So what I'm going to do is I am going to grab something, an LED and a resistor. Let's see, let me just grab all that. And I'm going to put it over here. And then what I'm going to do is I'm going to just delete some of this stuff. I'm going to delete this, I'm going to delete this, I'll delete this, and I will delete this. Now we've just got a current limiting resistor and an LED, so I'll put that right about there. Okay, and let's zoom back in for you guys. And we're just going to go here and connect that. Okay, so there's our output. All right, this R is reset. So this is, if you want to reset this, this is going to be pulled low. So we're just going to constantly pull this high because we don't want it to auto reset. So just pull that high. Okay. Also, off of the power, we're going to, for good design, we're going to put a bypass capacitor. So I'm just going to go steal a capacitor here. All right, I'm going to steal a capacitor, and then I am going to rotate it, and we're going to say rotate clockwise. And I'm going, you know what? No, as a matter of fact, let's just rotate this anti-clockwise. We'll just put it right here. So that's a 0.1. So that's a good bypass capacitor for a small IC. And we're just trying to get the wire here. This stuff is, it messes with you. You gotta, you know, with these CAD programs, they're always in like different little modes and kind of a pain. Okay, so we got our bypass capacitor there. We're doing good. Let's see, what else do we need? Let's go back to our schematic here. Let's drag it over here. All right, we got our trigger. Now, between, so this is a little bit tricky here. So between the positive, the V sub CC supply, we need RA, and that's going to go to discharge. And from that same node is going to go to threshold. And from that same node is our capacitor to ground. So instead of trying to connect all this, let's just put RA, RB, and C. RA, RB, and C. Okay, so here we go. So I'm going to get a resistor. Let me get another resistor right here. Matter of fact, let me move this a little bit. Move this a little bit. Okay, so now let's take this resistor here. All right, so I'm going to call this RA, and that's going to go from power to discharge to threshold. Okay, so I am going to, let's rotate it. Rotate. Let's change its value. We'll do that later. All right, so I'm going to actually relabel this for you guys. I'm going to call it RA. All right, and this right here, I'm just going to call this R LED, and then I'm just going to call this D555 for diode 555. And then for this right here, I'm just going to call this U555. I'm just trying not to get collisions with our capacitors, okay? And I'm going to call this capacitor, I'm just going to call it bypass, we'll just call it capacitor 100. All right, because I don't want it to collide with any of these other values up here. Okay, there's RA. Let's copy that. This is how you copy things. All these programs are very quirky. All right, this is RB. Okay, and we want our capacitor, so let's go copy this capacitor, and we're just going to put it right here, and we're going to rotate it. I'm going to rotate it if it'll let me. And it's not. I'm using so many different CAD tools, I am forgetting how this one works. Okay, here we go. So we're just going to call that C. Now we're going to wire these things together. I'm going to put a wire there. I'm going to put a wire there. All right, now let's go get our schematic again. This is how you do it, folks. All right, so RA, RB, C, ground. All right, so top node of RA goes to power, then the middle node goes to discharge, and then this other node goes to threshold. That is what we're trying to mimic, okay? All right, so RA, let's go ahead and let's take a wire, and we're going to put that wire right up here to power. So there's our power node, okay? And then between RA and RB, that goes to discharge. That's this node here. Let's try and make it semi-clean, okay? And then the next node goes to threshold, so it goes right here. So we can put it right here. And this is ugly. Let me see. Why is it? You gotta get the little pen sometimes. There you go. You get the little pen, and in little pen mode, it lets you draw things Okay, that's okay. And then now let's get the ground, and let's put our ground here. And don't just put grounds on top of things. It's better to put a little bit farther away and draw the ground in. Okay. All right, looking good. Okay, so now let's see. We got, and then we have trigger here, and trigger, and we made a mistake. We made a mistake. We made a mistake. What mistake did we make? Trigger goes to threshold. Trigger goes to threshold. All right, so let me erase this. I just made a little mistake right here. Trigger goes to threshold. So trigger, oops, trigger goes to threshold, right here. Okay, so trigger goes, so pin 2 goes to pin 6. Okay, don't worry about the control pin. Now pin 5, I believe that's the control pin. I believe this is the control pin, so we shouldn't have to worry about it. I'm gonna go look at the data sheet here, and let me make sure pin 5 is the control pin up in the actual package. And pin 5, control, yeah, it's called control voltage. Let me show that to you guys. Yeah, no one ever uses this, but, well, you do, depending on what you want to do. So pin 5, where are we here? Pin 5 is the control voltage, and if you look through here, pin 5, the control voltage controls the threshold and trigger levels. It determines the pulse width of the output waveform, and external voltage applied to this pin can also be used to modulate the output waveform. We're not going to use it, so you can just kind of leave it. All right, now, okay, so we have our 555, we've got our capacitor, and the capacitor actually is set to 0.1 microfarad. Now let's set our RA and our RB. Let's go back here. So with our duty cycle that was 50%, we had RA equals 0 and RB equals 720 ohms. All right, so let's go back, and we're going to say RA. Now, if you set things to zeros in these simulators, a lot of times you might get a divide by 0 problem. So we're just going to set that to 1 ohm, and then we're going to set RB to 720 ohms. Okay, so if we look here, RA is 0, RB is 720. Okay, so let's give that a try. All right, so we got those two values. I'm just going to go ahead and save this, and we may have some trouble over here, so give me a second. And we have to go to the power rails, which are in, is it view, is it graph, is it debug, is it library? No, edit. Where is that? Where is the power rail configuration? And folks, I just installed a new there we go. I just installed a new version of Proteus, just the point version update. So I thought maybe it might have moved it. Now, I should, okay, hopefully I don't need to mess with this. Okay, let's just go run the simulation. And if all's well, this is going to oscillate at 10 kilohertz. All right, fatal error, yes. Okay, so you can see we changed the circuit a little bit. I skipped ahead here. I had to play with it. So we were having trouble with power. We were getting simulation errors. So anyway, I got the power working properly. So we have a 5 volt up here, and then now the simulation is working. So, and then the other thing I did was I went ahead and added a oscilloscope over here and tied it to the output. All right, so now everything is working. Let's go ahead and let's take a look. All right, so we have two different sets of values here. If you recall, the 25%, RA equals 720. So we'll put a 720 here, and then RB is 360. So when we want the case where we have the 25% duty cycle, we need RA is 720, RB is 360. If we want the duty cycle is 50%, then RA can equal 0, then RB equals 720. Let's start off with the 25%. I think that's what I have in here now. Yeah, so I've got 720 and 360, and then our C is 0.1. So when we run the simulation, hopefully it doesn't crash and it runs this time. All right. Now, if you look at the output here in the virtual oscilloscope, you can see that this waveform, let's see, this is this oscilloscope does not work very good at all. Once you start playing with this, you realize that, okay, I'm gonna see if I can amplify it here a bit. And if I look at, I believe it is it, no, this is the offset. This is, yeah, oh, here we go. This is the gain, and then we will open up the frequency a little bit. There we go. All right, so if you take a look at one of these waveforms, like say, for example, this one, you can see that the total time that it's low is about 25% of the total time, right? And that's exactly what we want. So it's a duty cycle of they call it 25%. It's a low to the total time. A lot of other people call duty cycle high to the total time. All right, it also can be a high to low. So it really depends on convention and who's saying what. But anyway, this is 25% of this total, so that worked. Now, let's take a look at the frequency of it. Can we measure the frequency of it? There's a frequency measuring tool here someplace, but we can just do it with the oscilloscope. We can try to, if it doesn't drive me crazy first. All right, so let's see here. If we go, that's 1 microsecond, and these are milliseconds. Yeah, these are milliseconds. Okay, so that's 50, yeah, 50 microseconds, 20 microseconds, 10 microseconds. All right, so that's 10 microseconds per division. So if we take a look at the waveform here, and then again, every time I play with this thing, I've got to remember where everything is. I want to change the position. There we go. So let's go ahead and we will take the position. Oh, whoa, 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 whoa. What are you doing? Yeah, all right. So right here, I've lined it up. All right, so if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, roughly 10. So the entire thing is 10 divisions, and every division is 10 microseconds. Okay, so we take 10 microseconds times 10, right? That's the total time. And then we we take that and we invert that. Then we get this. Oops. Take that and we invert that. Thank you. And if you look, we'll get 10, there it is, our 10 kilohertz, right? So that is correct. So the frequency is correct. We're getting 10 kilohertz. We're getting the exact duty cycle we should get. All right, so all is good. Now let's try the other case. And you know, and if you've taken the course and you're just watching a bonus lecture, you know that this is how this stuff goes. Nothing works right, and there's always drama. You got to figure it out. So what's our other case? So RA equals 0 and RB equals 720 ohms. All right. So let's go and set that. So RA equals 0 and RB has to equal 720 ohms. So let's see what happens. So we should get a 50-50 duty cycle and still 10 kilohertz, right? That's what we're expecting. So we hit run. All right. And now we've got this. Now notice we have no waveform out of here. Okay. So now one of a few things are happening. The simulator is breaking, all right, because of this 0 here, or the model is breaking because it's actually accurate. Now, when you put this 0 resistor right here, now here's the thing, there's a 0 resistor right here. So basically we've just got RB inside of the circuit. Now, I'd have to look at the data sheet, and to be honest with you, 20 years ago I used 555s a lot, but you know, in modern electronics you don't use 555 timers that much. If we read through the data sheet, we might, and look at the design. So if we go through the data sheet, where'd the data sheet go? If we go through the data sheet, and these are the kinds of things that you got to do. Here it is here. And if we look at the design of the chip internally, how this thing is actually working, right? Let's see, here it is here. And let me shrink this out a little bit. So if we look at the actual design here, and then we put those resistors, and we've got discharge and this and that, and how this thing actually works, we might figure out that RA cannot be 0. And in fact, the duty cycle may never be able to be 50% exactly, right? And I think that actually may be true. I can't remember. But it's either the simulation is not able to handle this, or that might be a fact that maybe can be 51%, but it can't be 50 because you get this 0 for this one resistor. Okay, so let's go ahead and just for a minute, let's fudge it. All right, so let's go ahead and let's make this, say, 10 ohms. All right, 10 ohms. Will this work? Let's see if 10 ohms works. All right, still doesn't look like it's working. All right, So remember, whatever we add here, we got to subtract here, kind of, right? We got to be careful with this because we want the total resistance still has to be 1440 ohms if we want to maintain that 10 kilohertz, right? So check this out. So let's just jump this up to 100 ohms. So we jump that up to 100 ohms, and it's going to be 100 plus 2 times this, remember? So this gets us our 1440 plus 100. So really we need to lower this down. So we need to lower it down so that 2 times it plus the 100 is 1440. So if we were to subtract 50 from it, I believe, is that what we want to do? If we make this 670, right? So if we do 670, 670 times 2 plus 100, that gets us back to our 1440. Okay, so we know the frequency will at least be right, but we know our duty cycle is going to be a little tweaked. All right, so let's go ahead and let's try and run that. And there we go. So it's almost 50%. You see that? It's almost 50%, but not quite. Now let's see, can we make this a little bit lower? What happens if we make this 50 ohms? Will it work? And yeah, it's working. It's working. All right, but since we made that 50 ohms, we have to increase this a little bit. And again, so we basically need about 700 ohms here. So 700 times 2 is 1440, excuse me, is 1400 plus 50 is 1450. It's almost the 1440 perfectly that we would get our 50-50 duty cycle. So that's working. So the bottom line, we need a little bit of resistance here, and we could probably find the threshold here, but we'd have to try it on the actual hardware. So the rule of thumb is here, you got to be careful. We don't want this resistor to be absolutely zero. That's all. So, and by the same token, if you look at the modeling equations down here, do we create any kind of singularities or any issues with the modeling equations? So you see in this modeling equation here, you've got RB over 2RB. So if RA goes near zero, then you just get basically 1/2, all right? But also as RB becomes very large, RB divided by 2RB, and if RA is small compared to RB, then RA starts to go away. So the point is, if you want a 50-50 duty cycle, what we can do is we can make RA small compared to RB, and that'll also achieve it, and then we can tune the RB value so that we get the frequency. So we just want it to be small. So you can get near to 50%, but I don't think you can actually get exactly 50% because to do that you'd have to make RA equal to 0. I think the electronics, the design with the threshold, the comparator, and so forth of the actual 555 design, I don't think it tolerates that. So anyway, so that's it. So we basically did those 2 experiments. We did the math. We solved for RA and RB with a 25 and 50% duty cycle. We learned the trick that you have to set one of these variables. So just pick C usually, because that's something you can grab and buy, and then solve for RA and RB based on the duty cycle that you want. Then plug them in, run a simulation, and then we figured out that, hey, 0 just doesn't seem to work, so we got to raise this RA a little bit, compensate by changing RB a little bit, and then go ahead and go on your bench and actually build the thing. All right? That's what you want to do. So anyway, hopefully that helped a little bit, or I completely confused you, but I wanted to kind of show you what the process is to look at the modeling equations for various timing chips, and then if you have too many variables, what do you do with it? Well, you have to fix one, and how do you do that? You pick a common sense value or a sane value for the capacitance or the resistance or whatever, and then solve for the rest, okay? And that's what you want to do. And again, you can do the same thing. We could, say if we wanted a frequency of a megahertz, we could pick one of the R values that we want, and we could also pick one of the C value, and then we could try and solve for RB and see if we can get a solution. We may not be able to get a sane solution. It may not work out because of the way we pick them, but we can try. So if we get a valid solution, we might get a number that is nonsense. So anyway, typically with 555s, my advice is pick a C value, and then go and compute the two R values, RA and RB, based on the duty cycle that you want and the frequency that you want, and pick different C values, pick very small C values, 0.1, 0.01 microfarad for high frequencies, and then go to 1 farad, 1 microfarad, 10 microfarad, 100 microfarad as you start to go into tens, hundreds, or just down to hertz. You're going to want a big capacitor. All right, so that's it, and I hope you got something out of this lecture. Next time we will definitely do the programmable logic one. I will get that thing to work and on the next bonus lecture. All right, so I'll see you guys then. Bye. Hey everybody, I've been getting a few questions about grounding in circuits and ground. Some people seem to have a bit of confusion on what ground means and what the symbol means, what 0 volts mean. Now, the problem with talking about ground is the word ground really comes from more like AC power systems. It's a very old word, and it has to do specifically with uh, kind of the AC, the 110, the 120, or the 220 that's powering your house wherever you are. So that word kind of came from there, and it has to do with physically grounding things to ground. Um, so I don't want to get too much into that part of it, AC power, because it's kind of a large discussion. However, what I'm going to do is I'm going to talk about it a little bit, and I went through YouTube trying to find some good videos that have some visualizations that I think will really help people that are struggling with this concept of ground. Now remember, for what we're doing, we don't really care about AC ground. We don't care about things plugged in to sockets. We don't care about grounds exterior to the house. We don't care about lightning strikes. We're talking about electronics. And in electronics, we're talking about a ground, which is a notational kind of tool, which doesn't necessarily have anything to do with ground when we're talking about AC power systems. Anyway, to try and clarify this for the people that are having some trouble, I went through and I found there's a lot of good videos. If you Google, or excuse me, YouTube search for electrical grounding and why it's important, you'll come up with a bunch of different videos. The one that I found that's kind of the shortest and the most accurate and has some really good imagery and video is this one. It's from rimstar.org, and it's what is ground, question mark, earth ground / earthing. So this is actually a really good video. It's 10 minutes, and I would like everybody who's watching this video to watch this. You can watch it now, or you can watch it after we do our little video. And then I'll put a link. The link is here. It's lowercase z and then uppercase LW _ 7 T as in Tom, P as in Peter, then lowercase f310. Anyway, I'll put that link inside of this lecture. So watch this video. This will really help. All right, so let's talk about ground as far as electronics is concerned, and then we'll kind of go off and talk about it in AC systems. When I do some of the power electronics experiments in the course, I'm going to talk about this, what neutral is, what ground is, what hot is, and so forth. But again, this is just kind of a quick and dirty video to help some of those students that are just having trouble. They're making this way too hard. They're making ground way too hard. As far as we're concerned, this is really, really easy. So let's just start drawing some circuits here and see what the situation is. All right. So the first thing is, let's just say that we have the simplest circuit you can imagine, all right? So let's go here, and I'm just going to draw a battery, all right? And that's the symbol for a battery, right? Okay, and we're going to go and we're going to have a resistor, and then let's go down here and we're going to have an LED, all right? I'll put a little circle around this, LED, and we'll put arrows out of it. And again, you could just be watching this video out of order randomly, and because you're just interested in ground, and it's confusing you as well. So here's right here. Now let's say that this is, we'll just say that this is a 9-volt battery. So it's a 9-volt transistor battery, one of those rectangular prismatic cells, all right? And of course this is plus, and this is minus. All right, so what's going to happen in this circuit? When we connect this circuit up, we're going to get a current flow. All right, the current is going to flow this way, right? We're going to get a voltage drop over this resistor. I'm going to call that plus minus V1. All right, and then we can start labeling nodes if we like. All right, and I'm going to label this node, I'm going to label that A, and I'm going to label that B, and I'm going to label that C. All right, and we're also going to get a voltage drop over this diode here, right? I'm going to call that plus to minus, and I'm going to call that V2. All right, so this is our circuit here. All right, so let's write down some equations here. So first thing is the sum of the voltage drops in this complete loop better equal the source voltage, right? So V1 plus V2 must equal 9 volts. All right, fair enough. And the current in the circuit, let's call that I. All right, so the current in the circuit, where's Ohm's law? Let's write that down. So V always equals I times R. So voltage equals current times resistance, right? All right, so whatever the total resistance of the circuit is, right, this R here, that's going to give us our I. So we're going to get I equals V, and I'm just rearranging V over R, all right? Okay, so let's take a look over here. So if we want I, we're going to say I equals V, which is 9 volts, over R. But R is a bit of a problem. I don't really know what R is because I know what this R is. Say that this right here is, let's say that this is, let's use a different color. Maybe this is 200, that's not bright enough. Let's use this one. Maybe this is 220 ohms. All right, that R is 220 ohms, but this diode, all right, this diode right here, we don't know what its resistance is, all right, because this is a semiconductor device. So we got a little bit of a problem in this circuit trying to figure out what's going to go on here. But what we can do is we can kind of backtrack, all right. Now again, we're getting to the grounding part here, but you know, since we drew this circuit, we're going to have to kind of figure it out. So let's say that this light emitting diode, when it's forward biased, let's say that this thing drops 3 volts, all right? So when it's forward biased, it always drops roughly 3 volts, and then it's on. Now you can push more current through it if you want, and the voltage will change slightly, but for all intent purposes, it's 3 volts. So this is 3 volts right here, so then that means that we must have the other 6 volts over this resistor. 6 plus 3 equals 9. Okay, now we can kind of pin down what the current is. Well, I know that this resistor right here is 220 ohms, right? And then we've got this 6 volts here. So I must equal, we have another I that we can figure out. So we can say I equals, instead of this 9 volts over R, which would be kind of R total, we can say it equals this 6 volts over this 220 ohms here. All right. And if we get our calculator out, 6 volts, 6 divided by 220 is going to give us 27 milliamps. All right, 27 milliamps. Okay, so at 27 milliamps through the circuit, that's going to cause a 3 volt drop over this light emitting diode. And that's kind of in the ballpark, so this is okay. Now remember, with semiconductor circuits, you have to kind of iteratively calculate things, but we're going to leave this as is right now. So 27 milliamps. Okay. So now we have this circuit here, and I just went through this analysis just in case you have never done any circuit analysis. You can kind of see the process. Now, that's all great. So we have these nodes, A, B, and C. So at node A, right, I've got this 9 volt battery, but relative to what? 9 volt relative to what? Well, to the other end of the battery, all right? So here's one end of the battery, there's the other end. So if we were to take a meter and say a multimeter over here, and say this is a digital multimeter, right? And it's got a little movement, or it's a completely digital. All right, so we'll call this digital voltmeter, DVM. All right, and then we take its 2 little wires and say that this is plus and this is minus, and we run this up here to node A, and I run this down here to the bottom part of the battery, the other side, the negative side. Okay, if we were to do that, that would read 9 volts. We would read 9 volts on our DVM. All right, now what if we want to try something else here? what if I want to read what's the voltage over this resistor? Well, we put our positive here, and then we could take and run this other one over here, and we should read the 6 volts here, right? We should read that 6 volts. So from this node here to this node here, AB, we should have 6 volts. So we could say VAB equals 6 volts. All right, fine. Now, what if we were to go ahead and leave this probe here, but what if we were to go over here to C? All right, and I would go over here and go to C. There's always a Microsoft update, isn't there? All right, so if we were to go over to C, well, wait a minute. This whole node is a piece of wire, right? It's a piece of wire, isn't it? So this should all be at the same potential, right? It's just wire. So no matter what, anything along here is equivalent to the negative part of the battery. So again, I should read, if I put this here, I'm going to read 9 volts out of this because we have one lead of the meter going to the positive and we have the other lead going to negative, right? So we're going to read 9 volts here. All right, so now this is where people are getting confused. So now when we're doing all these tests, we're going from node A, node B, node C, right? But this node here, which is connected to the negative part of the battery, this is all the same node. And, you know, this, I want to call this ground, all right? And I want to say that this is at 0 volts. So this is completely a convention. I'm going to say this is at 0 volts. I'm going to say this is ground of the system. Now, this has nothing to do with ground connected to AC, connected to your house, connected to neutral, connected to earth ground. It has nothing to do with that yet. This is just ground in the circuit. And this is a reference. This is notational. So this means this is a common point. So why is that important? Well, it's important because of this. Now let me show you why and how this works. So now say that we draw another circuit over here. Okay? And now say that in this circuit, we're going to make this simpler. We have 2 resistors. This is plus, this is minus, this is a 5 volt voltage source, whatever that is. We have R1, we have R2, and for kicks, if you want to give these some values, this could be 100 ohms and this could be 200 ohms. All right, matter of fact, let's make it easy for the math. We'll make that 400 ohms. All right, so if I wanted to figure out I is going to flow through the circuit from positive, negative in this direction, so I is going to equal what? 5 volts over the total resistance, which is R1 plus R2, which is 500 ohms, right? So 5 volts divided by 500 ohms, we take our calculator, 5 divided by 500, right? And we're going to get 10 milliamperes, right? 10 milliamperes, okay? So that's it. So, great. Now, I want to relate one circuit to another. So let's say I've got these 2 circuits and I've built them on 2 different boards. I take my meter, right? And I want to connect the meter to measure 2 different things here. So I connect the meter here, let's say. All right. And what does the meter do? Absolutely nothing. All right. The circuits are not connected. There's no reference to either of them. There's no common reference. There's no common way for charge to get back to the battery or to the batteries. We need to create a common point. All right, so ground is like a common. So now what I'm going to do here is I'm going to say that this is ground. This node is ground, just like this node is ground, which is the same as this node and this node and this node and this node, right? Because this is all a piece of wire, and the piece of wire is one node. All right, so that's one node right there, and I want to make this clear also. And again, in the lectures we do this ad nauseum, but I want to make sure everyone gets this. And where's another node? Here's another node right here, right there. All of this wire, and then all of this. So whenever you have a wire, it could be 1 billion miles long. As far as we're concerned, it's all one point. So there's only 3 points in this circuit. 1, 2, 3. A, B, and C. C happens to be also what we're going to call ground, which is also common, which is also what we're going to call 0 volts. Now, when we write this symbol here, this means I want you to connect these things together. So when you see all these little grounds, that means all of them are connected together. So now this is electrically connected to that. Let's draw that a little bit better. So we'll come out here, and it's like that. So these are electrically connected together. So now that they're electrically connected together, now when we put this meter on things, we can read different voltages. So check this out. So I've got the positive of the meter here at this node A. All right. Now let's go ahead and let's take the negative, and if we put it here, right there, on this node, well, that's the same as putting it right here, right? So what are we going to read? Well, what's the potential difference between these 2 points? There is no potential difference. There is a short right here. So this point and this point are at the exact same potential, all right, which we're going to call 0 volts. So when we look at our meter, right now, we better get 9 volts out of it because we've got a 9-volt battery. Now here's where it gets fun. Now, if we were to go ahead and we were to break, let me see here, let me make sure, yeah. If we were to break this one here, all right, and we were to connect, and we'll just make this blue, the positive someplace else. So now we've got the negative to ground. So now we've got negative always to ground. So now we're looking at voltages relative to ground. So check this out. So if I go up here and put it there, I get 9 volts, right? What if I put it here? If I go all the way over here and I put it here, what am I going to get? Well, I'm going to get 5 volts because here is one reference connected here, which is connected here, which is connected back here. So that common ground, common, and the important word is common. It's your common. But we call it ground, your common ground, your reference. They're connected together. So now when I read this here, I get 5 volts. So I've got 2 different power supplies, 9 volt and 5 volt. I can read them both with a meter. Now, where are the currents in the circuit going? All right. Well, we've got one current going in this circuit right here, right? It's going like this. We've got another current going here, but neither of these currents make their way into either circuit. Because there's no closed path. There's a common ground, so this and this are connected together, so they're going to be at the same potential, but we don't need current to flow from one circuit to another. Now, if I were to take, let's say that from this node here, I took a wire, and then I put a resistor, then I connected it, say, to this node. Now we've got some funky circuitry going. We've got 2 different voltages, right? We've got resistors, and we do have a path now, so current can flow through this whole thing. But we don't have that. All we have is common ground here. So I can move this meter anywhere I want. Let's move it here. Can take our meter, and let's go measure what the voltage is there, right? I can take my meter, and I can measure what the voltage is here. What's the voltage here? So negative is at this point here, which this node is all the same, which is connected here, which is connected here, because remember, this is all one wire, right? Wire is the same node, so this node is all the same node. So we've got positive here, we've got negative there. Well, I'm just reading a piece of wire, so the potential difference is 0. There is no potential difference because it's a conductor, zero resistance conductor. Now, in reality, obviously, a piece of wire has some resistance. So if you were to measure the voltage across a long piece of wire, you'd actually find microvolts or millivolts or nanovolts, but for our purposes, it's 0 volts. Okay, so let's move that wire. Let's move that test. So now let's actually try and compute something. Now, so here's the deal. We can put the meter on the ground, or we can put it differentially over things, right? So say if I put it differentially, again, we can just erase this. And then we go here, and, you know, I always struggle with colors. I want to make them different enough. But so we can always take our meter and measure 2 points. So I can go all the way over here, for example, and measure this point, and come up here and measure this point. That's going to tell us the voltage drop over this resistor, right? And we know there's 10 milliamps, so 10 milliamps times the 100 volts, right? That would give us 1 volt, right? So if we take 10 milliamps times 100 ohms, that gives us 1 volt, right? If we were to measure that, that should be 1 volt. And of course, if 1 volt drops there and we've got a 5 volt supply, 4 volts had better drop over this resistor, right? Plus to minus. But that's what our meter will do. But now it's not relative to ground. It's just 1 volt differentially, right? Now, if we erase these 2 connectors and we take our plus again and we say put it right here. And then we take our minus and say we put it right here. Now we're going to read the voltage drop over R2, which is going to be 4 volts, but negative happens to also be at ground. So it's 4 volts relative to ground as well, and it's 4 volts just differentially, all right? Now, can we do anything else funky here? Can we do something else interesting? Well, let's see. What would happen if I put one end of the meter here, okay? One end of the meter is there. And what if I put, let's see here, what if I put another end of the meter here? All right, so let's see what happens here. So we got one end of the meter here, and that relative to ground is at 9 volts. So right here, this is 0. Here's our 0 point right here. Then we've got the other end of the meter here at this plus 5 volts. So now what's going to happen here is we're going to get a voltage differential, but what's the voltage differential? So let's think about this. If this is 0 volts right here, so this point is 0 volts. So here's our 0 volt right here. So now here's 0. So one of our meter probes, the negative one, is at positive 5, right? But then the positive probe is at positive 9, all right? So what's going to happen is we're going to get a difference here, all right? So if you could think of it this way, we start off at 9 volts, right? We drop down to 0, and then we go up by 5 volts. All right, so when we read this right here, we should get a positive 4 volts from these 2 points because they've got this common ground here. So the point is that when you're measuring things, the whole point of having ground is to connect circuits together so that they have a common reference. That's the point of ground, a common reference, all right? And again, if we were to draw yet another circuit, we come over here, and let's say that we have some signals coming in from a digital system. All right, so that is the worst square wave on Earth. So say we have an electrical signal, some square waves coming in from a general purpose I/O pin from, say, a microcontroller processing unit MPU, right? Well, we got this one signal, and here it is. And I want to do something with it in the rest of my circuit. I can't just connect that to things. I need to have a ground. So coming from that circuit, from that Arduino or whatever, that ground, which is going to be its negative ground, okay, I need to take that ground and tie it, let's use red here, and I'm going to tie it to this circuit. So it needs to be tied there. Or we just have the symbol here, right? We say ground. So that means I want you to tie all the grounds together. That's what that means. So these things are all tied together, all right? So that all circuits have a common reference for voltages. And that ground is always at 0 volts. Now, let's take a look at something else here. Now, what if, I'm not going to be able to erase it. Let's go ahead and just erase some. Let's give ourselves some space here. I want you to take a look at this. So here's something else that is confusing people. All right, move this over here. Good enough. Okay, let's say this. Say that we have a battery here. Oop. Say that we have a battery here. Okay, there's one. Okay, and then say we've got this node here, and then say that we have another battery here. Okay, like this. All right, and now say we have a resistor here, and I can have another resistor here. All right, now let's draw these in a different color and make them pretty. This is plus and minus, right? This is, say, 9 volts, and let's say that this is a 6-volt battery. Again, it's plus and minus. Now, and let's go here and let's call this R1, R2, and we're going to get voltage drops plus to minus like this. Okay, now let's slow down here and take a look at what's going on here. So I've got 2 batteries, I've got 2 resistors, I've got a closed circuit, I'm going to get a current flow. The question is, where is the current going to flow? What's it going to look like? Where is ground? And so forth. First, where is ground? Let's talk about that. It's wherever you want it to be. Ground is a convention. It is a reference, and typically it's the most convenient reference that you're going to reference in your circuit so that your circuit makes sense to you and what you're trying to do. So for example, we could put ground here and call this ground. Now, there's no connection to anything yet. In one circuit, this is just a reference. It's just a notation. This is what I'm going to call ground. I'm going to call this 0 volts, period. 0 volts. So now if this is 0 volts right here, so again, and again, if you've taken more of the course, then you understand this nodal mesh drawing stuff. But all this is a wire, so this is one node, and it's all the same node, it's all the same potential. It is at 0 volts, I say. So it's at 0 volts. So if that's at 0 volts, then what is it right here? What's this going to be? Well, we're going to go up. There's a voltage source, 6 volts. So this better be 6 volts. It's 6 volts. Now I'm right here. So now I've got another battery. I've got the minus of the battery connected to this node right here. All right, so now it has to go up again. So what's this going to be right here? It's going to have to be the sum of these two things, 15 volts, right here. So from this point down here, if you were to take our multimeter and connect it from this node down here to this node up here, you better get 15 volts. Okay, so there's 15 volts in this circuit. So then if we were to take 15 volts divided by the sum of R1 plus R2, we could compute the current in the circuit, and obviously the current goes like that. But what if I don't want to call that ground? What if I want to do something different? Well, I can do anything I want because I'm designing the circuit, right? What if, do we have enough undos? Yeah. What if I want to call this ground? What if I want to call this ground? All right. So now this is a completely different kind of thing. So now here's the interesting part. This is just a convention. So now don't think this is going to change the operation of the circuit. It is not. So again, what's the total voltage in the circuit? As far as these resistors are concerned, from this node right here, this bottom node, right? From this bottom node to this top node is still 15 volts. 6 volts and 9 volts are going to add up. You're going to have 15 volts over these two. You're going to get your current, right? That's going to tell you your current. But relative to this point right here, which I am calling ground, okay, relative to that point, if you start taking the meter, and let's say that we take the meter minus, let's say we take the minus, oops, and we connect the minus of the meter. So here's our digital multimeter again, all right, and here's the minus lead, and then here's the plus lead, okay, our little meter, DVM, oops. Okay, we've got our DVM right there. We put our minus there, so that's what I'm calling 0. That's what I'm calling ground. That's up to me. Now if I take this positive and I put it here, what do I get? I get 9 volts, right? I have to. The meter is over this 9 volts. I get 9 volts. That's all there is to it. All right? Positive 9 volts. The meter will show a positive 9 volts. But what if I take this and put it here? Now let's be super careful. So I've got the negative here. I've got the positive here. So it's going to be 6 volts, but what kind of 6 volts? It's a negative 6 volts because I'm relative to this point right here. I've used that as ground, so I hooked it to the negative of my meter. So when the meter reads it, it's going to read it as a negative 6 volts because from the meter's point of view, look at the plus. The plus is on minus, the minus is on plus, right? So I'm going to get a minus 6 volts there when I read that. So I'm going to get a minus 6 volts. So what does that mean? From this point right here, relative to this point here and this point here, I call this 0 volts. I just make this up because I feel like it. I want to call this 0 volts. So what's this up here? That's 9 volts. What's this down here? It's minus 6 volts. So I've got 9 volts and minus 6 volts. As long as I use this convention that this is ground and this is the common point of my circuit, I will have a minus 6 here and I will have a positive 9 up here. Now, here's where things get interesting. Here's one circuit and here's my ground. Right there is my ground. Can I take that ground and connect it over here? Sure. So here's this guy's ground, which I'm calling his ground right there. And I'm going to go connect these grounds together. And again, this point and this point and this point and this point and this point are all the same point, right? Because this is a piece of wire. So it's a conductor, so it is a surface, right? And you know I like talking about things in an abstract way sometimes. These are all these closed surfaces, right? And here's one more surface. So there's 1, 2, 3, 4 nodes in this circuit, right? That's it. I don't care if these wires are a billion miles long, there's only 4 nodes. Anyway, so I connect, here's ground, and the electrical engineer, the designer says, hey, I want all grounds connected, so connect this ground to this ground, and you do it. Will the circuits both work? Yes. Will they both do exactly what you think they're going to do? Yes. There's just a wire connecting one to the other. Now, since there's a wire connecting one to the other, they have common grounds. Now I can take my meter, right, and I can connect it to things. All right, so let's keep our ground to ground here. All right, and we'll use blue. So now if I take my meter and I put it up here, I better get 9 volts. I'll get 9 volts. If I take my meter and I go down here, what am I going to get? I'm going to get minus 6 volts relative to this. Okay, minus 6 volts relative to that. All right. Now, if I take my meter and put it up here, all right, so now what's going to happen? So here's this ground point right here. All right, we've got the, oh, I made a mistake. Oops, I made a mistake. I didn't mean, this was not our ground. This is our ground right here. So let's connect that back here. So here is our ground right here. Okay, so now, and let's erase this one. It does get messy when we're doing this, of course, obviously. All right, let's do that again. Okay, so here's where my meter's connected to this common point here. And I take that point and I connect it over here. That's what the ground means. It means common point. I want these points tied together. Okay, so if here's 0, what I'm calling 0 volts right here, right? I take my meter and I touch it up there. What do I get? I get 9 volts. It's fair enough, right? Then I take my meter and I touch it up here. What do I get? 5 volts. I have to get 5 volts because this point and this point are tied together. So basically I've just got 2 batteries coming off this common connection, so I will get 5 volts right here, all right, when I connect it to the meter. The only reason I can get the 5 volts is because the circuits are connected together. If I were to break this ground, this is not going to work anymore. So the whole point of the story is grounds tie everything together, all right? They're a common reference, and when you're talking about digital and analog circuitry, we're talking about we want these things all to be connected. So wherever you see grounds, I want them to be connected. Then, again, there's some more advanced things like when we talk about analog ground and digital ground in a circuit, and I've talked about this in lectures. I don't want to go too much into it right now, but when we have a bunch of digital electronics, we may take all the, so like for example, let me erase some of this. So we're talking about noise a lot of times and currents and things of that nature when we're doing circuits, and we want to isolate things. So say we have, here's all of our digital electronics, and in our digital electronics is a bunch of ICs, all kinds of stuff, right? And all of them have ground connections. So we take all those ground connections and we tie them all together, right? They're all together. Now there's my digital ground right there. So there's my D ground. Now over here, let's say that we have all of our analog electronics, right? We got all our analog electronics, right? We got filters and amplifiers and all kinds of stuff, and we tie all their grounds together, right? Okay, there it is right there. There's my A ground. Now I need these two to be connected together. So I could have just connected them together here like in a big mess, right? But instead, I connect them only at one point here with a big fat conductor or plane or something like that, but they're only at one point, they're all connected. All right, and then both of these can be connected to, say, the power system ground, right, which would be a general ground. But the point is now here's digital, here's ground. It's the same as analog ground, so we can reference voltages to each other. We can send signals back and forth if we need to, but now if there's noise from the digital system or the analog system, it's going to have a really hard time going through this one little wire, right? If it's got a bunch of wires, all kinds of noise can happen and all kinds of other bad things, ground loops and things of that nature. But we just have one ground tied together. So that's another part. We might have digital grounds, analog grounds, system grounds, and again, all of them will have these kind of symbols. You'll see these symbols. You'll see these symbols coming off here, right? These symbols coming off here, little ground symbols. That means they're all tied together. But then, furthermore, In a more advanced system, the designer may say, wait a minute, I don't want you just tying any digital to any analog. I want all the digitals connected together on one layer of the PCB, something like that. Then on another area of the PCB, I want all the analogs connected together. Then I want one single channel from analog to digital connected together, ground. Then I want that ground connected to power ground. That way, so that noise is minimized and other things that that designer may be interested in doing. Okay, now, I don't want to take too much longer here, but let's talk briefly, because I want you to watch that video, and that video is going to do way better than I'm going to do without doing a bunch of graphics, because it's a very visual thing trying to show this whole AC stuff. So all I want to talk about is I'm going to kind of paraphrase what's in the video that I want you to watch that we looked at. So when we have our wall socket, all right, and I'm going to try and draw this, and I'd have to look at one. Let me see here on the left. Yeah. So, I'm here obviously in the United States, North America, okay? And our sockets are 110 volts. All right, now, so here's the deal. This line right here, okay, this is hot. All right, that's hot. This one right here is neutral, usually larger blade, but not necessarily. It can be incorrect. And then the final one is ground. All right, ground. Now, so where is power flowing from? Well, power is flowing through hot and neutral here. All right, and so if we go look at what exactly is going on here, right? We go to say our panel in the garage kind of thing. So here's our panel in the garage, our breaker in the garage. All right, so we've got these hot lines, and these hots are going to one side of the panel here, and then we've got these neutrals, all right, and these neutrals are going to this other side of the panel here, all right. There's like a bus bar here, all right, and we've got all these different hot connections. Then we've got this ground connection, and this ground connection also goes to this panel, and it goes to the metal. It connects to the metal of the panel, all right. Then ultimately, this hot and this neutral, these go out to your transformer and to your service. Okay, these are going to go out to your transformer and to your service. Now, so this is what this looks like, and then you can have obviously multiple connections for each one of these hots. So power, electricity, is flowing through this hot and through this neutral, back and forth, back and forth, back and forth, right? Then we have this ground. This is different. So what's the story here? All right, a quick story, because that video is going to do much better. The graphics are going to show you much better. So the ground, the whole point of the ground is this, is at this breaker box, we've got this metal connected to this ground also. And then neutral is connected here as well. So these are electrically connected together, all right? Then this literally goes down into the ground, all right? So someplace there's going to be, from the breaker, there's a ground connection. This literally goes into the ground, into the dirt, down into the earth. So this is why this is called earth ground. All right, earthing or grounding. It goes down there, and it may be a copper pole that's 5, 10, 15 feet long. And I'm not an electrician, so I don't know what the code is in this area. Or it might be a water pipe that goes down into the ground to get a good ground. But this is connected electrically to the ground. The ground, the earth, right? The earth is fairly neutrally charged, right? So red and blue, positive and negative charges. And it's massive, it's gigantic. So this thing is neutrally charged. So this is a big sponge. This can give charge, it can take charge. That's the point of that. Now, a lot of this stuff is very old where this came from. So you plug things in, right? So we got power coming in hot. We've got neutral, which is connected electrically to ground, right? And then we say, well, what is this ground? What's this helping? So it helps in a couple different things here. So one is whenever we have any kind of appliance, and so we have some appliance here, and there's our appliance, and we plug our appliance in. So we got our hot coming into our appliance, we got our neutral coming into our appliance, okay, and we get our ground, all right, coming into our appliance. Now, what we do is the ground is connected to the metal chassis of your appliance, of your TV set, of your washer machine, of your microwave, of your refrigerator, whatever. All of these household appliances, forget about digital electronics, forget about modern stuff. We're talking about early 1900s, right? All of these kind of things that were powered with electricity. So you've got this hot AC coming in here, right? What happened if this hot line were to touch the metal case, because everything's made out of metal? What if it were to somehow touch this metal case, right? Then this metal case would become energized with hot, and if you were to touch it, you would die. So by grounding the metal case, if that ever were to happen, if the hot were to ever touch the metal case, it will create a short from here to here. There will be a short, a huge amount of current. That huge amount of current will go through here, go through the transformer, come back through here, and break the breaker open. The breaker will pop open. So it's a safety feature, okay? It's a safety feature. And again, we like everything relative to something. So we have a ground here. Over at the transformer, up on the poles, there's also another ground. And the other reason we want something at ground relative to what we're standing on is because otherwise things could start floating. So if we have this neutral and we have this hot and we don't have a ground, well, we know that hot is hot relative to something, but neutral could be also relative to the ground that we're on. As the ground became charged or a different potential, this could also have a voltage relative to what we're standing on. So we get shocked from that too. So the whole point is we want one common voltage that's a return path or a reference that everything else is connected to, so that we have a potential difference from ground, which we call 0, to whatever our AC system has, 110, 220, whatever, so that we have that voltage differential. And then we also have a way to connect and touch anything metal. So anyway, this is a long series of lectures on electrical safety and what happens during lightning strikes, what happens when there's charge offsets, what happens when things become charged. So anyway, having this ground and having this earth ground going into the earth is very important for electrical safety. That's where the word ground came from, and it's caused a lot of trouble with electronics and modern electronics because people think it has something to do with the ground. It doesn't. It only has to do with the ground when we're talking about power systems and AC systems. When we're talking about ground, it's just a word. It just means common reference. That doesn't mean that when you design something, you might have an input to the power to the system where you show a ground and you actually mean, I want this connected to this ground for safety because I'm going to connect that to the chassis of my device. So I have a chassis ground and I need that because I want it protected. So you want the chassis of your device actually grounded so that if something does short, it'll short against the chassis and blow the breaker and it won't hurt the user. Okay, so hopefully that didn't confuse you and that helped a little bit. I think having the different circuits kind of helps clarify the whole idea of different grounds, and to be able to make measurements or to have currents flow, we have to have a common electrical point between them to reference them. But that's all ground is. Don't get confused, just a word, and everything is relative to everything else. We can call anything we want ground. Again, to make one last obvious reference here, again, let's say we have a battery. I'm going to take a battery here, okay? I'm going to put it through 2 resistors, 1, 2. It's going to be a 12-volt battery. It's going to be 12 volt plus to minus. Then I say, where do you want ground? Well, the most common place to put it would be right there, right? But I could put ground right here, up here. I could call that ground, right? I could call that ground. Right? I'm just drawing it sideways. You can draw it anyway. I could call that ground if I want. So if that was ground, that's my 0. So if that's my 0, and if this is a 12 volt differential, well, if that's 0, that must be down here minus 12 volts. See? It's minus 12 volts. Right? So everything is relative to everything else. It's relative. Voltages are relative to a reference. Always relative to a reference, and I can call the reference anything I want. Where's another place I could put the ground? No one says I can't put it right here. I could put the ground right here. I could call this ground and then tie this to grounds of other pieces of the circuit. Now, that's not a good ground because that's going to change as this current changes. It's going to go up and it's going to go down. So we like grounds to stay at the same potential. We want them to be stable, all right? But I could make that ground as well. It would just be a funky ground, right? Then what would happen is up here I would have like plus some voltage, and over here I would have minus some voltage, right? But those are the kinds of things that you might want or need to do, all right? So I think that's it. We've got enough time. Before I go, I wanted to show you, oh yeah, I think in the last email, if you read it, let's see here if you can see this. So this is that Raptor power supply. So these are the first prototypes of it, of the finished design. So this is in one of the bonus lectures. We actually designed a variant of this. This is a more advanced version. And then what's cool about it, let me turn it on here. Is it turning on? Yep. So it's 5 volts, 3.3 volts. It's got external, you've got an external input, and you've also got USB, right? And it's got a lithium-ion battery, so it has lithium-ion battery charging, USB power, external wall wart power, and 3.3 and 5 volt regulated supplies. And with on the 5 volt, it's a boost buck converter. So if the voltage on the USB drops below 5 volts, which it's always below 5 volts, then you'll always get your 5 volt, and you can pull half an amp to an amp out of it. And then it's also got a couple cool little ties there. So anyway, I just want to show you that. So that's pretty cool. This is like the world's best solderless breadboard power supply. So like I said, at some point I'm going to do a Kickstarter or something like that on this, and then people can get these if they want, because a lot of people have these solderless breadboard power supplies from Amazon, and they do not work well. If you have anything from Amazon, anything from anybody, I guarantee that the 5 volt supply, when it's running off of USB, is not 5 volts. It's going to be 4.2, 4.3, because they're using linear regulators. There's no boosting. So when you get that USB 5 volts, it's always under 5 volts. So you can't regulate to 5 if you don't even have 5 to start with. So you need a boost converter. That's what this has, a boost converter. The 3.3 you can get away with, right? Because you can go from 4.5 down to 3.3. That's okay. But the 5 volts you can't get. Anyway, watch the video, the bonus video on the Raptor power supply if you're interested in that. And then, like I said, at some point I'm going to do a Kickstarter on that. What else? A couple fun things before I go. I wanted to show you, because these videos are kind of just for fun. Totally random. When I used to develop video games for a long time, and one of the first things that I did was back in the 90s was virtual reality. Just when it was starting, I was a chief scientist of one of only 3 companies doing VR in the early 90s. And so I've got to see from the very first VR that was even relatively usable for consumers. VR came out in the 60s. Most people don't realize that. But the first VR that was even tangibly usable was in the early 90s. And the company that I worked for, Visions of Reality, we did 2 games, Cybergate and Tank, location-based VR games with head mounts, full tracking, et cetera, 6 to 10 pods that you would play in. Anyway, the compute took $1 million of supercomputers, $80,000, $50,000 head-mounted displays, and now for $300, $399, you can get these Oculus completely wireless Quest where you can run around and do VR. And I got one a little while ago. Here it is here. And so I'm telling you right now, if you have the money, you need to get this. This is the coolest toy. The optics are amazing. The tracking is instantaneous. This is what we were trying to do, almost 30 years ago with all that money, and we could barely pull it off. And now it's for $399. So, and then, here's like the little hand trackers that you put. So anyway, if you're looking for something new to get into and you're kind of sick of gaming, try that. That's very cool. And another thing, I just got my little 4-year-old. I think I may have showed you guys this before, but obviously I'm into retro gaming. I make retro gaming hardware. So this company, Arcade 1Up, they're doing these arcade games. They're 3/4 size, and these things are gorgeous. They're beautiful. They have LCDs in the electronics, which are kind of a system on a chip, all built into the LCD, and the controls and everything are really, really nice. There's one there. It's kind of on an extra little prop up that props it up. But anyway, they have different ones. The new Star Wars one just came out, and I have the 12-in-1, which is here someplace. Anyway, kind of like this one. This thing is the coolest thing. Now, they've got some bugs. They've got some audio lag and some issues, and the SoCs are running MAME on them and 2 or 3 other emulators to run these games. But I'm telling you right now, if you're a retro enthusiast, these are like $2.99. I mean, the cabinet alone is worth $1,000. You could put a Raspberry Pi MAME in it, or this or that, or whatever you want. The screen is really good. I highly recommend, if any of these things you're into retro stuff, get one of these things. It takes about 2 to 4 hours to put together, and it's just a lot of fun. There are some bugs, some audio lag in some of the games, which is super annoying, but other than that, it's a lot of fun to play. So if you're into retro, definitely check that out. It's arcade1up.com. Can't miss it. So that's it. So hopefully the grounding video kind of helps a little. I don't know, maybe I confused you. And make sure you watch the video. I'll put the link inside of the information. What is ground? It's just what is ground, earth ground / earthing. If you just YouTube for that, rimstar.org, you'll be able to find it. But I'll put the link in there, and you guys can watch that. So that's it. So I will see you on the next bonus video. Bye-bye. Hello everybody, and welcome to another bonus lecture for Crash Course Electronics and PCB Design. So if you're watching this bonus video and you're already enrolled in the course, you know what these bonus videos are. Basically, I come up with some random topic about electronics, computer science. It really could be anything, game development, anything really that I just feel like talking about, and then I'll make a bonus video about it. The majority of them are about electronics, of course, since the course is about electronics, but sometimes I pivot off. Now, if you aren't in the course, then maybe you're watching this video on YouTube, something like that, so then make sure you click the link and check out Crash Course Electronics and PCB Design on Udemy. Anyway, so what I was thinking was I wanted to do another PCB design on the fly right in front of everybody and just come up with some idea and just build it. Now there's a lot of companies, SparkFun, Seed Studio, Parallax, my company, iConstructs.com, we build breakout boards, and we'll put like a chip on there, maybe 2 chips, something simple so you can just play with some particular integrated circuit, right? It might be a sensor, it might be an accelerometer, it might be a relay, whatever. And, you know, you'll go to a company and like SparkFun or Adafruit and buy one of these little breakout boards and then connect it up to maybe an Arduino or a Raspberry Pi or something. Sometimes they'll plug in, for example, it might be a shield that plugs into an Arduino, or maybe it's a, what do they call them, a hat, a Raspberry Pi hat that plugs into the Raspberry Pi, or it might just plug into a solderless breadboard and then you just run wires over to it. But the whole point is there's some chip, some IC that you want to experiment with or use or see how it works, and then you need to somehow to connect wires to it, and you got to solder it onto something. Many of these chips are surface mount, so they're difficult to work with, so you go and find a breakout board. So one of the things as an electrical engineer or an embedded designer that you're going to have to get really good at is building breakout boards. So sure, you can find some things at Adafruit, SparkFun, etc. You know, you might be able to find them on eBay and Banggood also. But the majority of your work as a embedded designer, there's going to be hundreds of ICs, if not thousands, over your career that you're going to need to test, and you're not going to be able to find a breakout board because they're fairly maybe advanced ICs, something like that, where they're just not kind of beginner things that people that would be playing with an Arduino or Raspberry Pi would be interested in. So you have to get good at building breakout boards, and it's a pain in the butt. For example, you know, over here you see me pointing once in a while over to my right, your left, about kind of an area where I have a lot of my prototyping boards, and I've got, you know, LCD displays. Let me see if I can grab one without breaking it all. So for example, let me put it in front of the camera here. So here's, you know, here's something that I had to make just to try out this LCD. So what do we have here? We've got, so this is off the shelf. So this is an off the shelf board that allows kind of these edge connectors to be soldered to them. So you got that, and then we've got kind of a solderless breadboard there. But this kind of prototyping, you're going to have to do a lot. All right, so you have to get comfortable with it. And for example, say you want to play with accelerometers. Maybe you have 10 different accelerometers you want to play with, and maybe you can only find 2 of them from some other company like SparkFun or Adafruit, whatever, that have breakouts. You're going to have to build the other 8. So the point is, you got to get good at being able to do this. All right. So what I thought we would do today is, let's see, let's go over to, let's just go to Google off this. All right. And um, let's do, I was thinking, a lot of people try searching for dinner recipes, funny cat videos. Never searched for that in my life. A lot of people need more GPIO. All right, so when you've got some design, some embedded design, or maybe you're playing with an Arduino or Raspberry Pi, or maybe some small processor like a microchip PIC, and you maybe need some more I/O. So you say to yourself, hey, I'd like to use an I/O expander IC. So that's an IC that you typically communicate over I2C or SPI, and it basically has maybe 4 or 8 or 16 general purpose IOs that you can use from your processor to talk to other devices. So this is a really useful thing. For example, the ESP32, right, the IoT device, is an awesome piece of hardware, but it's got really limited I/O. And of course, the ESP8266 has even got more limited I/O. So these chips are not really made to connect to a lot of peripherals. They have everything built in. So maybe they only have 3 or 4 or 5 or 6 or 10 GPIOs, and before you know it, you've used all those up. So anyway, if we search for GPIO expander, I just want to make sure you know what we're talking about here. So it comes up with some chips here and comes up with some different things. Let's look at some images. So if we look at some of these images here, you can see, and I can tell right off, so there's one, Adafruit has a GPIO expander. This looks like something that's more, this is really nice. So this right here, this is very cool. So if you look at this, what's going on here is they have a bunch of terminal blocks, and then GPIO expander, some different kind of connectors here. Maybe that's power. These are GPIOs here. And then that way with terminal blocks, you can screw them in. So that's kind of nice. Here, if we look here, that's nothing. Let's see. Where else is something? Yep, here we go right here. So this is a very common IC, this MCP23 series, so by Microchip, and I use these a lot. And so you can see they've just got this IC here, and then they have GPIO-A and GPIO-B, and then V sub CC, and this is SPI right here, ground, and a couple bypass capacitors, and that's really about it. So that's a breakout right there. All right, and then you can connect this to anything. So this one, I guess, yeah. So this one's I2C only. So now this particular IC, the 23 series, comes in a SPI and an I2C. So if we do use this MCP chip, which we're probably going to, because I like it and I use it in a lot of things, it comes in different packages. So it'll come in these kind of SOIC kind of looking packages. It might come in a TSOP also, and it comes in kind of a QFP or a QFN, more like this kind of package, right? Something that's a square. All right, so this right here is a QFP. So that's what, here's another one here. This looks like it's by SparkFun. Everything SparkFun makes is red, of course. And if you look here, so in this IC, I believe this is an NXP chip, the PCF. Same thing, just some IOs, and then now this, I'm not real happy with this because this doesn't have any bypass capacitors and all that. So one thing is, again, whenever we're going to design something, we're going to do the schematic design, we're going to do the layout, and that's what we're going to do in this video, and we're going to try and do it really fast. But we want to have a good design. We want to think about how it's used. Now think about this. If you've got a GPIO expander, let's go back to this one. And this thing right here looks like it has 2 ports, right? GPIO-A, GPA, and GPB. If I make all these outputs, right, and then if I look at the data sheet, it says, well, maybe each one can output 25 milliamps, right? Okay, so if I got 25 milliamps and we've got 16 of those, right? What do we got? We got 25 times 16. That's 400 milliamps, right? That's half an amp of current. So we could sink and source a lot of current from this GPIO. So you need to have bypass capacitors. You need to pay attention to noise and be able to have enough current and all that. So you can look at kind of poor designs. So this right here, this design right here, I'm not happy with because I don't see any bypass capacitors, anything like that. And then if you go over here and you look at the this one here, who made this? Is this? I'm not sure whose symbol that is, But anyway, this one's better because I can see some bypass capacitors. So anyway, we don't want to just put, so whenever you build a breakout board, don't just put the chip on a board. Put the chip on a board, put some filtering on the board, put some maybe some protection for some of the IOs, protection for the communication. You know, add a little bit to it. Don't just throw the chips on the board. So because that is really you know, pointless and oh, this is going to go to Adafruit. Yeah, so if you look at Adafruit right here, you know, their designs are always really good. And it looks like, you know, there's some bypass capacitor here and some resistors maybe for current limiting, something like that, who knows. But anyway, the boards are typically like this. They're 2 rows. And then the spacing between these, a lot of times, go to this view here. The spacing between these are so they'll comfortably fit inside of a solderless breadboard, which of course you know what one of those are. Let me grab one here. So let's see here. Where's the camera? So this right here, you know, if you're an Atari fan, this is a Atari 7800 game controller. 7800. This is an Atari game controller. It's compatible with like 2600, 400, 800, and I was doing something with it. But anyway, there's a solderless breadboard. And then if you look at the spacing, if you look at the spacing in the middle here, from side to side, it's across this main row, it's 0.3 inches. So a lot of times the smallest thing you can make is 0.3 inches, or a lot of times you'll see 0.6 inches. And the 0.6 is usually enough space so you can fit an IC. So that being said, this right here, from here to here, may be about 0.6, and it's definitely not 0.3 inches. It may be 0.6, so it can fit in the solderless breadboard and give you enough room to run some wires. All right, and of course, no matter what, we always want to make sure this distance to here is 0.1 inches, and this distance to here across is always a multiple of 0.1 inches, at least 0.3 inches. All right, so those are some of the kinds of things we're thinking about as we're designing a breakout board for anything, right? So we want to put the chip on there. We want to put some power filtering on there. We want to put some protection on there. We want to make it easy to use. Some people might want to solder it to something. Some people might want to put some headers in it. So we'll kind of, you know, we'll leave it like this, and you can put headers in there. And we'll now also you can see this has got mounting holes on here too. So that's another thing. You put some mounting holes on there, maybe so that this could go into another assembly, maybe a big piece of plastic or something like that, and drill holes and then put it all together. You know, whatever. All right. So anyway, that's the kind of thing that we are going to make. And so let's go ahead and start step 1, and which is looking for the part that we're going to use. So we're going to go to DigiKey here, and I'm going to type in GPIO expander, and I think they call it GPIO or IO expander. Yeah, IO expander, 91 items. There's a lot more than 91, but so if you look here, there's a lot of different options here, and you can see there's a few different companies that make these, Semtech, NXP, and then Microchip. We can look here. On Semiconductor, Semtech, Texas Instruments makes a couple of them, Nuvoton, Maxim, Microchip. So I've used more or less all of these different products from all of these different companies, and they all have different features. So some of these GPIO expanders are very complicated. So they might have 8 GPIOs, they might have 16. They might have open drain, they might have push-pull outputs, they might have the ability when something changes when it's an input. So these GPIOs can be used as inputs or outputs. So when it's in input mode, if something changes, the chip can actually generate an interrupt to a processor, which is very useful, so you can go do something or go read that data. All right, so you don't have to constantly pull things. So we like that feature. So we like interrupts. We also like to be able to drive currents, high currents. The other thing we want is we want it to be fast. So now, if we go with I2C, the I2C protocol maxes out at about 400 kilohertz. Sure, there's faster versions of it. You can push it up to a megahertz maybe if you want to, but it's kind of a 100 to 400 kilohertz speed. So let's do some math. All right. So if we're running at 400 kilohertz, right, and now of course we have the whole I2C protocol, right, and say that we have some bits that we want to toggle. All right, so we have to write those bits out serially. So we've got 8 bits per byte. So say if we just have an 8-bit GPIO port and I want to do something with it. All right, and let's say that once we get the processor or the chip into the mode to write, maybe writing only takes 2 transactions. All right, maybe we can just write and then we can write again. So maybe it takes 2 transactions. All right, so we say we've got 400 kilohertz we're running at, and now we're going to have to do 2 transactions, and each one of those transactions is got, we'll just say maybe 10 bits that have to be, shifted out with the AX and the NAX and the data and this and that. So we'll just call it 10. We're going to just be really, really kind of optimistic here. So we'll divide that speed by 20. 2 times 10 is 20. All right. So that's 20 kilohertz. So it takes at 20 kilohertz, we can make a change. So if we want to toggle a bit, we now divide that by 2, right? Divide that by 2, and we got 10 kilohertz. So maybe we can toggle a bit on these GPIOs at 10 kilohertz. That's not very good. And then, I'm probably being way too optimistic. Maybe we can only do that at half that rate, or 5 kilohertz. So that sucks. We don't like that. So really, whenever I do GPIO expanders, unless I'm stuck with an I2C bus and that's all I have on my processor, I will always use SPI. So you see over here the interface SPI. I like using SPI. So what I'm going to do is I'm going to select SPI, and I don't know why I just did that, but we're going to, so that's really interesting. Let's go back here and let's just click IO expand. There we go, 1600. There we go. So, and again, I talk about this in the course all the time when we're on DigiKey. Be careful. We were just on the page, we searched for GPIO expander, and that took us into a sub-search of interface IO expanders, but we actually were in a search of that with GPIO inside of the title or in some text, so that we only got 91 or whatever it was. Now we've got the full 1600. Okay, so be careful. Always make sure you're searching the whole search space on DigiKey or Mouser or whatever it is that you're buying parts from. All right, these search engines are always funny. Okay, so we're going to build this thing, and first thing, let's select it active, number of GPIOs. All right, I'm going to want, we are going to want 16. I want 16 general ones. I want it in stock. I want it row host compliant, and then we're just going to search for cut tape. Interrupt output, yes. All right, and let's apply filters. There's more filters here. All right, now let's see, what kind of interface do we want? We want SPI. We already talked about that. For only 5 remaining. So that worries me. So there's 112, and then if I put it down to SPI only, all of a sudden we only get 5. I don't believe that. So again, the search engine, sometimes when you put another search parameter, search constraint, it over constrains it, and you actually get back way less results. So when I see things change that much, I know there's more than 5 things with SPI in it. So let's just leave that off for now. But what I do want to do is we'll just say push pull. I'd like it open drain and push pull. That would be wonderful, but I doubt I'll be able to find it. And then we can go down here to more filters, and we can see the package in this. So I'm not going to constrain on package. Okay, so let's go here, apply filters. Okay, now let's see what we got here. So this is looking pretty good. So let's go ahead and do that. Okay, now, all right. So starting off here, we've got the NXP chips, and we've got the microchip chips, diodes incorporated, a few Texas Instrument ones. All right, now the other thing is you'll see is they'll say I2C and SM bus, okay? So, what is SM bus? SM bus is similar to SPI, so we'll say SM bus. And then if we go, actually it's similar to I2C. If we go system management bus, and what it's a bus to communicate kind of with motherboards and different things, but take a look at this. System management bus, or SM bus, is a single-ended 2-wire bus for the purpose of lightweight communications. So anyway, it's derived from I2C. It's very similar to I2C, so more or less you can use them interchangeably. So that's what that is, SM bus, and a lot of times motherboards will have it, so you can talk to the motherboard over this bus and kind of interrogate it when the motherboard is doing whatever it's doing. All right, so that's what these things are. All right, so we really want SPI. So let's go ahead and let's constrain down more to SPI. All right, and again, it says there's only 3 things that have SPI. Now let's back out. And again, we're here. I'm going to sit here, and I'm not going to edit this. We're just going to do this in real time. So if we go here and let's just sort on interface, you can see most are I2C, and then some are I2C with SM bus, and then yeah, it looks like Yeah, there only are 3 with SPI in this case. So we're going to take one of those because we want this thing to be fast. Because with SPI, we can run this thing at like 20, 25 megahertz, right? So we can run this thing 50 times faster. So going back to our example, we said we could maybe get away with 5 kilohertz. If we speed that up by a factor of 50, what does that give us? That gives us 250 kilohertz. So we could actually, from our processor, do something almost a megahertz, right? And we could definitely do audio effects and all kinds of things like that. So I want that speed. Also, whenever I'm doing anything with GPIO, I don't want to spend a lot of time talking to the chip with I squared C. I squared C is slow. So if you look at, say, a real-time system, and this is the block of time, right? Every cycle or every processing iteration that I have, if I'm on that I squared C bus this much doing stuff, that's a long time. So I want to be on that real quick. So in my total block, I want to whatever I talk to real quick, and I need to do that with higher frequency protocols like SPI. So we want SPI. End of story. All right, so let's pop SPI in there. Okay. And we only have these 3 things. So you can see we've got kind of these 3 different packages here. They're all from Microchip. And like I said, the microchip stuff I've used a lot and I like it. So these are all push-pull. Now, if you look here, it says that these 2 have this power on reset. This is what this stands for, POR, power on reset. But I bet this one does also. It's just a lot of times so another thing, when you're looking at data sheets and you're looking at online distributors, remember, don't believe everything you read, right? So a lot of this stuff is, copied and incorrect and all that. So you got to, take it with a grain of salt. So all 3 of these are basically the SOIC, the SSOP, and the VQFN, all right? ICs. Now, they should, you would think, have all exactly identical everything, and so I bet you this POR should have been here also. So anyway, let's look at cost. So the cheapest one, they're all really the same except for this guy, a little bit more expensive for this QFN. And QFNs are a little bit harder to solder and all that because of the pad and all that. So why don't we take a look at these 2, the SOIC and the SSOP. So if you look at it, this is 7.5 millimeters wide. This is 5.3. So this one, I think we're going to go with this one. A little bit smaller, a little bit more manageable. All right, so let's see. Now, of course, the problem is, does the tool have a footprint for it? If it doesn't, then we're going to have to make a footprint, which I'm not going to do. So we're going to find something that the tool, and of course we use Circuit Maker in this course along with Lab Center Proteus. But if you're just watching this video, you could use whatever tool you're using, EagleCAD, KiCad, whatever. It's all the same thing. This video is not about Circuit Maker. It's about design and layout. Okay, so if we look here, the part number is this right here. So let's go over to, I've got Circuit Maker fired up here. So we're going to go to Circuit Maker and we'll go to Libraries, and I'm going to plug this in, this SS version, and oh, it does have it. Okay, cool. So it does have this SS version, so we can use that, all right? So if we want to use this particular IC, we can. So let's go ahead, we're going to use this IC. Okay, so that's the chip that we're going to use. So let's get the data sheet and let's take a look at this and see what we're dealing with here, all right? So, and which one we got to be careful. We're using the S, which stands for SPI 17T. All right, so let's open up the data sheet. Same. And then there's 2 variants. We're using the S variant, which is here. So this is the variant we're using here. So let's take a look at the pinout. So we've got GPIO-A 0 through 7. All right, so that's just general purpose GPIO. And then we've got B through 7. General purpose GPIO. Then we've got V sub DD, we've got ground B sub SS, we've got our SPI interface, which is chip select, clock, serial in, and serial out. Serial in, of course, would be MOSA, master out serial in from the processor, and serial out here would be MISO, master in serial out from the peripheral or slave chip, right? Then we've got reset. So this is just to reset this thing. So we're going to be thinking about maybe we want to be able to control that remotely from our host also. Then we've got these 2 interrupt lines. So this is cool. So we're just going to run those out also. And then we've got these 3 lines right here, these address lines. And what these address lines do is these allow you to use different addresses that the chips will respond to when you communicate to them, right? So with I squared C, you actually have an address, right, to communicate to the IC. But with SPI, there is no address. There's just a chip select. You select this chip with chip select, and then it's going to respond. But with these, they allow you to have these other inputs here that give it kind of a global address as far as hardware is concerned. So so once you chip select it, then as you're talking to it with the protocol headers have to match in the SPI data this address right here. So that's what that is all about. So you can have multiple chips all responding to the same chip select maybe, and then depending on the address inside the SPI protocol, then you can activate each one of them separately and have them do something. Okay? All right, so you can take a look here at the block diagram. So again, there's our SPI stuff, right? Straightforward. Now, if it's the plain version, the 23017, then it's got this I squared C, which we can just throw away. And then so this A2 through A0, so this is going here to this I squared C. Now, I was just saying that it also allows it to be used as an address in SPI. I may have been wrong about that. So they may, and we're going to go look at this. So on this S version, this should just be for the SPI version. These pins are either used in a funky way with the SPI, like I told you, or they actually might be unused. So because they're over here and they keep them on both, but we'll actually read about it and find out. So that's, I can't remember. All right, anyway, reset is just reset, and there's our interrupt logic. So when something happens, we can get external interrupts. That's really cool. And then we've just got these GPIOs. And I don't think this data sheet drills down. It might drill down to showing what the GPIO pads look like, but they're usually just two FETs, plus to minus V sub CC to ground, and allows you to short them. Yeah. All right. So, all right. Now, so what you got to do here is you got to read this. All right. So I'm not going to read this. I'm not going to go through this much right now. Right. We're like hardware guys right now. We pretend we don't know anything about software or firmware, and we just want to hook this thing up. Right. So the one thing is operating voltages 1.8 to 5.5, 2.7. All right. So here's these different operating voltage ranges. So now the one thing that we're concerned about is what is the voltage that we can do for the 23S17. Can it tolerate 5 volts? Can we run it at 3.3 volts? Then can it tolerate 5 volt inputs? If we run it at 5 volts, right, is that okay? Can we do 5 volt outputs? But if you look here at this, it seems that any of these ranges will be okay, right? And we can dig down more to see what the situation is as far as, say you've got it at 3.3 volts, can it tolerate a 5 volt input, all right? So you can read about all that and make sure of it. And let's see here. Let's see, look at something interesting. Now reset, now this one, so we say, hey, does this one have this POR, power on reset? And let's see. We're going to keep searching for port here. There we go. The on-chip POR circuit holds the device in reset until the VDD has reached a high enough voltage to deactivate the POR circuit. So when the device exits the POR condition, releases reset device operating parameters, i.e. voltage, etc., must be met to ensure proper operation. So it does have, like we said, it has a POR, so it has its own POR. So we can just let that do whatever it does, or you can probably put a 100K pull up on that if you just want to be comfortable that something's pulling it up real weakly, and we're probably going to design that in. Now, let's look at the I squared C interface. All right, so if we look at the I squared C, which we're not using, all right, then let's see here. Let's see. I want to go to where we talk about protocol here, and yeah, so it does look like, so addressing SPI devices, so the S17 is a slave device. Now, if enabled via iocon.haen, pins A2, A1, and A0 with a read-write bit filling out the shows, okay, so it does have a slave address. So the whole idea is, even though it's an I squared C device, it will not respond unless excuse me, unless over here in SPI, the external hardware matches these 3 bits, all right? So that gives you this kind of flexibility. It's sort of like an I2C device. You don't have to have multiple chip selects. That's what that's all about. Now with I2C, these definitely are necessary because that builds up its address, right? That builds up the 7-bit address. But in SPI, these things are inside of the protocol, but they're enabled via this iocon.haen. So this is an internal register. So when this thing boots up, what's going to happen is it's going to be in some state so that no matter what these are, you'll be able to talk to it. Then once you enable this, right, then only if it matches what the external A0, A1, and A2 are will the thing respond. So I was right that it was using them, and like I said, it's you got to just read through these things and try and remember what's going on. Okay, so that means we're going to export these out on our breakout as well. Okay, now let's see. And again, this data sheet it's not too long. It's like, how big is this? 42 pages. Yeah. So you got to, I've read this thing before, of course. You just got to read through it all and figure it out. And then if we look at what I want to see here is if there's any, yeah, okay, so yeah, supply voltage 1.8 minimum, 5.5, typical 1, and then there's a little note, and it says parameters characterized but not 100% tested. Anyway, go ahead and run this thing at 3.3 or 5 volts. It'll be fine either way, and I can tell you this, that say you're running it at 3.3, and you want to output and talk to a 5-volt device, it will tolerate the 5-volt inputs and it will drive 5-volt outputs, because a 3.3 to the rail is definitely a 1 as far as CMOS is concerned, so it can be used in either way. And of course, it'll be completely compatible with 3.3 or lower voltages like 2.5 or 1.8 is where it starts getting iffy. Okay, so that's it. That's our chip. All right, so this is what we're going to use. So we're going to keep this right here so we can mess around with this and look at it. All right, so let's go ahead and go create a new project. So I'm here in Circuit Maker. Again, if you don't know how to use Circuit Maker, I use it in the course. You will learn this entire package when you do take the course, if you were to take the course. But for now, whatever you're using, we're just going to create a new project here. So we're just going to say add new project. All right, and we're going to make it public, and then we're going to call this, what is this, GPIO, let's call it Crash Course Electronics, and we'll call it GPIO, and then we'll say expander. Did I spell that right? GPIO expander looks good, and this is just a generic GPIO expander breakout board, and that's it. Good enough. Okay, so let's save that. Okay, and we don't need anything here. It's public concept. Don't need to mess with any of this stuff, and we'll just put, what is this right here? These are the different licenses, and again, the reduce the commercial as long as it's parcel, just license most restricted. We want to put just makes tweak work on a commercial. Yeah, this one right here, I think, is the basic one that lets you do whatever. Doing this for open source. Okay. All right, good. So now we can go ahead and say open design. All right. And there it is. Okay, so now in the design, there's nothing in it right now. So let's go ahead and let's add. So let's start off and let's add new to project. We need a schematic. All right, now my naming convention is I always name it the exact same here. So I'm going to call this GPIO, and I'm going to call this expander. And then this is version 001, and then what I do is I have 2 or 3 digits, which is the iteration. So as you're doing design, like I'll do an iteration, another, but it's still the same version. So I kind of do this kind of convention, which works. All right, and then we'll go ahead and we'll add also add new to project. We'll add a PCB. We'll do the same thing. All right, and your tool, whatever you got to do that. Okay, and then up here we got this blank circuit. Okay, so there's not much in here. One thing is I usually like to make these a little bit bigger. So let's see, where is that? Now, another thing, I use a lot of tools and lots of tools, and I become expert at them and then I forget about them. So between designs of Circuit Maker and Proteus and other Altium tools and this and that, and all these different things, I forget how these things work. I am human. So sometimes you'll see me kind of waffling around trying to figure it out, and that's okay. So to change the document size, we go here, and I'm trying to remember if, yeah, that's big. We want it smaller. So we want to make this smaller. So we have enough room, but we don't want this crazy. It's a fairly simple design. Let's try A2 size. A2, and maybe let's go one more smaller. Little bit too big still, huh? Okay, we'll go to A3. There we go. That's kind of what I want. Okay, now there's nothing in here, so now I'm going to save, and I'm going to go ahead and save this project. And then you got to do this, and then you have to go ahead and commit it. All right, and then it's going to commit it to the cloud, to the Circuit Maker Altium Cloud, Vault, whatever they call it. All right, so we're doing pretty good. We're about a half hour in, so I'm going to try and get this done in a total of an hour. So I'm going to start going even faster now. All right. Okay, so we're all good. This is it. All right, so we got our design right here. Now, another thing, when if you're a designer, electrical engineer, obviously you don't want to start from scratch every single time. So inside of my account, I've got lots of projects from the course, and here's one right here. This is a power supply from another bonus video. It's called the Raptor PSX, and this is a surface mount a PCB power supply. But why I like it is it's got a lot of parts on it that we're just going to steal and use, so I don't have to go searching through libraries and confirming they exist. All right, so we're going to use some of this stuff on here to just speed things up and copy and paste like resistors, capacitors, whatever, so I don't have to kind of search for parts. All right, so the first thing that I want to do is I want to go down and lay down our IC. So we're going to go place. All right, and we're just going to pop it right here. And let's zoom in so we can see what we're doing. Okay, first thing is I do not trust anyone or anything. So what I want to make sure of right now is that the pinout here is actually correct. Okay, and so a lot of you guys know that I develop gaming hardware, and so I just I finished developing the new Intellivision Amico game consoles controllers, the electrical design for the controllers. So one of the other electrical engineers who's working on the console, there's a couple of them. So as he was doing something, one of the ICs laid down, right, which is a massive not FPGA, but BGA, ball grid array. Apparently, either there was a mistake and maybe it would lay down one pin off, or the footprint was one pin off, but the bottom line was the footprint and what it was supposed to be didn't match, and like you make that kind of mistake, the whole thing is shifted, it won't work. So we are going to look and always make sure, don't assume anybody did anything right. Everyone makes mistakes. This is stuff that's very easy to get wrong. All right, so we're going to go through here and look. All right, so GPIO-A looks like it's 21, 22, 23, 24, 25, 26, 27, 28. GPIO-A, 21, 22, 23, 24, 25, 26, 27, 28. Good. GPIO-B, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, ground is 10. Very important that the ground is in the right place. 10. B sub DD, 9. And remember, I'm using the S version, so I'm paying attention to that also, right? All right, let's see. Interrupt A and B is on 20 and 19 respectively. 20 and 19, that's correct. Reset is on 18, that's correct. My address bus here is 15, 16, 17 incrementally. 15, 16, 17 incrementally, that's correct. My chip select is on 11. Chip select is on 11. Clock is on 12. Clock is on 12. SI is 13. SI is 13. 14 is S out. 14 is S out. And I'm happy. All right, so now I know that that is correct. Okay, so that's correct and good. I still don't know if this footprint is totally accurate though, right? So really what we need to do is we need to kind of, once we do the layout and we pop this thing down and we see this footprint, we're going to go to the mechanical of this chip and we're just going to do a sanity check. We're going to check the pitch between the pins and we're going to check the width between the pins. Just do a sanity check and make sure, because you design the whole thing, you got the wrong footprint, you're going to be pretty mad, all right? So, all right, so what do we need here? All right, what do we need here? Let's go ahead and, so if we look here, and there's a billion ways to do this, right? we've got two GPIOs. We can put them on each side of the board, so we can have a board where on one side is GPIO, one side is GPIO-B. We can do that. Then maybe next to one of them we can have the control bus, right? Or we could put both GPIOs on one side and then the other side the control. You can do anything you want, right? The whole idea is just whatever's convenient and kind of small so you can kind of work with it, right? So we'll mess with that in a second. Right now, let's go ahead and let's start putting some hardware down, okay? All right, so the first thing is let's get power in here. So I'm going to bring power in. Let's clean the power up a little bit. Let's filter it a little bit. So what I'm going to do is I am going to get a couple. This is a GPIO expander. I want this power really clean, right? So this is an 805. So that's an 805. So this design, everything is 805. So I'm going to just copy these right. You know what? As a matter of fact, yeah, I'm going to copy these right here. Now I'm going to copy this whole thing. Copy this whole thing. I'm going to copy this whole thing. All right. So everybody knows, if you take my class, I'm really, really, really into power. I build a lot of power supplies for companies, and so I like my power to be really, really, really clean. All right. So that typically means filters. All right, so right here I've got a ferrite filter, so this is going to get rid of any high frequency noise because I don't want that getting into this chip. This is probably overkill, but I don't care. All right, so then let's move these right here, okay, and move this right here. Okay, and then where's our power right there? So this is pretty good. Oops. And I'm just going to kind of put this right here. So V sub CCN, that's what we're going to call it. All right, let's put some wires down here. Just like that, and then there's our V sub DD, and I'll just put this right here. Looks good. Let's get a ground, copy, paste, and W for wire again. All right, so there we go. So now I've got power, and I'm calling this V sub CC in. These capacitors, let's change these a little bit. So let's think about this. So 0.1, I want that right there is for high frequency noise, but I'm going to leave this as a 22 microfarad. I want a big capacitor because remember, you know, someone drives all these IOs. You could drive a ton of current in and out, and it's going to be hard to get that current. Where's that current coming from? Well, it's got to go here, it's got to go back through here, it's got to go back through the wire, it's got to go back to the cable, it's got to go back to the regulator. That's a long, long way. But if we have a capacitor right here, we can source that current, right? And we can mitigate trying to pull that current back from the power supply and having any voltage dips. So we're going to leave that as 22 microfarad. Very important on big GPIO expanders. Don't be afraid to put a big bulk capacitor on here. And this isn't a bulk. It's not like 220 or 1,000 microfarad. But for an IC, it's pretty big. But it's a GPIO block. It's going to drive a lot of current. And I want to be able to drive that current. Okay, so we got that. Let's see here. What else? Is there anything else we need? Okay, so on reset here, what we could do if we want is we're gonna bring this out a little bit here, and then what I can do is since I want to make sure this thing always resets, now even though it always resets with power, right? I want to make sure it doesn't kind of float or do anything weird. So I'm just going to put a weak pull-up on here. Okay, so let's go get a resistor. So we're just going to go get a generic resistor. All right, there's our generic resistor, and I can already tell you that this is 805 size. It should be. All right, I'm just going to put this. Matter of fact, I'm going to put this, like this. Sometimes you see this kind of horizontal design. A lot of times I like to put pull-ups up, right? You can do that, or you can put it kind of horizontally to power. Kind of depends on what you want to do. So you kind of decide, and we're going to call this R1. So let's start changing some of these reference designators. Let's make this 100K. Hey, and no one said we have to place this resistor, right? But it's good design. Okay, I'm going to go like that, and then W again puts down wires in this tool. All right, and now we need power, so that's going to be V sub CC in. Now, if we connect this directly here, right? So here's one thing. So here's V sub CC in. Here's where V sub CC is filtered, right? So we can take V sub CC in and just put it to this pull-up, but that's kind of the noisy power coming in. We kind of want kind of the cleaner power after our little filter here, right? So we might go ahead and put another label here. Not going to hurt us. We can put another little label here. In fact, I can put the label right here, all right? And that'll be the same. And I can put that label right here, and I can call this V sub CC in F, okay? Filtered. So now this is the filtered version of it, and now I can put that up there if I want to, and then I know that this is a little bit cleaner power, right? A little bit cleaner power, all right? Good. Okay, so Control S, always Control Sing. So now that's about it. We got our interrupt A, we got our interrupt B, we've got our bus here. Same thing. So on the chip select here, say that you've got this chip connected up, right? But you've just got power. You don't have it to a host, and maybe all these GPIOs are actually connected to some device now that you've built, right? Well, I don't want noise just running around on here and writing registers. Who knows what weird stuff could happen on clock and all that. Maybe it does something. So let's go ahead and make sure that this chip doesn't do anything when it's off, okay? So we're just going to go ahead and I'm just going to pull up chip select also and make sure this thing is not, inadvertently chip selected, okay? Fair enough. Just a little protection, all right? I'm going to put that right there. Good. Okay, so now I've got chip select, we got everything here. So let's go ahead and let's put some labels here. Now, old school electrical design, you kind of connect everything with wires, right? And there's nothing wrong with that, but moving things is very difficult. You got to drag all the wires. So kind of new school is you kind of put labels or ports on everything. That way you can just grab a block and move it and you don't have the wires. So I'll connect a few little ones that are localized, but kind of things that are going to connect to other blocks. I'll use net identifiers or ports, that kind of thing. So let's go ahead and get some over here. There should be some lying around. Here we go. Okay, so we got, let's get this green one here. All right, and let's go over here. All right, and I like color coding. I do software obviously also. So everything I do, I like to be color coded. All right, so let's go over here. And this one, so this should be, I want this to be bidirectional. IO type. Let's see. I'm just going to say bidirectional. I just want the arrows. Now I don't really care. I don't go into all that making, ports have the right iconography for input, output, power, this, that. That's just too much, right? It's just too much. That's too anal, right? But I like the two arrows. All right, so what I'm going to call this here is I'm just going to call this GPA 0, all right? And then let's make this smaller, okay? Because it's going to have to hold 2 characters at some point. Cool. All right, now I'm going to take that and copy it. All right, now watch this. Okay, and let's copy that. Do everything in binary. All right, and let's go and over here. This one's going to be GPIO B, right? And let's go change the color right now. So we got kind of this green here. What do you guys think? You want to do red? We'll do red and black, maybe a little lighter. Let's do red. Why not? That's cool. I can still see that. Okay. All right. We'll do red. No, you know what? I don't like that idea. Let's make it blue. Let's make it blue. We'll do red for power. All right. Make it blue. Okay. And then the text is a little bit hard to read. So we'll go to text color and we'll make that white. Good. How we doing on time? Okay. All right. Okay. Now we're going to copy this. Okay. All right, now let's go fix these. So GPIO 0 and 1 and 2. And of course, I have no one to tell me I'm doing anything wrong. So I'm doing this in real time always. So sometimes I'm scanning at the same time I'm talking here. So hopefully I'm not making any mistakes. And if I have, you're probably saying, Andre, fix that. It's driving me crazy. But I don't think I have yet. All right, and let's go here to 1. Okay, this will be 2. Okay, this will be 3. This will be 4. This will be 5. This will be 6. And this will be 7, right? Okay, cool. That looks good. Let's go ahead and let's put some wires in here. Put some wires. And again, how you do wires in circuit makers, you press W, it goes into wire mode, and then you can just click with the left mouse button and start and stop each line. All right, and see a little crosshair, put it right there. And we do this. Looking good. All right. My save finger is getting twitchy right now, so I want to save this. So right when I get done here, good. And Control S, save, okay. Back it out, looking good. All right, what do we need here? Let's call this, so the SPI bus, let's go over here. So the SPI bus, and let's go here, and we're gonna call, so I'm gonna name this a little bit differently. I like using like actual SPI names for things. So this is SPI chip select. So, and I call anything that's inverted, I put an N on it, right? So that's SPI chip select. All right, now let's put these others, and let's color this also before we go any farther. How about SPI? SPI, I don't know. What does SPI feel purple to you guys today? Purple. My wife likes this color, purple. All right. Is that okay? Yeah, I think so. Should we make it white? Should we make the text white? A little bit easier to see. What do you think? Yeah, that's better. Okay, so let's take that, and we've got these three right here. 1, 2, 3. All right, so that's chip select. Now we need clock. SPI S clock. And then what's the next one? This is serial in, so be careful. So this is going to be master out, serial in. All right. And okay, so now we see we need to make these a little bit bigger to fit everything. So I'll just go like that, and I'll go like that, and I will go like that, and like that. Okay, and what's this one? This is MISO, master in, serial out. So this is master in from this device. Okay, let's go lay down these, fix these wires. Okay, oops. And I unless I'm doing something really repetitive, I don't do speed up the video, right? I like you to see what I'm doing. Okay, there's not a mistake. I haven't even done all this yet, but that make that R2. And while we're down doing that, let's go make that ferrite bead 1, and let's make this C1, and we'll make this C2. Okay, looking good. Control S. All right, getting happy. All right, and then the last thing we have our two things, address bus and our control bus, I'll call it. So on the address bus, so this is the same thing. So on the address bus, we want to, again, to be able to select this, but maybe I don't want to hook this thing up, right? Again, less wires to your breakout board is always a good thing. So the more things you can kind of put on the breakout, that's what these pull-ups are for. It's less work. I don't have to wire things. So why don't we, again, do something here where we put something to each one of these. We could do pull-ups or pull-downs. We could put it at 0, 0, 0, or we could put it at 1, 1, 1. Let's see. Let's go ahead and of course we could also hard code it on here so that you can control it, but it can be changed where we can put a pull up and a pull down, and then you can either populate either one, right? So that's another option you can do. So maybe you want to have multiple breakout boards, right? So let's not get too fancy here. We're trying to do this fast. We're not trying to build an Iron Man suit. So why don't we just go ahead? Let's just pull these things all up. We'll just pull them all up. And that way the address is just going to be 111, end of story, unless you put something different on it. We'll keep the pull-ups weak, all right? So that's R1, R2, 3, 4, 5, all right? But these are the kind of decisions, that you got to make, and, there's no right and wrong decision. There's just, you just decide what you want to do, and kind of figure it out, all right? And kind of do this. They're all going to the same place, so we don't have to copy the power each time. So, again, the way that I think is this is kind of the same devices doing the same thing. So I'll hook it up to the same kind of power, even though these are all completely identical, right? Why didn't I connect both of these here? Yeah, I could have, but they're on two different kind of pins. So I kind of keep them separate, maybe because later I want to put these to different things. But since these are all kind of doing the same thing, I'll just have one node here and I won't have to copy VCC in filtered 3 times. That's all, just personal choice. Keep everything clean. Okay, so now we're going to go here. And okay, so now let's be careful here. Let's do this in the least amount of crossing wires. So there we go, like that. Okay, cool. And now we need three guys for this. So I'm just going to copy this right here. And where are you? You're right there. Okay, let's go here and let's go and make these. I'm feeling. What am I feeling? I'm feeling kind of cyan. No, I'm kind of feeling orange. Yeah, let's do orange. And let's see how that white works. That white now so that white's a little bit hard to see. So let's go ahead and make it back black, orange and black. Okay, that's cool. All right, I don't want to have to go change those colors twice. So I'm just going to go here. I'm going to go like this, like that. Okay, and now this is going to be A0. This is going to be A1, and this is going to be A2. I could make these port labels the same smaller width. They don't need to be as big, but I kind of like the consistency of it rather than, a bunch of different sizes. So I'll just leave them like that. Okay. So again, there's a decision for everything. You got to be thinking about everything, right? Okay. Those are done. Okay, so we're almost done. So there's our address bus. And now let's go here and let's get our final control bus. All right. And matter of fact, so we don't have to do, because we're going to change the color of this. Let's make this one yellow. All right, we'll make this one yellow. Okay, and we're going to use black. That does look good. Okay, good. All right, we're going to copy that. And there and there. All right, so here we go. So here's reset. So I'm going to call it reset N. This is interrupt A. I'm just going to call it what it is. This is interrupt B. Now, here's another thing. This chip is configurable so that these interrupts are either active high or active low. They also can be tied together, so you can do a lot with these interrupts. So you can just use one pin that'll get interrupts from both port A and port B. You can, I think you can make it open drain, you can make it push pull, you can do all kinds of cool things. It's got lots of different settings, is my point, that will help you integrate it into your processor. All right. Okay, so now we have